Hey guys, good evening and welcome back again to your Unacademy NEET English channel. My dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats with some fire emojis. Good evening everyone, good evening and welcome back. Good evening and welcome back. Good evening and welcome back, my dear students. Quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Yeah? So, my dear students, all ready for the session for the Mega Marathon number 1? Are you all ready for the Mega Marathon 1? Yes? There should be the super high Josh in the chats. There should be the super high Josh in the chats. Welcome back, welcome back, welcome back, welcome back. So before starting this particular session, which you know is our Mega Marathon, right? This is the first session which we are taking. And my dear students, today, I will be completing your entire class 12th physical chemistry. I will be starting exactly from the basics. I'll be starting exactly from the scratch. I'll be covering all the theory, all the problems which can be asked from the class 12th physical chemistry in very much detail, right? But for that, I would want to know whether you guys will be with me till the end or not. Because you know, the session duration is going to be almost 12 hours, right? So are you going to be with me this night or not? Yes or no in the chats, everyone. Yes or no in the chats, everyone. Well, it's not my birthday today. My birthday is on 6th of April. Okay? My birthday is on 6th of April. I just want to know whether you guys will be with me till the end or not. Perfect. This is something which I wanted from all of you. Okay, one small question I'm asking you. Which part of the country you guys are watching this particular session from? I mean, which state you guys are from, basically. I just want to know where the majority belongs from. I just want to know where the majority belongs from. Quickly. I just want to know where the majority belongs from. Which part of the country you guys are watching this session from? All right, Karnataka, MP, Punjab, Delhi, Kerala, Tamil Nadu, Surat, Hyderabad, okay, Telangana, MP, Rajasthan, Kashmir, Assam. Wow. Amazing, amazing, guys. Amazing. Amazing, amazing. All right, before starting this particular session, one thing which you have to do, which is absolutely free for all. Right now, I would want every one of you to like this session, okay, and subscribe to your Unacademy NEET English channel so that you remain updated about all the sessions which we are planning to take on this particular channel. So do smash the like button right now, which will definitely keep us motivated as well, okay, which will definitely keep us motivated as well. I can see almost 2,200 people are watching live, and only there are 1.4k likes. That's not that's not good. That's not good, guys. Yeah. So take the likes to 2,200 quick. Yes, we are going to complete this entire series. Don't worry. This entire series will be completing. Don't worry, guys. Don't worry. Don't worry. All right. Amazing. Amazing. Right now it's at 1.9k. Make it to 2k right now. Then we'll be starting. Yeah. Yes, yes, I'll take care of myself. You guys take care of yourself too, okay? Because you have to be with me for 12 hours. You have to be with me for 12 hours. Perfect, perfect, perfect. All right. So my dear students, since we are going to complete your class 12th physical chemistry in the today's session, so tell me one thing. Which chapter of your class 12th physical chemistry you want to start with? Just tell me that. Which chapter of your class 12th physical chemistry you guys want to start with? And the majority wins here. Majority wins here. Someone is asking, can we watch this session if we have zero knowledge? As I told you, I'll be starting exactly from the basics. I'll be starting from the scratch. No need to worry. I will be starting from the scratch. All right, all right, all right. I can see majority of the students want to start with the chapter solution. Is that? Majority of the students want to start with the chapter solution. Or let me just do one thing. Let me create a poll so that I'll get to know which chapter do you want to start with. Just a second. I'll create a poll once. Just a second. Just a second, people. Just a second. Okay, tell me now quickly. Which chapter you want to start with? Quick. All right, I can see majority is starting. Majority wants solution chapter first. Majority wants solution chapter first. Majority wants solution chapter first. All right, all right, all right. All right, amazing. So my dear students, without wasting further time, let's directly get started and let's start with the chapter solution. I knew it already, you guys are going to say, let's start with the chapter solution. Okay, one thing I want from all of you, whatever things I'll be writing on the screen, I want you guys to take a note of every single thing. I want you guys to take a note of every single thing, my dear students. Okay? Because every single thing is going to be equally important in the today's session. So, let's start with the first chapter of our class 12 chemistry, and you know already the name of the chapter, that is solution. And one thing I would want to tell before starting, my dear students, don't worry, I'll be giving you the breaks, small breaks in between as well. Okay? After every 3 hours, after every 3.5 hours, I'll be giving you some 20-minute breaks so that you can refresh, have some food also, so that I can also have some food in between. Yeah? Okay? Perfect, my dear students. So first of all, my dear students, if I talk about the term solution, as you all must be familiar with the fact, solution, it consists of two components. One is called as solute and one is called as solvent. If I talk about the term solution consists of two components. One is your solute and one is your solvent. Now, my dear students, what is solute exactly and what is solvent exactly. Remember, solute is that component. Solute is that component of the solution which is present in lesser amount. Which is present in lesser amount. And if I talk about solvent, solvent is basically that component of the solution which is present in larger amount. Which is present in larger amount. Okay? So I would say, if I talk about solution from now onwards, solution, it consists of two components. One is going to be your solute and one is going to be your solvent. Right? As simple as that. Solute is that component of the solution which is present in lesser amount. Solvent is that component of the solution which is present in larger amount. Point number one, complete basic thing. Right? My dear students, few basic things which I would want you guys to remember from now onwards. From now onwards, solvent you are going to represent with either number 1 or you are going to represent it with letter A. Solvent you guys are going to represent either with number 1 or you will be representing it with letter A. If I talk about solute, solute you are going to represent with either number 2 or you are going to represent it with the letter B. Okay? This will make our things very easy. Solvent will be represented by 1 or A. Solute I'll be representing with 2 or B. Okay? My dear students, one more thing. There are few terms which I'm writing here. For example, I'm writing W. For example, I'm writing N. For example, I'm writing M. For example, I'm writing E. These are some basic terms which I'll be using in this chapter. And let me tell you, what does W stand for? W stands for the mass of substance. W stands for the mass of substance. N stands for number of moles of the substance. Right? M over here will stand for molar mass of the substance. M will stand for the molar mass of the substance. And in the similar way, my dear students, E will stand for the equivalent mass of the substance. Okay? W stands for mass of substance. N stands for number of moles of substance. M stands for molar mass of the substance. And E stands for equivalent mass of the substance. Now, my dear students, one more important thing. For example, sometimes if I write W2, what is meant by W2? Since W stands for mass and 2 stands for solute, that means W2 stands for the mass of solute, that too in grams. Okay? For example, sometimes if I write W1, W1 represents the mass of solvent. The mass of solvent in what? In grams. Sometimes, for example, if I write N2, what does N2 stand for? Since N stands for moles and 2 stands for solute, therefore N2 would be called as the number of moles of solute. The number of moles of solute. And my dear students, in the similar way, for example, sometimes if I use the term M1, for example, let's say M1, since M stands for molar mass, 1 stands for solvent, so M1 would be called as the molar mass of solvent. Okay, these are some basic things which you need to know before starting the chapter. Number 1. Number 2, my dear students, there are few, again, basic terminologies which you should know. What are those basic terminologies? Sometimes I'll use the term binary solution. Sometimes I'll be using the term binary solution. Okay? What is a binary solution? My dear students, in case of binary solution, you will have 2 components. You will have 2 components. In case of what? In case of binary solution. Right? And out of those 2 components, there would be 1 component of solute, 1 component of solute, and 1 component of solvent. Okay, in case of binary solution consists of 2 components, out of which 1 component would be for solute and 1 component would be for solvent. Similarly, my dear students, sometimes I'll be using the term ternary solution. In case of ternary solution, how many components will be there? There'll be exactly 3 components. And out of these three components, let me tell you, there will be two components of solute and there would be one component of solvent. There would be one component of solvent. And my dear students, sometimes I'll be using the term quaternary solution. Sometimes I'll be using the term quaternary solution. And in case of quaternary solution, how many components will be there? There'll be exactly 4 components, out of which there will be 3 components of solute and 1 component of solvent. 1 component of solvent. And my dear students, sometimes I'll be using the term aqueous solution. Sometimes I'll be using the term aqueous solution. And in case of aqueous solution, do remember, in case of aqueous solution, the solvent used, in case of aqueous solution, the solvent used is water. In case of aqueous solution, the solvent used is water. So these are some basic things which you must know before starting this particular session. Okay? Am I clear to everyone? Am I clear to everyone, people? I believe yes. Okay? Now, my dear students, the first topic which we are going to start in this particular chapter, which is the favorite of all of you, what is that? That is concentration terms. Where do you get the notes? Notes, handwritten notes of the today's session, I'll be sharing on my Telegram. Okay? If you are not the part of my Telegram, be the part of it. The name of the Telegram channel is Wassim Bhat Chemistry Official. WASSIM BHAT Chemistry Official. That is the name of my Telegram channel. Okay? Perfect. You can be the part of it. On that particular Telegram channel, I shall be sharing the handwritten PDF of the today's session. All right, people. The first topic with which we are starting today, that is your concentration terms. And in case of the concentration terms, what is something which we are going to discuss first? What is something which we are going to discuss first? The first thing here is what you call as weight by weight percentage of solute. Weight by weight percentage of solute. Okay, weight by weight percentage of solute. Or you can call it as the mass percentage of solute as well. Weight by weight percentage of solute, or you can call it as the mass percentage of solute as well. Now, how do you define the weight by weight percentage of solute? My dear students, it is simply defined as that mass of solute in grams which is present in 100 grams of solution. That mass of solute in grams, which is present in 100 grams of solution, that is something which you call as weight by weight percentage of solute, right? For example, if you have got 100 grams of solution, let's say in 100 grams of solution, there are 20 grams of solute. Let's say in 100 grams of solution, there are 20 grams of solute. So you can directly say weight by weight percentage of solute is 20. Let's say in 100 grams of solution, there are 30 grams of solute. You will directly say weight by weight percentage of solute is 30. Let's say in 100 grams of solution, there are 40 grams of solute. You will directly say weight by weight percentage of solute is 40. So as simple as that. That mass of solute, which is present in 100 grams of solution, you call that as weight by weight percentage of solute. Number 1. My dear students, how do we exactly calculate this weight by weight percentage of solute? You have to remember one formula here. Weight by weight percentage of solute is calculated as the mass of solute in grams divided by the mass of solution in grams divided by the mass of solution in grams multiplied by 100. This is how you calculate the weight by weight percentage of solute. In the similar way, if they ask us to calculate weight by weight percentage of solvent, how do we exactly calculate it? It is again going to be mass of solvent in grams divided by mass of solution in grams. Mass of solution in grams multiplied by what? Multiplied by 100. These are the two results which I would want every one of you to remember. Okay. Now, my dear students, note one thing. Take a note of one thing. In case of your binary solution, In case of your binary solution, you can say weight by weight percentage of solute plus weight by weight percentage of solvent. Weight by weight percentage of solute plus weight by weight percentage of solvent. It's always going to be what? It's always going to be 100. This is one more thing which I would want every one of you to remember. So this was, my dear students, this was our first term, that is weight by weight percentage of solute. I believe I'm clear to everyone. Okay? Perfect, guys? Perfect. Now, I'm moving on to the second terminology. What is that? That is weight by volume percentage of solute. Weight by volume percentage of solute. Now the point is, how do we define the weight by volume percentage of solute? Understand properly. Let me tell you, weight by volume percentage of solute is defined as, the mass of solute in grams. The mass of solute in grams, which is present in 100 ml of solution. What was weight by weight? That was 100 grams of solution. In case of weight by volume, we have 100 ml of solution. Okay? That is the difference here. So people, I can clearly say weight by volume percentage of solute is nothing. It is that mass of solute in grams which is present in 100 ml of solution. For example, in 100 ml of solution, let's say there are 20 grams of solute. In 100 ml of solution, let's say there are 20 grams of solute. What does that mean? That means weight by volume percentage of solute is 20. Let's say in 100 ml of solution, there are 30 grams of solute. That means weight by volume percentage of solute is 30. Let's say in 100 ml of solution, there are 40 grams of solute. That means weight by volume percentage of solute is simply 40. So remember the definition from now onwards. Weight by volume percentage of solute is nothing but it is that mass of solute which is present in 100 ml of solution. Okay. Now, my dear students, remember its result as well. Weight by volume percentage of solute is calculated as the mass of solute in grams divided by the volume of solution in ml multiplied by 100. This is the result which I would want every one of you to remember. Weight by volume percentage of solute is equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. Similarly, my dear students, sometimes if I need to calculate weight by volume percentage of solvent, and as per the formula, it is nothing but it is mass of solvent in grams divided by the volume of solution in ml multiplied by 100. Okay, multiplied by 100. Okay, these are the two results which I would want every one of you to remember. And my dear students, at the same time, take a note of one important thing. Remember, weight by volume percentage of solute. Weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by the density of solution in grams per ml. Okay, well, it is one result which I'm not deriving here. I'm just giving you the result, right? So that we can apply this result in the questions. Weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of the solution in grams per ml. Okay, remember this particular result as well, because this is again super important. Okay, perfect. Now, my dear students, the third terminology which I'm using here. What is that? That is volume by volume percentage of solute. Volume by volume percentage of solute. And how do I define volume by volume percentage of solute? You should know it as well. Let me tell you, volume by volume percentage of solute is nothing. It is basically that volume of solute. It is basically that volume of the solute in ml which is present in 100 ml of solution. Let's say in 100 ml of solution, let's say there are 20 ml of solute. In 100 ml of solution, let's say there are 20 ml of solute. What does that mean? That means volume by volume percentage of solute is 20. Okay, right? Perfect. Questions will be doing in some time. First of all, you should know all these things. First of all, you should know all these things. Okay? So my dear students, remember, in 100 ml of solution, if there are 20 ml of solute, that means volume by volume percentage of solute is 20. In 100 ml of solution, if there are 30 ml of solute, that means volume by volume percentage of solute is 30. If in 100 ml of solution, there are 40 ml of solute, that means volume by volume percentage of solute is 40. As simple as that. As simple as that, right? So, volume by volume percentage of solute is nothing but it is that volume of solute in ml which is present in 100 ml of solution. Okay, which is present in 100 ml of solution. Perfect, my dear students. Perfect. I believe I'm clear till here. I believe I'm clear till here. Now, the result with the help of which you guys are going to calculate volume by volume percentage of solute. It is always equal to volume of solute in ml divided by volume of solution in ml multiplied by what? Multiplied by 100. This is the result with the help of which you can calculate volume by volume percentage of solute. Volume by volume percentage of solute. Okay? Right? Similarly, my dear students, sometimes if they ask you to calculate volume by volume percentage of solvent, it is equal to volume of solvent in ml divided by volume of solution in ml multiplied by 100. This is one more result which you guys will be remembering from now onwards. Volume by volume percentage of solvent. Okay? Perfect? Perfect, people. I hope every single thing is clear till here. Now, if these things are clear, I'm writing 3 statements here. And you guys are going to tell me the meaning of these 3 statements. First statement I'm writing, 10% weight by weight of NaCl aqueous solution. This is my first statement. You need to tell me the meaning of this particular statement. The second statement I'm writing, 10% weight by volume of NaCl aqueous solution. This is the second statement. The third statement I'm writing, for example, 10% volume by volume of, for example, NaOH aqueous solution. Now, I'm asking you all to decode these 3 statements. How can we decode these 3 statements? How can we decode these 3 statements? 10% weight by weight of NaCl. What does that mean? It means that 10 grams of NaCl are present in 100 grams of solution. Okay? Here you have got weight by volume. It means that 10 grams of NaCl are present in 100 ml of solution. 100 ml of solution. Here you have got volume by volume. What does it mean? It means that 10 ml of NaOH, 10 ml of NaOH are present in 100 ml of solution. Tell me once in the chats if these 3 statements are very much clear to all of you. Tell me quickly in the chats, my dear students. Tell me quickly in the chats. Tell me quickly in the chats. I want you to be super active in the chats, people. Everyone. I want you to be super active in the chats. Everyone. Perfect. Perfect. Amazing. Amazing, guys. All right. Now let's have a look on our third terminology. Sorry, the fourth terminology, which I believe all of you already know. What is that? That is mole fraction. That is mole fraction. Okay. For example, I'm talking about the mole fraction. For example, I'm talking about the mole fraction of solute, which I'm representing with Chi2. Mole fraction of solute. How do you define the mole fraction of solute? Simple. Mole fraction of solute is nothing. It is number of moles of solute in the solution divided by the total moles present in the solution. Divided by the total moles present in the solution. Okay. So number of moles of solute divided by the total moles present in the solution. That gives me the mole fraction of solute. Similarly, my dear students, if I ask you to calculate mole fraction of solvent, how do you write mole fraction of solvent? It's simply number of moles of solvent divided by the total moles present in the solution. Number of moles of solvent divided by the total moles present in the solution. And my dear students, at the same time, remember, in case of binary solution, in case of your binary solution, mole fraction of solvent plus mole fraction of solute, it's always equal to what? It's always equal to 1. It's always equal to 1. This is one more important thing. Similarly, my dear students, sometimes in the questions, they'll use certain fancy terminologies like mole percentage. Like mole percentage. What is mole percentage? It is nothing. Mole percentage is nothing. It is just mole fraction multiplied by 100. Mole percentage is nothing but it is mole fraction multiplied by 100. Okay. And my dear students, for example, if I write, let's say, if I write mole percentage of solute, mole percentage of solute is nothing. It is mole fraction of solute multiplied by 100. Similarly, if I sometimes write mole percentage of solvent, it is nothing but mole fraction of solvent multiplied by what? Multiplied by 100. So sometimes in the questions, they might ask you to calculate mole percentage. Okay? Don't be confused at that time. That means you have to calculate mole fraction and multiply mole fraction with 100. That's it. Okay? That's it. Perfect. Mehran Rashid, by watching your lectures, I qualified IIT JAM in chemistry. Amazing, Mehran. Glad to know that. Congratulations. Congratulations. I hope this is clear to everyone. And my dear students, if this is clear to everyone, let's do the first question of the session. This is our question number 1. Calculate the mole fraction of solute. Calculate the mole fraction of solute present in 10% weight by weight of NaOH aqueous solution. Of NaOH aqueous. What does it mean? First of all, I have written the statement here. The statement is 10% weight by weight of NaOH aqueous. First thing, can you decode this statement? Can you decode this statement? You should be able to decode it. It means that 10 grams of NaOH are present in 100 grams of solution. 10 grams of NaOH are present in 100 grams of solution. My dear students, look at this term aqueous. What does it mean? Aqueous means the solvent used. Aqueous means the solvent used is water. So if water is the solvent, that means NaOH automatically becomes my solute. If water is my solvent, NaOH automatically becomes my what? It becomes my solute. Now, my dear students, I got to know 10 grams of NaOH are present in 100 grams of solution. So can I say the mass of the solute, mass of NaOH here is equal to 10 grams? Absolutely. Mass of solution is how much? 100 grams. Now, my dear students, think over it. Mass of solution is 100. Mass of solute is 10 grams. So what would be the mass of solvent? Mass of solvent would be mass of solution minus mass of solute, which would be 90 grams. So first of all, by looking at this particular statement, I got the mass of solute, I got the mass of solution. Now, what do I have to calculate basically? I have to calculate mole fraction of solute. Mole fraction of solute as per formula is nothing but number of moles of solute divided by total moles present in the solution. Mole fraction of solute is nothing but number of moles of solute divided by total moles present in the solution. So can I say, my dear students, can I say in order to calculate Chi2, I should know the value of N1 and N2. I should know the value of N1 and N2. So first of all, let's calculate the value of N2, number of moles of solute. Number of moles of solute would be nothing, mass of solute divided by molar mass of solute. What is the mass of solute? Mass of solute is 10 grams divided by, what would be the molar mass of solute? Molar mass of NaOH, 23 plus 16 plus 1. That comes out to be 40 grams. The value would be 1 by 4. Okay. Similarly, if I want to calculate number of moles of solvent, number of moles of solvent would be mass of solvent divided by molar mass of solvent. What is mass of solvent? Mass of solvent is 90 grams divided by molar mass of solvent. Solvent here is water. And what is the molar mass of water? That is 18. The value comes out to be 5. I got the value of N1. I got the value of N2. I got the value of N1 as well as N2, my dear students. So, in order to calculate Chi2, N2 value, N2 is how much? Where is N2? Okay, 1 by 4 divided by 5 plus 1 by 4. The value comes out to be 1 upon 21. So, this is the mole fraction of solute which I was supposed to calculate. Is this particular question clear to everyone? Quickly in the chats. Everybody, people. Is this particular question clear to everyone? Let me know quickly in the chats. Okay, if in the same question, they ask you to calculate mole fraction of solvent, you will directly say, since Chi1 plus Chi2 is equal to 1, therefore Chi1 would be equal to 1 minus Chi2, which is 1 minus 1 upon 21. The value comes out to be 20 divided by 21. This is going to be the mole fraction of solvent if they ask you in the question. I hope this is super clear to everyone. And if this is clear, let's have a look on one more question. Let's have a look on one more question. Look at the question carefully, my dear students. Look at the question carefully. Look at the question carefully. Look at the question carefully. All right. What mass of water should be added to 16 grams of methanol to make its mole fraction as 0.25? My dear students, understand what the question says. See, imagine you have got a container. And in this container, my dear students, you have got 16 grams of methanol. You have got 16 grams of methanol in this container. Now the question says, what mass of water should be added? What mass of water should be added in this container to make the mole fraction of methanol as 0.25? Okay, so technically as per the question, we have to make mole fraction of methanol as 0.25. We have to make the mole fraction of methanol as 0.25. Now the question is saying, what mass of water should be added? Let's assume, in order to make the mole fraction of methanol as 0.25, let's say X grams of water is to be added. Let's assume that X grams of water is to be added. X grams of water is to be added in order to make the mole fraction of methanol as 0.25. Now, my dear students, try to understand. Mole fraction of methanol means, as per formula, number of moles of methanol divided by total moles present in the container, which will be number of moles of methanol plus number of moles of water. And as per the question, it's nothing but 0.25. So technically, we have to calculate moles of methanol and moles of water. So if I ask you, in the container, how many moles of methanol are there? Number of moles of methanol is equal to mass of methanol divided by, what is the molar mass of methanol? It would be 32. The value comes out to be 0.5. Right? Similarly, my dear students, if I ask you, how many moles of water are there in the container? You'll write mass of water divided by molar mass of water. Okay, perfect. Now put these values in this expression. Number of moles of methanol is 0.5 divided by number of moles of methanol is 0.5 plus number of moles of water is X by 18. And this value as per question is nothing but 0.25. You just need to do the cross multiplication here and you will be getting the value of X. And as far as I know, the value of X would come out to be 27 grams. So what does this 27 grams mean? It means that 27 grams of water are to be added. 27 grams of water are to be added to make the mole fraction of methanol as 0.25. If I am clear, let me know once in the chats quickly. If I'm clear, let me know quickly in the chats. Everyone. Everyone, my dear students. Everyone. Perfect. Perfect. Someone is saying, sir, can you go a little slow? I think I'm going very slow. Yeah, I think I'm going very slow. Okay, for you slightly, I'll reduce my speed for you. Don't worry. All right. All right. Guys, this particular session, for today's video, it's going to be enough for your class 12 physical chemistry. Don't worry. It's going to be super sufficient. Okay. All right. Let's move on. Let's move on. Now, my dear students, the most important term in the concentration terms. The most important term in the concentration terms. What is that? That is your favorite. What is that? Molarity. Representing it with capital M. First of all, how do we exactly define the term molarity? How do we define the term molarity? You should first of all know its definition. My dear students, molarity is defined as the number of moles of solute. The number of moles of solute present in 1 liter of solution. The number of moles of solute present in 1 liter of solution. For example, let's say you have got 1 liter of solution. For example, in 1 liter of solution, let's say in 1 liter of solution, there are 2 moles of solute present. What does that mean? That means molarity of the solution is 2. Okay? If in 1 liter of solution, there are 10 moles of solute present, that means molarity of the solution is 10. If in 1 liter of solution, there are 20 moles of solute present, that means molarity of the solution is 20. So in short, I must say, molarity of the solution is nothing but number of moles of solute which are present in 1 liter of solution. Which are present in 1 liter of solution. Now, my dear students, leaving everything aside, you have to remember certain results to calculate molarity. The first result, you have to remember all, okay? First result. Molarity is nothing but number of moles of solute divided by the volume of solution in liters, okay? The first result. Now, number of moles of solute. Instead of number of moles of solute, I can write mass of solute in grams divided by molar mass of solute. Here I'm taking volume of solution in liters. If I take volume of solution in ml, here I will have to multiply with 1000. This becomes my second result to calculate molarity of the solution. The third result, my dear students, which I would want you guys to remember directly because I'm not deriving anything. Derivation is least important here. Remember, molarity is also calculated as 10 multiplied by weight percentage of solute multiplied by density of solution in grams per ml divided by what? Divided by what? Can you let me know in the chats? Divided by what? Everyone. Can you let me know in the chats quickly? Guys, you should know this formula. Exactly. Divided by molar mass of solute. Divided by the molar mass of solute. Right? 10 multiplied by weight percentage of solute multiplied by density of solution divided by what? Divided by molar mass of solute. Okay? Divided by molar mass of solute. One more thing, my dear students. One more formula which I can write here. One more formula which I can write here. See, 10 I'm writing as such multiplied by weight percentage of solute multiplied by density of solution. Weight percentage of solute multiplied by density of solution. What do we call that as? That is what we call as weight by volume percentage of solute. If you remember, few minutes back I told you, divided by what? Divided by the molar mass of solute. This is one more result to calculate molarity of the solution. Okay? This is one more result to calculate molarity of the solution. I hope I'm clear with this. So, how many results you guys have to remember? This is the first one. This is the second one here. This is the third one. And this is the fourth one. So, remember these results. Now, people, one more important thing. One more important thing. If I talk about molarity in particular, if I talk about molarity in particular, what are the units of molarity? Here you have got moles, here you have got liters. So unit of molarity is nothing but moles per liter, or you can directly call it as molar. You can directly call it as molar. For example, sometimes if I write a statement like this, I'm writing 10 molar NaCl aqueous solution. 10 molar NaCl aqueous solution. What does it mean? What does it mean? It simply means that 10 moles of solute, 10 moles of solute are present in 1 liter of solution. 10 moles of solute are present in 1 liter of solution. Okay. Similarly, my dear students, one more important thing. If you ask me, is molarity temperature dependent or independent? Remember, molarity is temperature dependent concentration term. It is temperature dependent concentration term. This is one more thing which you need to remember. Okay. One more thing which you need to remember. I hope the term molarity is clear to you. And if the term molarity is clear, let's have a look on the question. Let's have a look on the question. Let's have a look on the question. Calculate the weight by weight. You have to calculate weight by weight percentage of solute. And you should be in a position to kill this question now. See, my dear students, I am given with a CH3COH aqueous solution whose molarity is 1.5. So as per the question, M value is nothing but 1.5. Okay. Density of the solution is also given to me, which is 0.8 grams per ml. What do I need to calculate as per the question? I need to calculate weight by weight percentage of solute. Tell me one thing. Is there any result which relates these terms? I gave you one result a few minutes back. Molarity of the solution is equal to 10 multiplied by density of solution in grams per ml multiplied by weight percentage of solute divided by what? Divided by the molar mass of solute. This is one result which I gave you a few minutes back. Okay. Now, my dear students, molarity of the solution is nothing but 1.5 is equal to 10 multiplied by density of solution is nothing but 0.8. Weight by weight percentage of solute is to be calculated divided by molar mass of solute. Solute here is CH3COH. So what would be the molar mass of CH3COH? Carbon 12, 12 plus 12, 24, 24 plus 4, 28, 28 plus 32. That comes out to be 60. Right? Perfect. Now solve this expression and get the weight by weight percentage of solute. And by solving it, weight by weight percentage of solute would come out to be 11.25. 11.25, sorry. 11.25. Okay. I believe this is clear to everyone. Absolutely. All the students are writing 11.25. Yes, correct. I hope this sort of a question is clear. Have a look on the next type of the question. Have a look on the next type of the question. Have a look on the next type of the question. My dear students, question says, dissolving 120 grams of urea. Dissolving 120 grams of urea. In what? In 1000 grams of water. In 1000 grams of water. Gives a solution. Gives a solution whose density is 1.15 grams per ml. What do I need to calculate? I need to calculate molarity of the solution. I need to calculate molarity of the solution. Okay. So first of all, how do you calculate molarity of the solution? One of the results I gave you a few minutes back. Molarity of the solution is mass of solute in grams multiplied by 1000 divided by molar mass of solute, and this is volume of solution in ml. Okay. This is the result to calculate molarity. Now, my dear students, we are done. We are done. How exactly we are done? Understand. Understand properly what I'll be saying. See, urea, you have got 120 grams. Water, we have got 1000 grams. So which one is present in lesser amount? Urea is present in lesser amount. If urea is present in lesser amount, so I would say urea would be your solute. Okay. Urea is going to be our solute. Water is going to be our solvent. So my dear students, as per the question is concerned, mass of solute we know that is 120 grams. Similarly, mass of solvent we know that is 1000 grams. So this term I know. Okay, this term I know. Now, first of all, molar mass of solute. Molar mass of solute. Molar mass of urea. Urea is basically NH2CONH2. This is your urea. When you calculate molar mass of urea will come out to be 60 grams per mole. This would be the molar mass of urea when you calculate it. Okay. Now, my dear students, understand. So, mass of solute we have. Molar mass of solute we have. What do we need? We need volume of solution. In the question, do you see volume of solution anywhere? No. Volume of solution is not given. So, what do I do? Volume of solution is not given. So, what do I do? Understand. Mass of solute I know. Mass of solvent I know. So, can I calculate mass of solution? Mass of solution would be mass of solute plus mass of solvent, which would be directly equal to 1000 plus 120. It would be 1120 grams. This is the mass of solution. Now, my dear students, mass of solution I know. Density of solution I know. Can't I get the volume of solution? Simple. I can say density of solution is nothing but mass of solution in grams divided by the volume of solution in ml. Divided by the volume of solution in ml. Correct? Now, I can say volume of solution would be equal to mass of solution in grams divided by the density of solution in grams per ml. So, tell me the values. Mass of solution is 1120 grams divided by density of solution is 1.15 grams per ml. When you solve this term, you get the value 973 ml. So what is this 973 ml? It is nothing but the volume of solution. So I think, my dear students, all these terms we got. And if we got all these terms, you can calculate molarity. W2, that's 120 multiplied by 1000 divided by molar mass of solute, that is 60, volume of solution, 973 ml. When you solve it, the value comes out to be 2.05. So molarity of the solution is nothing but 2.05 over here. I believe it's clear to everyone. Param, this is not the lengthy question. It's the easy question only, okay? Don't worry. Calculation-wise, it's going to be easy in the question. Calculation part is going to be easy in the question, but concept might be the same. Perfect. So you have to learn all the things perfectly. So I hope molarity is clear. Let's have a look on one more concentration term, that is molality. Okay. What is molality exactly? Molality, what is it? See guys, if I talk about the term molality, which we represent with small m, molality, which I represent with small m. So molality is nothing but, it is defined as the number of moles of solute, present in 1 kg of solvent. The number of moles of solute present in 1 kg of solvent. What does that mean? Let's say in 1 kg of solvent, there are 2 moles of solute. What does that mean? Let's say in 1 kg of solvent, there are 2 moles of solute. That means molality of the solution is 2. Let's say in 1 kg of solvent, there are 10 moles of solute. That means molality of the solution is 10. Let's say in 1 kg of solvent, there are 20 moles of solute. That means molality of the solution is 20. As simple as that. So basically, molality is nothing but number of moles of solute present in 1 kg of solvent. Now, my dear students, here I would want you guys to remember its results. Molality, the first result. It's going to be number of moles of solute divided by the mass of solvent in kg. Okay. So here you can make one more thing. Number of moles of solute means mass of solute in grams divided by molar mass of solute. Here I have used the mass of solvent in kg. So if I use the mass of solvent in grams, here I'll be multiplying with 1000. This is one more result to calculate molality of the solution. The third result, molality is nothing but, it is 1000 multiplied by molarity of the solution divided by 1000 multiplied by the density of solution minus molarity multiplied by the molar mass of solute. Okay. So this is one more result with the help of which you can calculate molality of the solution. Similarly, my dear students, let me give you one more result. Molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molar mass of solvent. These are some results which can be directly used in the questions. These are some results which are directly used in the questions, my dear students. Okay? Perfect. I believe it's super clear to everyone. So you have to remember all these results here. Now people, understand one more thing. If I ask you what are going to be the units of molality, see, here you have got moles, here you have got kg. So its units will be moles per kg, or you can directly call it as molal. You can call it as molal. So, for example, if I write a statement, 5 molal NaCl aqueous solution. What is meant by 5 molal NaCl aqueous solution? It means you have got NaCl aqueous solution whose molality is 5. What does that mean? That means 5 moles of NaCl are present in 1 kg of solvent. Perfect. Now, if you ask me, is molality temperature dependent or independent? My dear students, molality term, it is temperature independent. And since molality is temperature independent, that is the reason why molality is preferred. That is the reason why molality is preferred over what? Over molarity. That is the reason why molality is preferred over molality. Sorry, that is the reason why molality is preferred over molarity. Okay, remember this particular point as well. This is again important. And if all these points are very clear to you, then give this question a try. Give this particular question a try. Give this question a try. It's a simple question. Guys, we just started. You're asking for the break. What are you talking about? What are you talking about? Break I'll be giving after every 3 hours, not after every 1 hour. After every 3 hours, okay? Do not spam here for the break and all. Okay. Calculate the molality of the solution containing 10% weight by weight of NaOH aqueous solution. So first of all, decode this particular statement. And when you decode the statement, it means that 10 grams of NaOH are present in 100 grams of solution. 10 grams of NaOH are present in 100 grams of solution. Now people, tell me one thing. What is the mass of solute here? Mass of solute is 10 grams. Okay. What is the mass of solution here? Mass of solution is 100 grams. So what would be the mass of solvent? What would be the mass of solvent? Mass of solution minus mass of solute. That would be 90 grams. Okay, that would be 90 grams. Now tell me one thing. What am I supposed to calculate? I'm supposed to calculate molality. One of the results I gave you a few minutes back. W2 multiplied by 1000. This is M2 and this is W1 in grams. Now tell me one thing. What is W2? W2 is 10 multiplied by what? Multiplied by 1000 divided by molar mass of solute. Solute here is NaOH. And the molar mass of NaOH is nothing but 40. And W1 is given to me here. That is 90. You just need to solve this and get the molality of the solution. That's all. That's all, people. Am I clear with this? Am I clear with this? Everyone in the chats? A simple basic question. And we are done. People are saying the answer is coming out to be 2.7. All right, I believe you here. The molality of the solution, if you are saying is 2.7, it has to be 2.7 only. Perfect. Amazing. Amazing, guys. One more question on your screen. Guys, these are very, very, very important questions which I'm solving here. Have a look on the question clearly. The question says, calculate the molality of KCl. Let me just modify this question a bit. I'm writing KCl aqueous solution here, okay? Write it as, calculate the molality of KCl aqueous solution prepared by dissolving 7.45 grams of KCl in 500 ml of solution. Let's first of all write all the data which is given to us in the question. And in the question, my dear students, it's mentioned that 7.45 grams. of KCl are present in 500 ml of solution. This is something which is given to me in the question. This is something which is given to me in the question, my dear students. Okay. Now have a look. Try to understand. Density of the solution is also given. How much? Density of the solution is 1.2 grams per ml. What do I need to calculate? I need to calculate molality of the solution. And formula, all of you already know. Molality is nothing but mass of solute in grams multiplied by 1000 divided by the molar mass of solute, and this is mass of solvent in grams. This is your formula to calculate molality. This is your formula to calculate molality. Okay. Now, try to understand what all things are given to us. The mass of solute as per question, which is W2. The value of W2 is given to me as 7.45 grams. Okay. Molar mass of solute. What would be the molar mass of KCl? Potassium is 39. Chlorine is 35.5. So, molar mass of solute is 74.5 grams per mole. Okay. Volume of solution is also given. Volume of solution is also given. How much? Volume of solution is given to me as 500 ml. Volume of solution is given to me as 500 ml. Look at all the parameters which are required in this formula. See guys, W2 value is given to us. M2 value, we got it. What do we need now? We need W1. What do we need now? We need W1. How do I get the value of W1? That is the concern now. That is the concern. Understand, my dear students, what I'll be doing. Density of the solution is given to me as 1.2. Density of the solution is nothing but mass of solution divided by the volume of solution. That's equal to 1.2. Okay. So can I say mass of solution would be equal to 1.2 multiplied by volume of solution, and volume of solution is nothing but 500 ml. The value comes out to be 600 grams. So this is your mass of solution. This is your mass of solution. And my dear students, in this expression, I do not need the mass of solution. What do I need? I need the mass of solvent. I need the mass of solvent. This is the mass of solution. This is the mass of solute. This is the mass of solution. This is the mass of solute. So mass of solution minus mass of solute. That gives me the mass of solvent, which comes out to be 592.55 grams. Right? This is my mass of solvent. Now all the parameters I got, and put all these parameters in this expression, you'll be getting the molality of the solution. And how much it comes out to be? People are saying 0.16. All right, I believe you here. So 0.16 is nothing but the molality of the solution. Am I clear to everyone quickly in the chats? Am I clear to everyone quickly in the chats? Everybody. Everybody, people. Everybody in the chats. Quick. Perfectly done. Amazing, guys. Amazing, amazing. Guys, I'm not going to miss out a single question type, okay? So don't worry. Do not think about my speed the way I'm going. I know in 12 hours I have to complete all your physical chemistry. I'll be doing that. Don't worry. I know where I have to increase the speed, where I have to decrease the speed. I know that. You don't teach me that, okay? All right? Perfect. Now comes one more important topic. What is that? That is molarity of dilution. Molarity of dilution. Now, what is this molarity of dilution? What is this molarity of dilution? Let's get to know what molarity of dilution is all about. My dear students, first of all, as I told you a few minutes back, molarity is nothing, number of moles of solute divided by volume of solution in liters. Number of moles of solute divided by volume of solution in liters. Okay? So people, from this expression, can I write number of moles of solute would be equal to M multiplied by V? Absolutely. Number of moles of solute in the solution is equal to molarity of the solution multiplied by volume of solution in liters. Molarity of the solution multiplied by volume of solution in liters, that gives me the number of moles of solute. That gives me the number of moles of solute. Now try to understand what exactly I'm going to do. For example, I've got a container. Let's say in this particular container, we have got HCl aqueous solution. Let's say we have got HCl aqueous solution here in this container, HCl aqueous solution. Let the molarity of this particular solution is M1. Let the volume of this particular solution is V1 liters. We have got a solution whose molarity is M1, whose volume is V1. All right. Now, my dear students, if I ask you one simple thing, you have got a solution whose molarity is M1, whose volume is V1. Can you let me know how many moles of solute are there in the container right now? Number of moles of solute right now in the container will be equal to molarity of the solution, M1, volume of the solution, that is V1. So M1 multiplied by V1, it is giving me the number of moles of solute present in this solution right now. Okay. Now, my dear students, imagine that in this container, I'm adding some extra solvent. Imagine that in this container, I'm adding some extra solvent. Okay. Imagine that I'm adding some extra solvent. Tell me one thing. When I will be adding the extra solvent, some extra solvent I'm adding, so that means volume of the solution would be increasing. Let the final volume of this HCl aqueous solution, is V2 liters. And since volume has increased, volume of the solution has increased, therefore molarity of the solution would have decreased. Initial molarity of the solution was M1. Now let the final molarity of the solution is M2. Okay. What we did, we just introduced some extra solvent, due to which volume of the solution increased, molarity of the solution decreased. Now final volume of the solution is V2. Final molarity of the solution is M2. Now, my dear students, what have we done? We have done the dilution here. Addition of extra solvent in a particular solution. In simple words, I'm saying addition of extra solvent in a particular solution. That's what you call as dilution. So here, what am I doing? I'm doing dilution. I will say these were the number of moles of solute. In the container before dilution. And what are going to be the number of moles of solute in this container after dilution? Since after dilution, molarity is given, volume is given. So I will say M2 multiplied by V2 here will give me the number of moles of solute present in the final container after dilution. Okay. Perfect. Now, my dear students, think logically. What have we done? We have just introduced extra solvent. Have we done anything with the solute? We have done nothing with the solute. Have I added some solute? No. Have I taken some solute out? No. I have just added extra solvent. Nothing else. So can I say number of moles of solute before dilution has to be equal to number of moles of solute after dilution? Absolutely. Because we have done nothing with the solute. We have done changes with the solvent only. We have done nothing with the solute. Okay. We have done nothing with the solute. We have just done changes with the solvent. I have just added extra solvent. I have not done anything with the solute. Okay. So remember, number of moles of solute present in the container before will be equal to the number of moles of solute present in the container afterwards, after dilution. Because I have done nothing with the solute, right? So number of moles of solute before dilution is nothing but M1V1. Number of moles of solute present finally is M2 multiplied by V2. This is one result, and this is something which you call as your dilution formula. And my dear students, I would want you guys to remember this dilution formula. Okay, if I ask you, calculate the volume of extra solvent added. What volume of extra solvent you have added? See, before dilution, volume of the solution was V1. Before dilution, volume of the solution was V1. After adding some extra solvent, now the final volume of the solution is V2. So I will simply say V2 minus V1 will be giving me the volume of extra solvent added. Okay, so remember these things which are very, very, very important. I believe I'm clear with this. And my dear students, if I'm clear with this, let's give one question a try. The question says, how much water should be added such that 200 ml of 2 molar solution becomes 0.2? Again, the question based on the same thing. Again, the question based on the dilution. See, it's pretty much simple. You have got a solution whose initial molarity is 2. Initial volume is 200 ml. What we are doing now? We are adding some extra solvent. We are adding some extra solvent, due to which the final molarity of the solution becomes 0.2. Let the final volume of the solution be V2. Since it is the case of dilution, so I can use the dilution formula. I can say M1V1 has to be equal to M2V2. M1 is 2, V1 is 200, M2 is 0.2. Let's calculate V2 from here, and V2 will come out to be 2000 ml. Right? This is the final volume of the solution after dilution. This is the final volume of the solution after dilution. But in the question, what are we asked? How much extra water has been added? How much extra solvent has been added? How do you calculate volume of extra solvent? How do you calculate volume of extra solvent added? It's always V2 minus V1. V2 is 2000. V1 is 200. The value comes out to be 1800 ml. So I will say simply, 1800 ml of water has to be added. 1800 ml of water has to be added. Then only molarity of the solution will go from 2 to 0.2. Am I clear? Yes or no in the charts? Quick. Am I clear? Yes or no in the charts? Quick. Everyone. Everyone, people. Everyone, people. Quickly in the charts. Yeah? All clear? Amazing. Amazing, guys. Let's move on to one more thing. What is that? That is molarity of mixing. Molarity of mixing. Molarity of mixing. This I will be teaching you in 2 cases. Case 1. Case 1. Understand what I'll be doing. My dear students, this is one of the container. This is one more container. And this is one more container. Understand what I'll be doing. Let's say in the container number 1, you have got, for example, HCl aqueous solution. Here also you have got one HCl aqueous solution. Let the molarity of this solution is M1. Let the volume of this solution is V1. Let the molarity of this solution is M2. Let the volume of this solution is V2. Okay. So we have got 2 non-reacting solutions here. We have got 2 non-reacting solutions here. Have I mixed them yet? I have not mixed them yet. I have not mixed them yet. Now, my dear students, tell me how many moles of solute are here in this container? You will say M1 multiplied by V1. How many moles of solute are here in this container? You will say M2 multiplied by V2. So have I added them yet? Have I mixed them yet? I have not mixed them yet. So can you tell me how many total moles of solute will be there in both the containers before mixing? Number of moles of solute present in both the containers before mixing is equal to M1V1 plus M2V2. Okay. Now imagine you are adding them in this final container. HCl aqueous, you are putting in this final container. So what do you get here? You will be again getting HCl aqueous solution only. Let the volume of the final solution here is VR. Let the molarity of the final solution is MR. Okay. Let the volume of the final solution, when you add these two in this final container, let the volume of this final solution is VR. Let the molarity of this final solution is MR. And technically VR has to be equal to V1 plus V2 here. Right? If the resulting solution is basically ideal. Now, my dear students, tell me one thing. Can I say before the arrow? Before the arrow. This was the case of before dilution. Now, this is the case of after dilution. After dilution, molarity of the solution is MR. After dilution, volume of the solution is VR. So, if I multiply MR with VR, what do I get? I'll be getting number of moles of solute present in this container after dilution. Okay? Simple. Now, tell me one thing. What have we done? We have just added these two solutions in this final container. Okay? We have just added these two solutions in this final container. Imagine there were, for example, 5 moles of solute here. For example, there were 3 moles of solute here. So can you tell me in the final solution how many moles of solute would be present? I'll say whatever solute was present here, plus whatever solute was present here, all that solute will reach into this particular solution. So this solution will be containing some 8 moles of solute. This solution will be containing some 8 moles of solute. So my dear students, can I simply say one thing? Number of moles of solute before mixing has to be equal to number of moles of solute after mixing. Okay? And number of moles of solute before mixing is nothing but M1V1 plus M2V2 is equal. Number of moles of solute after mixing is equal to MR multiplied by VR. So this is one result which I would want every one of you to remember. Okay? This is one result which I would want every one of you to remember. I believe I'm clear with this. I believe I'm clear with this. This was your case number 1. Now, before showing you the question, there is one more case which I would want to discuss with you. Because there you might get confused. You might get confused. See guys, for example, imagine that I'm taking 3 containers. Imagine that these are the 3 containers which I'm taking. And this is the final one. This is the final one. Understand what I'll be doing. Let's say in the first container, you have got HCl aqueous solution. In the second container also, for example, you have got HCl aqueous solution. In the third container, you only have water. In the third container, you only have water. So here you have got a solution. Here you have got a solution. Here you have got only solvent. Okay, here you have got only solvent. Let molarity of this solution is M1, volume of this solution is V1. Molarity of this solution is M2, volume of this solution is V2. Volume of this water here in the container is V3. Okay. Now what do I have to do? I am going to add these 3 in this final solution. I am going to add this, and finally introduce here. And what do I get at the end? I will be getting a resulting solution of HCl. I will be getting a resulting solution of HCl here. Okay. I'll be getting a resulting solution of HCl here. Now, my dear students, before mixing these three, if I ask you how many moles of solute were here in this container, you will say M1 multiplied by V1. How many moles of solute were there in this container? You will say M2 multiplied by V2. Was there any solute here? No, there was no solute here in this container, because in this container you have got only solvent, right? Now, just add these two. Can I say these are the number of moles of solute with us before mixing? So before mixing, these are the moles of solute which we have. Okay. Now after mixing, this is the resulting solution. Let the volume of resulting solution be VR. Let the molarity of the resulting solution is MR. Now tell me one thing. What would be the volume of resulting solution? Volume of resulting solution would be V1 plus V2 plus V3. V1 plus V2 plus V3. If I ask you how many moles of solute are there in this particular container after mixing, that is going to be equal to molarity multiplied by its volume. Okay, molarity multiplied by its volume. Again, my dear students, which concept I'll be using? Since I'm adding these three, imagine that there were 2 moles of solute here. Imagine that there were 3 moles of solute here. This one does not contain any solute. Since you are mixing these three, so can I say all these 5 moles of solute will finally reach in this container? All the 5 moles of solute will finally reach in this container. So can I simply say number of moles of solute before mixing will be again equal to number of moles of solute after mixing? Okay. Now number of moles of solute before mixing is nothing but M1V1 plus M2V2 is equal to number of moles of solute after mixing is nothing but MR multiplied by VR. What is VR? VR is nothing but, that's going to be V1 plus V2 plus V3. And what is V3? V3 is volume of water which I had taken in the container, in the third container. From this expression, my dear students, you will be asked to calculate volume of water. You should be in a position to make this expression. And once you are in a position to make this expression, you can easily calculate the volume of water. Okay. Am I clear, my dear students? Everyone in the chat's quick. Everyone in the chat's quick. Quickly, let me know in the chats. Perfect. Amazing. Amazing, people. Now. One simple question which is in front of you. Can you kill this? Can you kill this one? Everyone. See, guys, you are mixing two solutions. So basically, let me quickly summarize this. You have got two solutions. The first one is HCl aqueous. The second one is also HCl aqueous. Okay. Molarity of this solution is 3. Volume of this solution is 200 ml. Molarity of this solution is 2. Volume of this solution is 300 ml. Now, since you are mixing them, you are getting the final solution of HCl. You are getting a final solution of HCl whose molarity is, for example, Mr. And volume of the final solution, as per question, is made how much? Volume of the final solution is made 1500 ml. So people, you should be able to solve this. It's a simple question. You can say M1V1 plus M2V2 has to be equal to Mr multiplied by Vr. Simple. M1 is given, V1 is given, M2 is given, V2 is given, Vr is also given. So you just have to calculate Mr here, right? That is going to give you the molarity of the final solution. People are saying 0.8. Absolutely, all of you are perfectly right. It is going to be 0.8. It is going to be 0.8 molar. This is the molarity of the final solution. As simple as that. And if it is clear, my dear students, can you give this question a try? Can you give this question a try very quickly? Everybody, look at the question. This question resembles with case 2. This question resembles with case 2. This question resembles with case 2, and you should be in a position to solve all of these. You should be in a position to solve all of these. Amazing. A lot of students have already given the correct answer. That's great. This is something which I wanted. This is something which I wanted, people. Amazing. Amazing. Good. See what the question says. As per the question, my dear students, it's pretty much simple. Calculate the volume of water that must be added to a mixture of 250 ml of 0.6 molar HCl, 750 ml of 0.2 molar HCl to obtain 0.25 molar resulting solution. So let me write all the data first. See, as per the question, V1 value is given to me as 250 ml, right? M1 value is given to me as 0.6 molar. V2 value is equal to 750 ml. M2 value is equal to 0.2, right? This is your one HCl solution. This is one more HCl aqueous solution. And in the third container, imagine that you only have got water. Let's say volume of water used here is VH2O, which I have to calculate. And now you are adding these three. You are making the final solution here. This final solution of HCl, its molarity is given to me as how much? 0.25, right? Volume of this final solution, volume of this resulting solution would be equal to this plus volume of water. So 250 plus 750 makes it 1000. So I'll say it is going to be 1000 plus volume of water. Correct? Now guys, we are almost done. I can say M1V1 plus M2V2 has to be equal to Mr multiplied by Vr. And what is Vr? Vr is 1000 plus volume of water. Okay. What is M1? M1 is 0.6. What is V1? V1 is 250 ml. M2 is 0.2. V2 is 750 ml. Mr is equal to 0.25 multiplied by, this is 1000 plus volume of water. And as per the question, I was supposed to calculate this volume of water, and this volume of water, when you calculate, it will come out to be 200 ml. So basically, in this third container, you had kept some 200 ml of water, which I was supposed to calculate. Clear? Clear, people? Everybody in the chats. Everybody in the chats. Everybody in the chats. Amazing. Amazing, guys. Amazing. Now, there is one more concentration term, which is what you call as parts per million. It's a simple one. Parts per million of solute. How do you exactly define this particular concentration term? Parts per million of solute. Now, people, parts per million of solute is defined as, in simple words I'm writing, the mass of solute in grams, which is present in 10 raised power 6 grams of solution. The mass of solute in grams, which is present in, the mass of solute in grams, which is present in 10 raised power 6 grams of solution. For example, imagine that you have got 10 raised power 6 grams of solution. Imagine in 10 raised power 6 grams of solution, there are some 100 grams of solute. You will say ppm of solute is 100. Imagine that in 10 raised power 6 grams of solution, there are some 50 grams of solute. You will say ppm of solute is 50. Imagine that in 10 raised power 6 grams of solution, there are 500 grams of solute. You will say ppm of solute is 500. So in short, what is ppm of solute? That mass of solute in grams, which is present in 10 raised power 6 grams of solution. Now, people, remember its result. Parts per million of solute is nothing but mass of solute in grams divided by the mass of solution in grams multiplied by what? Multiplied by 10 raised power 6. With this particular expression, you can calculate ppm of solute. You can calculate ppm of solute. Similarly, if you want to calculate ppm of solvent, it is going to be equal mass of solvent in grams divided by the mass of solution in grams multiplied by 10 raised power 6. This is your result to calculate parts per million of solvent. Okay, parts per million of solvent. Now, my dear students, one more thing. Remember, your ppm of solute can be also calculated like this. Weight by weight percentage of solute multiplied by 10 raised power 4. Similarly, your ppm of solvent can also be calculated as weight by weight percentage of solvent multiplied by 10 raised power 4. These are further two expressions which I want you all to remember. Now, similarly, there is one more term which you can easily do now. That's called as parts per billion. Let's say parts per billion of solute. Parts per billion of solute. Which is your PPB of solute. Now, can you define this particular term as well? See, this was 10 raised power 6. Now it's billion. So it has to be 10 raised power 9. Nothing else. It has to be 10 raised power 9. So I can say parts per billion of solute. It is basically the mass of solute. In grams, which is present in 10 raised power 9 grams of solution. 10 raised power 9 grams of solution. So I can make the result simple. PPB of solute is equal to mass of solute in grams divided by the mass of solution in grams multiplied by 10 raised power 9. This is the first expression. PPB of solute. Okay, which you have to remember. Now, similarly, if I write PPB of solvent will be mass of solvent in grams divided by the mass of solution in grams multiplied by 10 raised power 9. Okay, 10 raised power 9. So basic simple changes. Wherever you saw 10 raised power 6, here you have to mention 10 raised power 9. That's it. These are the only changes. These are the only changes here. I believe I'm clear. And people, here you can write two more things. Remember, PPB of solute can be also written like this. weight by weight percentage of solute multiplied by 10 raised power 7. PPB of solvent can be written as weight by weight percentage of solvent multiplied by 10 raised power 7. Okay, remember these two expressions as well. Remember these two expressions as well. So with this, our first and the most important part of the chapter, that is concentration term, is done and dusted. If I am clear, let me know in the chats if I am clear to every single guy. I want everyone to let me know in the chats if all the things still here are clear. I want you guys to let me know in the chats if all the things still here are clear. Everyone, guys, everyone. I'm teaching everything in the detailed form. I'm not missing out a single thing. Everything I'm teaching in the detailed form. Don't worry about the speed and everything. I will be completing everything in 12 hours. Don't worry. So tell me in the chats quickly. Is every single thing is clear till here? Normality I won't be teaching here. Normality would be taught in redox reaction. Okay, that's a vast topic, normality. That will be taught in redox, not here. All right. Amazing. Amazing, guys. Amazing. As I told you, notes I'll be sharing on my Telegram, right? If you do not know my Telegram, let me write the Telegram here. You just search WASSIM BHAT Chemistry Official. This is the name of the Telegram channel where I'll be sharing the handwritten notes. Wassim Bhat Chemistry Official is the Telegram channel name. Okay? Right? Break would be given after every 3 hours. Not now. Not now. All right, guys. All right. Anjali, neutralization is also the topic in redox, not here. Okay? Neutralization is also the topic in redox. When I'll be teaching you normality and all, that will be discussed there, not here. I've perfectly designed everything. Don't worry. Okay? I hope every single thing is clear till here. Now, let's have a look on the term vapor pressure. See, this entire chapter depends upon this term. Entire chapter revolves under vapor pressure. Entire chapter revolves around vapor pressure. So first of all, you should know what this vapor pressure is. So try to understand very carefully what vapor pressure is and how do we relate this with all the other things. Okay? How do we relate this with all the other things? If you look at this particular definition, vapor pressure. Here I've mentioned that vapor pressure is nothing but it is the pressure exerted. It is the pressure exerted by the vapors. The pressure exerted by the vapors of a volatile liquid. The pressure exerted by the vapors. Vapors of what? Vapors of a volatile liquid. When a liquid and its vapors are at equilibrium at a particular temperature. What does it mean? What does it mean? Understand, people, what does it mean? Say, for example, this is a container. Imagine this container is closed. Now, my dear students, in this container, for example, we are keeping a volatile liquid. We are keeping a volatile liquid. Volatile liquid is that liquid which can form its vapors. It can be water. Water can form its vapors, right? Let's say the volatile liquid here is X, right? It is X. Let's say this liquid is at a particular temperature. Let's say the liquid is at 25 degrees centigrade right now. Let's say the liquid is at 25 degrees centigrade right now. Now, my dear students, since it's a volatile liquid, it is a volatile liquid. So if it is a volatile liquid, I would say it has got tendency to form its vapors. Absolutely, it has got tendency to form its vapors. So I would say some of the liquid molecules would be forming vapors here. Some of the liquid molecules would be forming vapors here. So can I say, first of all, X liquid is getting converted into X gas. And this phenomenon is what you call as evaporation. conversion of liquid into vapors is what you call as evaporation. So first of all, when I kept this volatile liquid here, right, some of the liquid molecules got converted into its vapors, and this phenomenon is what you call as evaporation. Now, my dear students, after some time, what you will see, after some time you will see some of the vapors again getting back into the liquid state, some of the vapors again getting converted into liquid. So after some time you will see process of condensation starting. So first of all, initially evaporation started. After some time, condensation started. There will be a scenario when rate of evaporation and rate of condensation would be equal. There would be the scenario when rate of evaporation and rate of condensation would get equal. At that point of time, when rate of evaporation and rate of condensation becomes equal, I will say at that point of time, the liquid and its vapors, they are at equilibrium. I would say at that point of time, the liquid and its vapors, they are at equilibrium. My dear students, imagine right now a scenario has got created. If one liquid particle is getting converted into vapors, at the same time, one vapor particle is getting converted into liquid. So can I say when equilibrium is established between liquid and its vapors, if one liquid particle is getting converted into vapor, at the same time, one vapor particle is getting converted into liquid. So equilibrium is established, and if equilibrium is established, I would say the amount of vapors generated here would be fixed. Because if one particle is getting converted into vapor, at the same time, one vapor particle is getting converted into liquid. So amount of vapors remain constant here. Amount of vapors will be fixed here. So that is the statement which I mentioned here. At equilibrium, amount of vapors generated are fixed. Okay. Now, my dear students, one more important thing. Now, since the liquid and its vapors are at equilibrium, tell me one thing. Will these vapor particles be at rest or they will be in random motion? I'll say these vapor particles would be in random motion. If these vapor particles are in random motion, they'll be colliding with each other. They'll be colliding with the walls of the container. They'll be colliding with the top surface of the liquid as well. Since these vapor particles are in random motion, right? So I can say the pressure exerted by the vapors, the pressure exerted by the vapors of a volatile liquid, when liquid and its vapors are at equilibrium at a particular temperature, that pressure exerted is what you call as vapor pressure. Am I clear to everyone? People? Am I clear to everyone? The pressure exerted by the vapors, right? Okay, when liquid and its vapors are at equilibrium is something which you call as vapor pressure. Quickly, let me know in the chats if I'm clear. Everybody, did you understand what is vapor pressure? Did you understand what is vapor pressure? Everyone in the chats? Everyone in the chats? So simple vapor pressure is the pressure exerted by the vapors of a volatile liquid when liquid and its vapors are at equilibrium. Okay. Now, my dear students, one point. On what factors this vapor pressure depends on? The two important factors on which vapor pressure depends on. First one, force of interaction between liquid molecules. Let's say there's a container, and in this container, for example, these are the liquid molecules. Tell me one thing. More the force of attraction between the liquid molecules. Can I say lesser would be the escaping tendency? If more is the force of attraction, between the liquid molecules, can I say lesser would be the escaping tendency? If lesser is the escaping tendency, can I say amount of vapor generated would be less? And if amount of vapor generated are less, can I say lesser will be the vapor pressure? Simple. So more the force of interaction between the liquid molecules, lesser is going to be the vapor pressure. Perfect. So your force of interaction between the liquid and the vapor pressure It has to be inversely proportional to each other. So remember, vapor pressure is inversely proportional to force of attraction between the liquid molecules. All right. Now, my dear students, the second factor on which vapor pressure depends on, that's temperature. It is pretty much simple. More the temperature, more the vapor pressure. It's pretty much simple, right? More the temperature, more is going to be simply the vapor pressure. So how vapor pressure is related? Vapor pressure is related to temperature like this. Vapor pressure of the liquid is directly proportional to its temperature. Okay, I think this point needs not to be explained. All right. Now, my dear students, this equation, what this equation is basically for. Try to understand what this equation will make us understand. Try to understand what this equation will make us understand. Properly understand what I'll be saying. See, guys, for example, this is a container, and here in this container, I've got a volatile liquid. Okay, it's a volatile liquid. Let this liquid is at temperature T1. When the liquid is at temperature T1, let its vapor pressure at that point of time is P1. Let's vapor pressure at that point of time is P1. Now, for example, I'm increasing the temperature of the liquid from T1 to T2. If I'm changing the temperature of the liquid, let the vapor pressure of the liquid now is P2. When the liquid is at temperature T1, its vapor pressure is P1. When the liquid is at temperature T2, its vapor pressure is P2. Okay. Now there is one equation which relates all these four terms, and that is your Clausius-Clapeyron equation. That's your Clausius-Clapeyron equation. Log of P2 by P1 is equal to delta H vaporization divided by 2.303 R, 1 by T1 minus 1 by T2. I'm not deriving this. Just remember this particular equation directly. Just remember this particular equation directly. Okay. See, guys, from this equation, what we can understand. From this particular equation, what we can understand properly what I'll be saying. My dear students, initially the temperature of liquid was T1. Now the liquid is at temperature T2. Imagine I have increased the temperature of liquid. Imagine that I have increased the temperature of liquid. If I have increased the temperature of liquid, so this T2 minus T1, final temperature minus initial temperature, this term would be coming out to be positive. I'll say T2 minus T1. On increasing the temperature, T2 minus T1 will come out to be positive. Delta H vaporization is already positive. Delta H vaporization. Vaporization is endothermic process. It is already positive. So this term is positive. This term is positive. Can I say the overall term is positive? If the overall term is positive, that means the log of P2 divided by P1 is coming out to be positive. Log of P2 divided by P1 is coming out to be positive. Now, how can log of X be positive? Log of X will be positive only if X is greater than 1. If P2 divided by P1 is greater than 1, which means that P2 is greater than P1, right? Which means that P2 is greater than P1. So what you can understand from here? What you can understand from here? You can simply say, on increasing the temperature, what is happening to the vapor pressure of the liquid? It's increasing. Simple. On increasing the temperature, what is happening to the vapor pressure of the liquid? It's increasing. As simple as that. Okay. And my dear students, one more important point. Please note this. Vapor pressure of the liquid, it does not depend on the amount of the liquid, as well as it does not depend on the shape of the container in which liquid is kept. Okay. Remember your vapor pressure. Since it does not depend on the amount of liquid, so you can say your vapor pressure is nothing but it's an intensive property. Vapor pressure is nothing but intensive property. Vapor pressure of the liquid does not depend on the amount of liquid. It does not depend on the container in which liquid. It does not depend on the shape of the container in which liquid is kept. These are the two important things which I would want you guys to remember directly. Now comes the most important topic of the chapter. What is that? That's your Raoult's law. Is the vapor pressure term clear? Tell me, on how many factors vapor pressure depends on? Quick. On how many factors vapor pressure depends on? In the chats. In the chats, everybody. It depends on two factors. Number one, Number one, force of interaction between the liquid particles. Number two, that's temperature. Okay? Number two, that's temperature. Number two, that's temperature. Perfect, guys. Perfect. All right. Now, my dear students, what is Raoult's law exactly? Let's have a look at its statement, then I'll make you understand. The partial vapor pressure of the component, the partial vapor pressure of a component over the liquid solution is directly proportional to the mole fraction of the component in the liquid phase. What does that mean? What does that mean? Try to understand what I'll be saying. This is one important topic, and please understand it properly. Please understand it properly. See, guys. For example, in this container, I'm keeping a volatile liquid A. I'm keeping a volatile liquid A in this container. So if this liquid is volatile, so definitely you will find vapors of A here. Since the liquid is volatile, so you'll be finding vapors of A here. Okay. My dear students, since this A is right now in its pure state, there is nothing mixed with this A right now. Okay. So let the vapor pressure here be P naught A. So what is P naught A? P naught A is nothing but it is vapor pressure of A in which state? I'll say in pure state. Vapor pressure of A in which state? In pure state. Perfect. Now, my dear students, imagine you have got one more volatile liquid B. This is your volatile liquid B in the container. If this liquid B is also volatile, so I would say there will be vapors of B here. There will be vapors of B. Let the vapor pressure here is P naught B. And what is this P naught B? It is the vapor pressure of B in which state? In pure state. Vapor pressure of B in which state? In pure state. Perfect. For example, I'm mixing these two liquids. When I mix these two liquids, what do I get here? Can I say over here, I'll be getting a solution of A and B. Over here, I'll be getting a solution of A and B, right? My dear students, I got solution of A and B, okay? Since A and B both are volatile, so here you will find vapors of A as well as B. Here you will find vapors of A as well as B. Let the vapor pressure of the solution here is PS. PS represents vapor pressure of the solution. Now, is the vapor pressure of solution only due to A, only due to B, or both have contributed? I'll say both have contributed. Okay, so vapor pressure of solution would be nothing but it would be PA plus PB. What is PA? PA is nothing but it is contribution. It is contribution made by A. It is contribution made by A towards total vapor pressure of the solution. And this PB is contribution made by B towards the total vapor pressure of the solution. Okay, perfect. And contribution made by A towards the total vapor pressure is what I call as partial vapor pressure. This is the partial vapor pressure of A, and this is what you call as the partial vapor pressure of B. This is what I call as the partial vapor pressure of B. Now, what Raoult's law says? What Raoult's law exactly says? Raoult's law says that the partial vapor pressure of A, for example, the partial vapor pressure of A, that means contribution made by A towards the total vapor pressure, that is directly proportional to the mole fraction of A in the solution phase. The partial vapor pressure of A is directly proportional to mole fraction of A in the solution phase. Similarly, partial vapor pressure of B is directly proportional to mole fraction of B in the solution phase. And my dear students, if you remove the proportionality, it becomes P naught A and this becomes chi A. Similarly, if you remove the proportionality, it becomes P naught B multiplied by what? Multiplied by chi B. Okay. So what is this chi A and chi B here? What is this chi A and chi B here? What is this chi A and chi B here? Let me tell you, chi A is mole fraction of A in solution phase. In solution phase. Similarly, chi B is mole fraction of B in the solution phase. These are the two results which are equally important, and I would want every one of you to remember these results. And once you remember these results, then you should be in a position to make some graphs as well. For example, I have to make a graph between PA versus chi A. Let's say I have to make a graph between PB versus chi B. Versus chi B. Let's say I have to make a graph between PA versus chi B. Okay, let's say I have to make a graph between PB versus chi A. Can I make all these graphs? Absolutely. We are in the position to make all these graphs. Understand, guys. First thing, PA I'm plotting along y-axis, chi A I'm plotting along x-axis, right? We know PA is nothing but, it is P naught A, chi A, correct? PA I'm plotting along y-axis, chi A I'm plotting along x-axis. This becomes my M, y is equal to mx. So straight line. If y is equal to mx, straight line, its slope is nothing but m, and m is nothing but, that is P naught A. Correct? One simple straight line. Similarly, PB versus chi B. You know your PB is nothing but, that is P naught B, chi B. P naught B, I mean PB I'm plotting along y-axis. This I'm plotting along x-axis. So this is y, this is your x, and this becomes my m. Y is equal to mx. Again a straight line whose slope would be what? Whose slope would be P naught B. Correct? Now, PA versus chi B. Since PA is equal to P naught A chi A. Correct? This you have to plot along y-axis. This you have to plot along x-axis. Now, my dear students, remember, PA I'm writing as such. This is P naught A. Instead of chi A, I'm writing 1 minus chi B. Instead of chi A, I'm writing 1 minus chi B. So I can say your PA is nothing but, it is P naught A minus P naught A chi B. Minus P naught A chi B. PA you are plotting along y-axis. PA you are plotting along y-axis. Chi B you are plotting along x-axis. This becomes my M. Sign is minus, and this is C. Y is equal to minus mx plus C. Minus mx plus C means straight line with a negative slope. Minus mx plus C, straight line with a negative slope, and its slope here is going to be minus P naught A, right? Perfect. I believe this particular one you can easily do. This particular one you can easily do. Yeah? Right, people? Yeah? Am I clear? Am I clear? Wassim, that is least important. Why you are worried about least important things? Am I clear, people? All right. All right. Amazing. Amazing. Even this particular one is also going to be a straight line like this, right? And its slope is going to be minus P naught B. Correct? Minus P naught B. Okay? Perfect. Perfect, guys. Now, guys, one more important thing. One more important thing. What is that? That is simply the Raoult's law. Raoult's law for a solution containing Raoult's law for a solution containing two volatile liquids. Two volatile liquids. Raoult's law for a solution containing what? Containing two volatile liquids. Now, remember, understand what I'll be doing. See, guys. See, guys. Again, the same scenario. I'm taking three containers. I'm taking three containers. In this particular container, what do we have? We have got the volatile liquid A. In this particular container, what do we have? We have got volatile liquid B. Okay. Over here, you'll only find vapors of A. Over here, you'll only find vapors of B. Here, the vapor pressure is P naught A. Here, the vapor pressure is P naught B. Now you are mixing them up. When you mix them up, what do we get? We get a solution of A and B. We get a solution of A and B, right? So here you will find vapors of A as well as B. So I can say the total vapor pressure of the solution is nothing but that is your PA plus PB. Total vapor pressure of the solution is nothing but partial vapor pressure of A plus partial vapor pressure of B. Okay. So my dear students, you can say PS is equal to, instead of PA, you can write P naught A chi A. Instead of PB, you can write P naught B chi B. This is the first result which you are going to remember from now onwards. The first result. The first result. Okay. Now the second result. PS is equal to P naught A chi A plus P naught B. Instead of chi B, I can write 1 minus chi A. So the result becomes PS is equal to P naught A chi A plus, this would become P naught B minus P naught B chi A. So your PS is equal to, write this P naught B in the beginning. Okay. Now P naught A chi A, P naught B chi A. So chi A I can take common here. Chi A I can take common here. And when I take chi A common, it is going to be P naught A minus P naught B multiplied by chi A. This is one more expression which I would want you guys to remember directly. Now, is it necessary? Is it necessary to replace chi B with 1 minus chi A? You can replace this chi A as well. You can replace this chi A as well with 1 minus chi B and make one more expression on your own. So these are the 2-3 expressions which I would want every one of you to remember. Okay? Perfect. Perfect, people. Let me know quickly in the chats, or let me make this expression for you so that it becomes clear. So PS is equal to P naught A multiplied by chi A. Instead of chi A, I'm writing 1 minus chi B plus P naught B multiplied by chi B. So your PS is equal to, this is P naught A minus P naught A chi B plus P naught B chi B plus P naught B chi B. So PS is equal to P naught A as such. P naught A as such. Here you can take chi B common. It is going to become P naught B minus P naught A. And what you have taken common? The common is your chi B. Perfect. These are the 3 expressions which you will have to remember from now onwards. All right, my dear friends. Am I clear? And if I am clear, there is one more thing which I would want to share with you. What is that? Let's have a look. There is one more thing which I would want to share with you. That is calculation of mole fraction. Calculation of mole fraction of A and B. Of A and B in vapor phase. Calculation of mole fraction of A and B in vapor phase. This is also asked. This is also asked. Okay. What it means exactly. Again, I'm doing the same thing. Again, I'm going to do the same thing. See guys, let's say this is the container. In this particular container, what do we have? We have got a solution of A and B. We have got a solution of A and B. And I've already told you A and B both are volatile. So here you will find vapors of A as well as B. Here you will find vapors of A as well as B. Total vapor pressure of the solution, we already know that is PA plus PB. That is PA plus PB. Now, my dear students, here I'm writing 4 terms. One is chi A, one is chi B, one is chi dash A, one is chi dash B. You should first of all know the meaning of all these 4 terms. What is chi A? Chi A is what I call as mole fraction of A in solution phase, in liquid phase. Chi B is mole fraction of B, again in solution phase. What is chi dash A? That is mole fraction of A in vapor phase. What is chi dash B? That is mole fraction of B in vapor phase. Sometimes you will be asked a question in which you will be supposed to calculate chi dash A and chi dash B. You'll be asked a question in which you'll be supposed to calculate chi dash A and chi dash B. I'm directly giving you the result. Chi dash A is nothing but P naught A multiplied by chi A divided by PS. This is the result which you'll be using to calculate chi dash A. Similarly, if they ask you to calculate chi dash B, it is going to be P naught B multiplied by chi B divided by PS. Okay, this is one more expression. These can be directly asked. I have not derived these expressions. I'm just giving you these expressions directly so that you'll utilize them in the questions. I hope I'm clear. I hope I'm clear to everyone. DPP, I'll be sharing in the Telegram. Yes. Don't worry. I hope I'm clear with this. Okay, and if I am clear with this, first and the basic question, which is here in front of you. First and the basic question, which is here in the front of you. Quickly. The question is, the vapor pressure of two pure liquids A and B are 100 torr and 80 torr respectively. Calculate the total pressure of the solution obtained by mixing 2 moles of A and 3 moles of B. So basically, my dear students, the question says, in the question, what all parameters are given? In the question, vapor pressure of A in pure state, P naught A, is given to me as 100 torr. Similarly, P naught B is given to me as 80 torr. Okay. Number of moles of A in the solution, in the liquid, is equal to 2. Number of moles of B in the liquid is equal to 3. What do I have to calculate? I have to calculate the total vapor pressure of the solution. So PS, which is nothing but P naught A chi A plus P naught B multiplied by chi B. Okay, so PS is equal, P naught A is 100, chi A, mole fraction of A, would be nothing, number of moles of A divided by total moles present in the solution, 3 plus 2 is 5, plus P naught B is 80, mole fraction of B, that means moles of B divided by total moles. Correct? When you solve this, absolutely all of you got the correct answer. The final answer is going to be 88 torr. So 88 torr is going to be the final vapor pressure of the solution. 88 torr is going to be the final vapor pressure of the solution. I hope this is clear. I hope this is clear. Perfect. Amazing, amazing, amazing. Can you give this question a try quick? Can you give this question a try quick? Can you give this question a try quick? Everybody. Everybody in the chats. The question is the vapor pressure of pure liquid A. So P naught A is given. That is 70 torr. Okay. It forms an ideal solution with another liquid B. The mole fraction of B in the solution. The mole fraction of B in the solution is 0.2. And total vapor pressure of the solution is 84 torr. What do I need to calculate? I need to calculate the value of P naught B. I need to get the value of P naught B. A simple basic question. A simple and basic question, my dear students. So first of all, what do you need to do? Again, use the same expression. PS is equal to P naught A chi A plus P naught B multiplied by chi B. So I'll say your PS as per the question is equal to 84. P naught A is equal to 70. If chi B is 0.2, that means chi A would be 0.8 plus P naught B I need to calculate. Chi B is 0.2. One equation, one unknown. So what is the value of P naught B, which you are getting from here? People are saying it's 140. Is it 140? I believe you. Okay, 140 torr is basically the vapor pressure of B in the pure state, which I was supposed to calculate. I hope this sort of a question you can easily solve from now onwards. Okay, look at this particular question. 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 A solution has 1:4 molar ratio of pentane to hexane. You've got a solution containing pentane and hexane. Okay? You've got a solution containing pentane and hexane. Let me represent pentane with A. Let me represent hexane with B. Okay. So first of all, as per the question, you have got a solution. You have got a solution. This is the solution containing pentane and hexane, containing A and B. The molar ratio of A is to B is 1:4. If the molar ratio of A is to B is 1:4, if I ask you, what would be the mole fraction of A here? Mole fraction of A in the solution would be 1/5. Mole fraction of B in the solution would be 4/5. It would be 4/5, correct? Mole fraction of A in the solution is going to be 1/5. Mole fraction of B in the solution is going to be 4/5. Now, my dear students, what am I supposed to calculate? What am I supposed to calculate? What am I supposed to calculate? Calculate the mole fraction of pentane in the vapor phase. So we have to calculate chi A dash. How do you calculate chi A dash? I have given you the formula a few minutes back. Chi A dash is nothing but P naught A chi A divided by PS. P naught A chi A divided by PS. Now, as per the question, let's see what all parameters we have already. See, guys, P naught A is given to me as 440 mm of Hg. Okay. As per the question, P naught B is also given to me as 120 mm of Hg. Correct? Okay. These are the two things which I'm given with. These are the two things which I'm given with. And chi A and chi B I already know. So I can easily calculate PS first of all. PS is going to be P naught A chi A plus P naught B multiplied by chi B. So tell me, my dear students, what is P naught A? P naught A is 440. What is chi A? Chi A is 1/5. P naught B is 120. What is chi B? Chi B is 4/5. Can you tell me what is the value coming out to be after solving this? Aditi is saying 184. Is that? So it is 184 torr. So this is your PS. Now, put all the values here. P naught A is 440. Chi A is 1/5 divided by, what is PS? PS is 184. Solve this. It will give you the mole fraction of A in the vapor phase. Am I clear to everyone, people? Am I clear to everyone quickly? In the chats. Everybody in the chats, quick, quick, quick. Let me know in the chats, quick. I want everyone to say it quickly, guys. Don't wait. Don't wait. Don't wait. When will class end? Class will end in the morning. We have just started. What are you saying? Class will end in the morning. All right, all right, all right. All right, people. Amazing. Now, there is one graph. There is one graph which I want to give you because that is important. So remember this graph as well. Remember the graph as well. The graph is something like this. See, guys, what I'll be doing. See properly what I'll be doing. Along y-axis, I'm plotting pressure. Okay. Along x-axis, I'm plotting mole fraction. Mole fraction in liquid phase, in solution phase. In solution phase. Already I know two things. What is that? I know PA is nothing but that is P naught A chi A. I know PB is nothing but that is P naught B chi B. Okay, these are the two things which I already know. Now, my dear students, let's say at this particular point, at this point, for example, chi A value is 0. If chi A is 0, Therefore, chi B has to be 1. Because chi A plus chi B has eventually be 1. It has to be 1. Now, my dear students, on moving from left to right, let chi A increase, and at this point, let the maximum value of chi A is 1. If chi A is 1 here, therefore chi B has to be 0. Therefore, chi B has to be 0. Now, people, try to understand what I say. At this point, chi A is 0. That means in the solution, there is no A. There is only B. In the container, there is only B. There is only B in the container. If there is only B in the container, that means all the vapors will be due to B. If there is no A, there is only B in the container. So whatever vapor pressure will be there, that will be due to pure B, which is going to be P naught B. Which is going to be P naught B. Correct? Agreed? If you move from left to right, what is happening to chi B? Chi B is decreasing. What is happening to chi B? Chi B is decreasing. Chi B is decreasing. That means mole fraction of B in the solution is decreasing. If mole fraction of B in the solution is decreasing, that means vapors of B would be decreasing as well. And if vapors of B are decreasing, that means contribution made by B towards the total vapor pressure, that will be also decreasing. So I will say simply PB value would be decreasing, and finally PB reduces to 0, right? Because at this point there is no B in the container. If there is no B in the container, there is only A. If there is only A, so whatever is going to be vapor pressure, that is going to be due to pure A, and due to pure A, vapor pressure is nothing but that is P naught A. Correct? Now, my dear students, understand very carefully what I'll be saying. Understand what I'll be saying. See, at this particular point, chi A is 0. When you move from left to right, chi A value is increasing. If chi A is increasing, that means mole fraction of A in the solution is increasing. Mole fraction of A in the solution is increasing. If mole fraction of A in the solution is increasing, that means vapors of A would be also increasing. If vapors of A are increasing, that means vapor pressure due to A, that will be also increasing. So on moving from left to right, this graph will go here and finally reach here. Okay. So can you tell me the equations first of all? This particular line is telling you that PB is equal to P naught B chi B. And this particular line is telling us that PA is equal to P naught A chi A. And my dear students, if you join these two lines, this gives me the total vapor pressure of the solution, which is nothing but PA plus PB, which is P naught A chi A plus P naught B chi B. Let me know once in the chats if this is clear. Let me know once in the chats if this graph is also clear. Everyone, quickly. Everyone, quickly. Everyone, quickly. Perfect. Guys, dinner break will be at 10, not now. At 10, I'll be giving the dinner break. Perfect, people. Now. Moving on to something called as ideal non-ideal solutions. Ideal non-ideal solutions. My dear students, ideal non-ideal solutions, I'm not going into very much detail. I'm giving you one sheet. Okay. On one slide, I'll be making it very much clear. Okay. On one slide, I'm giving you points which will be asked. Okay. Apart from those points, nothing will be asked. See, what do we need to do? First of all, let me tell you, in order to calculate vapor pressure of the solution, there are two ways. There are two ways to calculate vapor pressure of the solution. One is with the help of Raoult's law. One is experimentally. One is experimentally. In order to calculate vapor pressure of the solution, we have got two ways. Either I'll be calculating vapor pressure of the solution as per Raoult's law, which will be P naught A chi A plus P naught B chi B as per Raoult's law, correct? Or I'll be calculating it experimentally, correct? My dear students, whenever I calculate vapor pressure of the solution with the help of Raoult's law, I call that as the theoretical vapor pressure. I call that as the theoretical vapor pressure. And whenever I calculate vapor pressure of the solution experimentally, I directly call that as the experimentally determined vapor pressure. I call that as the experimentally determined vapor pressure. My dear students, remember that there are some solutions for which experimentally determined vapor pressure and theoretically determined vapor pressure, as per Raoult's law, they come out to be same. But there are some solutions for which experimentally determined vapor pressure and theoretically determined vapor pressure, they do not come out to be same. These sort of solutions are what you call as ideal solutions, and these sort of solutions are what you call as non-ideal solutions. Non-ideal solutions. These are what I call as non-ideal solutions. Perfect. Now, my dear students, these non-ideal solutions are further of two types. One is non-ideal solution showing positive deviation. One is non-ideal solution showing negative deviation. Okay. Remember, in case of non-ideal solution showing positive deviation, experimentally determined vapor pressure will be greater than that of theoretically determined vapor pressure. In case of non-ideal solution showing negative deviation, experimentally determined vapor pressure will be less than that of theoretically determined vapor pressure. Okay, will be less than that of theoretically determined vapor pressure. Am I clear? Am I clear? Guys, listen, whatever I'm teaching you, questions will be asked from these topics only. Okay? Do not use your brain. Perfect? Just do whatever I'm telling you to do. All right? Got it? Got it? Just do whatever I tell you to do. Do not give me the orders. Just listen to my orders. Okay? So do not say, sir, this topic, that topic. I know what comes in the exam. That's what I'm teaching. Perfect? All right. So shut up. Perfect. Now, guys. Now, if you look carefully, we have got three types of things here. One is ideal solution. One is non-ideal solution showing positive deviation. One is non-ideal solution showing negative deviation. Okay. So people, try to understand and remember the things which I am giving you on one simple sheet. No need to go into much depth. No need to go into much depth, because whatever things I'll be writing on the screen, only these things will be asked in the exam. Nothing else. So here I'm writing ideal solutions. Ideal solution. Here I'm writing non-ideal solution showing positive deviation. Okay. Here I'm writing non-ideal solution showing negative deviation. Showing negative deviation. Okay. Directly I'm giving you the points. Try to remember them directly, and they are very easy to be remembered. They are very easy to be remembered. They are very easy to be remembered. See guys, in case of non-ideal solution, theoretically determined vapor pressure and experimentally determined vapor pressure, they'll come out to be equal. We know that already. Okay. In case of non-ideal solution showing positive deviation, experimentally determined vapor pressure will be coming out to be greater than that of theoretically determined. In case of non-ideal solution showing negative deviation, experimentally determined vapor pressure would be less than that of theoretically determined vapor pressure. Point number one. Point number one. Point number two. In case of ideal solutions, all the interactions, A interactions, PB interactions, and AB interactions, they are same. What does that mean? What does that mean exactly? If you have a look here, you have got pure liquid A. This is pure liquid B. This is solution of A and B. Here in this liquid, there are A interactions present. Here in this liquid, there are BB interactions present. Here in this liquid, there are AB interactions present. In case of ideal solutions, all these interactions are going to be magnitude-wise same. Okay, so A interaction, BB interaction, and AB interaction would be the same. Second point. Second point. Non-ideal solution showing positive deviation. Experimentally determined vapor pressure comes out to be greater than theoretical. What does that mean? That means whatever vapor pressure is coming out to be, whatever vapor pressure we are calculating experimentally, that is coming out to be greater than that of theoretical, that is coming out to be greater than that of as what was expected from Raoult's law. So technically, as per Raoult's law, all the interactions should be same. But in reality, I would say AB interactions would be weaker. AB interactions would be weaker in reality. That's why more vapors would have generated. That's why the experimentally determined vapor pressure would be greater than that of what we expected as per Raoult's law. Okay? So AB interactions are weaker than expected. Here I'll say AB interactions are stronger. AB interactions are stronger than expected. Okay? Correct? Correct? Now, my dear students, the third point. In case of ideal solution, remember delta V mixing is 0. Remember delta H mixing is 0. Okay? Remember delta S mixing is positive. Remember delta G mixing is negative. These are the direct points which I want all of you to remember. All of you to remember. In case of non-ideal solution showing positive deviation, remember delta V mixing is positive. Delta H mixing is positive. See, this is positive, positive, positive. Delta S mixing is also positive. Delta G mixing here is negative. It is negative. In this particular one, negative deviation. Negative deviation. Remember, delta V mix is negative. Delta H mix is also negative. Delta S mix is always positive. Okay? And delta G mix is negative. Questions will be asked from this table only. Questions will be asked from this particular table only. Okay? Anything. Delta H mix, delta V mix, delta S mix, delta G mix. And one more thing will be asked, my dear students. Remember, non-ideal solutions showing positive deviations, they form minimum boiling azeotrophs. They form minimum boiling azeotrophs. And negative deviation ones show they form maximum boiling azeotrophs. Maximum boiling azeotrophs. This will be the question asked. Which of the following solutions show, which of the following solution forms minimum boiling azeotrophs and maximum boiling? Non-ideal solution showing positive deviation, they form minimum boiling azeotrophs. Non-ideal solutions showing negative deviation, they form maximum boiling azeotrophs. And my dear students, whatever examples of ideal solutions are there in your NCERT, whatever examples of ideal solution, non-ideal solution showing positive deviation are in your NCERT, and whatever examples of non-ideal solution showing negative deviation are in your NCERT, you have to remember those examples as well. And examples you will be taking directly from your NCERT. Okay? Examples you'll be taking directly from your NCERT. Am I clear till here? Am I clear till here, my dear students? Everyone? Everyone in the chats? Am I clear till here quickly? Everybody. Everyone. Everyone means everyone. Everyone means everyone. Quick. Okay? All right. Basically, azeotrophs is not in your NEET syllabus. That is the syllabus for JEE students. Okay? There will be only two questions asked. Which of the following solutions showing minimum boiling azeotroph, maximum boiling azeotroph? Just remember that. That's more than sufficient. Why do you want to waste your time? Okay? All right. Do you want the dinner break right now? Do you want the dinner break right now? Okay, let's do one thing. Let's take the dinner break till, what is the time now? 9:30 till 10. But only one thing, my dear students, I want every one of you to be back exactly at 10 p.m. Okay, I want every one of you to be back exactly at 10 p.m. Okay? I want every one of you to be back exactly at 10 p.m. Will you be back by 10? Okay? I'm trusting you all right now. 1,550 students are watching. I would want everyone to be back on time. I want everyone to be back on time. Okay? I'll also have rest for like half an hour. I'm not going to have the dinner though, because if I have the dinner, I'll be sleepy. That's what I do not want. I'll have some coffee or something. You'll also be back, okay? Perfect. Exactly at 10, I want everyone to be back. Because at 10, I'll be starting. Okay? And if I saw people not coming at 10, then we might stop the session. The choice is all yours. Be back on time. See you. Is everyone back? Is everyone back? Wassim sir belongs to where? I'm right now live from Srinagar, Jammu and Kashmir. I'm from Srinagar. All right, everyone is back? People? Yes? Is everyone back with the same Josh? Or you are sleepy? Don't tell me you guys are sleepy. Don't tell me you guys are sleepy. We have to stay awake till 7 a.m. Do you know that? Do you know that? We have to stay awake till 7 a.m. Okay. All right. All right. I would want the same Josh throughout these 15 days, okay? Throughout these 15 days, I would want the same Josh. Okay, are you done with the dinner? Are you guys done with the dinner? Are you guys done with the dinner? Yes or no? Yes, sir. Fully active. Great. Well, once we complete the today's session, after that, on my Telegram only, I'll be sharing a DPP with you, which will contain 3 chapters: solution, kinetics, electrochemistry, right? And tomorrow you'll be solving those questions on your own. Okay? Never ate that quick. I did not eat anything though. I just had tea. Because I know if I'll eat something, I'll be passed out. Perfect. Should we start now? Should we start? Should we start? Should we start? Say yes or no in the chats quick. All ready? All ready? Quick, 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 quick. Let me see your chats once. All ready? Chat rate. Increase the chat rate. Quick. I want everyone to write it. Okay. All right. Perfect. Now, my dear students, now we are going to talk about one more important topic of the chapter. And this is your last topic of the chapter. What is that? That is your colligative properties. Colligative properties. My dear students, one thing I'm telling you. Whenever a question is asked from the chapter solution, whenever a question is framed from the chapter solution, it is framed particularly from 3 topics. One is concentration terms, one is the Raoult's law, and one is colligative properties. 95% chances are there that the questions will be asked from these 3 topics, right? Okay, so remember this. Concentration terms, your Raoult's law, and your colligative properties. Now, first of all, what are colligative properties? My dear students, let me tell you, colligative properties, these are the properties of These are the properties of ideal solutions. These are the properties of ideal solutions whose value only depends upon the number of particles of solute. Whose value only depends upon the number of particles of solute. So first of all, colligative properties. These are first of all the properties of ideal solutions whose value only depends on what? Whose value only depends on the number of particles of solute. That means when we change the number of particles of solute in the solution, the values of colligative properties will automatically change. Okay? So first of all, colligative properties, these are the properties of ideal solutions which only and only depends on the number of particles of solute. When we change the number of particles of solute, the values of colligative properties will automatically change. Now, my dear students, let me tell you how many colligative properties we have to study. The first colligative property which we shall be studying, that is going to be your relative lowering in vapor pressure. Okay, this is the first colligative property. Second one is going to be your elevation of boiling point. The third colligative property is going to be your depression of freezing point. The fourth colligative property is going to be your osmotic pressure. It is going to be your osmotic pressure. Now let's get to know one by one what these colligative properties exactly are. Relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. So mark the heading first of all as relative lowering of vapor pressure. Okay, a relative lowering of vapor pressure. Try to understand, my dear students, what I'll be doing. Imagine that this is one of the containers which I have. Imagine in this particular container, for example, I have got a volatile liquid A. There is volatile liquid A in this container, right? So basically, here you will find only and only the vapors of A, right? And the vapor pressure of A, when it is present in pure state, it is represented by P naught A. Vapor pressure of A, when A is present in pure state, is represented by P naught A. Now, my dear students, in this particular container, let's say I am adding a non-volatile solute B. In the same container. And let me tell you, when I will be adding a non-volatile solute B, what I'll be getting? I will be getting a solution. of A and B. And let me tell you, out of A and B, A is the volatile component and B is the non-volatile component. So here, you will only find the vapors of A, not the vapors of B, because B is non-volatile. B cannot form its vapors. Right? So, my dear students, vapor pressure of this solution was supposed to be equal to PA plus PB, but since B is non-volatile, it cannot form its vapors. So, B has got no contribution towards the vapor pressure of the solution. So can I say the total vapor pressure of the solution will be simply equal to PA, and PA, as you all must be knowing, is nothing but P naught A chi. Okay? Perfect. Now, my dear students, what happens? Write the statement. Okay? On adding a non-volatile solute in a volatile liquid, what happens? Vapor pressure decreases. And this decrease in the vapor pressure, And this decrease in the vapor pressure is called as lowering in vapor pressure. It is called as lowering in vapor pressure, and it is represented by delta P. It is represented by delta P. It is represented by delta P. Okay? It is represented by delta P. So basically, when you add a non-volatile solute in a volatile liquid, vapor pressure decreases. What does that mean? That means your PS, which is the final vapor pressure, it will be always less than that of initial vapor pressure. It will be always less than that of initial vapor pressure. Okay? It will be always less than that of initial vapor pressure. PS will be less than that of P naught A. Now, if I ask you how much vapor pressure has decreased, how much vapor pressure has decreased? That means I'm talking about lowering of vapor pressure. Initially, it was P naught A. Now it is PS. So I would say it is P naught A minus PS. It is P naught A minus PS. This is what I call as lowering in vapor pressure. Perfect. Now, my dear students, lowering in vapor pressure, delta P, lowering in vapor pressure with respect to initial vapor pressure. Lowering in vapor pressure with respect to initial vapor pressure is what we call as relative lowering in vapor pressure. Lowering in vapor pressure with respect to what? With respect to initial vapor pressure is what I call as relative lowering in vapor pressure. And this relative lowering in vapor pressure is equal to, let's see what we get the result. Delta P is nothing but, as I told you, it is P naught A minus PS divided by, this is P naught A. Now, my dear students, P naught A I'm writing as such. PS, few minutes back, we got to know PS is nothing but P naught A chi A divided by your P naught A. Divided by your P naught A. So if I take P naught A common here, P naught A cancels out. So it comes out to be 1 minus chi A, and 1 minus chi A is nothing but chi B. 1 minus chi A is nothing but chi B. So people, here we got one important result. What is that? That is the relative lowering in vapor pressure, which is delta P divided by P naught A is equal to mole fraction of non-volatile solute, which can be further written as number of moles of solute in the solution divided by total moles present in the solution. Okay, this is the result which all of you will be remembering. Number one. Number two, my dear students, if by chance you have got a dilute solution, for a very dilute solution, if by chance you have got a dilute solution means number of moles of solvent would be greater than, far greater than number of moles of solute. If you will be having a very dilute solution in which number of moles of solvent would be far greater than number of moles of solute, at that point of time, you can say delta P divided by P naught A has to be equal to NB divided by, instead of NA plus NB, I'll only write NA. NB approach towards 0 because NB is far less than that of NA. Perfect. This particular result is valid only for what? This particular result is only valid for the very dilute solutions. I hope this particular point is clear. Is this point clear? Let me know once in the chats. Quick. Is this point clear, people? Everybody. Is it clear? Is it clear? Is it clear? Now, my dear students, here I'm going to make one more expression which we are going to use in the questions directly. See, lowering in vapor pressure, that's delta P. If I divide it with PS, over here, what I'm exactly going to do, I am going to make one more result which I'll be using directly in the questions. Okay? Now, people, delta P, lowering in vapor pressure with respect to PS, with respect to final vapor pressure. First of all, this is not called as relative lowering. What is relative lowering? Relative lowering is when the denominator is P naught. When the denominator is P naught. So this is not your relative lowering in vapor pressure. I'm just going to make one expression for the numerical purpose. So delta P. Delta P is your P naught A minus PS divided by what? Divided by PS. P naught A I'm writing as such. PS is going to be P naught A chi A divided by what? Divided by P naught A chi A. So again P naught A cancels out. So it becomes 1 minus chi A divided by chi A. 1 minus chi A is nothing but your chi B divided by what? Divided by chi A. Chi B is nothing but number of moles of B divided by total moles present in the solution. This is number of moles of A divided by total moles in the solution. So this finally becomes NB divided by NA. So my dear students, one important result which I'll be frequently using in the questions. What is that? Delta P divided by PS is equal to NB divided by NA. And this particular result is valid for dilute as well as the concentrated solutions. Dilute as well as the concentrated solutions. Am I clear to everyone? Am I clear to everyone, people? Am I clear to everyone? Now, one more result here I'm making. Try to understand what I'll be doing. See, delta P divided by PS is equal to NB I'm writing as such. What is NB? Number of moles of solute. Number of moles of solute. What is Na? Na is mass of solvent divided by molar mass of solvent. Mass of solvent divided by molar mass of solvent. Okay? Perfect. Now, my dear students, let me just write this WA somewhere here. Correct? Now, for example, if I multiply with 1000 as well as if I divide with 1000, does not make any difference. If I am multiplying as well as dividing with 1000. Perfect. Now, people, if you look carefully, look at this particular term. Look at this particular term. Number of moles of solute divided by mass of solvent in grams multiplied by 1000. What do we call this particular term as? What do we call this particular term as? This is called as molality, right? So remember, delta P divided by PS is equal to molality of the solution multiplied by molar mass of solvent divided by 1000. And people, from this particular expression also, we can get the questions. From this particular expression also, we can get the questions. So there are three expressions which I would want every one of you to remember. Number one, that is the general expression. This is valid for only the dilute solutions, right? This is valid for dilute as well as concentrated. And this is the formula which I'll be using when in the question they'll ask me about the molality of the solution. Okay? Perfectly done till here? Perfectly done till here? Quickly? Perfectly done till here? Quickly? Yeah? Perfectly done till here? Let's have a look on the question. See what kind of the question can be asked here. Look here carefully. P naught of water is given. The vapor pressure of the solution containing 5.4 grams of non-volatile solute in 90 grams of water is 23.232 torr. Calculate the molecular weight of solute. See what you'll be doing. As far as the question is concerned, imagine this is the container in which you had water. Right? So over here, you will only find the vapors of water. And as per question, P naught water, which I'm representing with P naught A, it is given to me as 23.76 torr. Now, my dear students, in the container, what is the mass of water present? We have got 90 grams of water. So mass of solvent here in the container is 90 grams. Now, as per the question, what are we adding? We are adding a non-volatile solute B. And when we add a non-volatile solute B, what happens exactly? We'll be getting a solution. And this is your solution here. Perfect. Let the vapor pressure of the solution is equal to PS, right? And as per the question, vapor pressure of the solution is how much? It is 23.32 torr. If you look carefully, when we added non-volatile solute, what happened to the vapor pressure? Earlier it was 23.76. Now it's 23.32. That means vapor pressure has decreased. What do we need to calculate? We need to calculate the molecular weight of solute. Few minutes back, I gave you one result. That is P naught A minus PS divided by PS is equal to NB divided by NA. Valid for all dilute as well as concentrated solutions. Now, my dear students, what is P naught A? P naught A is 23.76. What is PS? PS is 23.32 divided by, what is PS? 23.32 is equal to number of moles of solute would be equal to mass of solute. Mass of solute is 5.4 grams divided by molar mass of solute, whole divided by number of moles of solvent would be equal to mass of solvent divided by molar mass of solvent. Can you see one equation which only contains one variable, and from this you can easily calculate molecular weight of solute which I was supposed to calculate. Okay, am I clear with this? A simple basic question, and these sort of questions are asked in your examination. Let me tell you that. Okay, these sort of questions are asked in your examination. My dear students, look at one more question. These are actually two questions. These are actually two questions. If you look carefully, what weight of non-volatile solute urea? What weight of non-volatile? Someone is saying, sir, do the calculation. Guys, calculation you have to do on your own. Okay? In 12 hours, we have to complete the entire physical chemistry of class 12th. So at least you have to do something on your own as well. You have to exert something. I cannot do calculation here. Perfect. If I start doing calculation, it has to exceed 20 hours. That is not possible. At least something you have to do on your own as well. Okay? Don't expect me doing everything for you. I can teach at least calculation part. That is something which you can do on your own, correct? Perfect. All right. What is it? Multiply and divide you have to do. Nothing else. Okay. Look at this particular question now. Look at this particular question now. See guys, as far as this particular question is concerned, this is your container which contains 100 grams of water. Which contains 100 grams of water. Okay, which contains 100 grams of water. Since this water is right now in its pure state, so let the vapor pressure of this pure water right now is equal to P naught A. Okay. As far as the question is concerned, we are adding urea here. Urea is the example of non-volatile solute. We are adding urea here. Okay. As per the question, when we are adding urea, what is happening exactly? When we are adding a non-volatile solute, what is happening? On adding non-volatile solute, you know, vapor pressure decreases. Okay. Vapor pressure decreases. And as far as the question is concerned, we have to add urea till vapor pressure decreases by 20%. So basically, we have to decrease the vapor pressure by 20%. Okay. We have to keep on adding urea till vapor pressure decreases by 20%. And when vapor pressure decreases by 20%, at that point of time, what will be the vapor pressure of the final solution? It is going to be initial vapor pressure minus 20% of P naught. Okay, this is going to be the final vapor pressure, which is going to be simply 0.8 P naught A. Which is going to be simply 0.8 P naught A. Initially, it was P naught A. Now we have to add urea till vapor pressure decreases by 20%. Till vapor pressure decreases by 20%. And the question is asking, what mass of urea needs to be added to decrease the vapor pressure by 20%? What mass of urea needs to be added to decrease the vapor pressure by 20%? So we have to calculate WB. Perfect. Again, I'll be using the result which I gave you. P naught A minus PS divided by PS is equal to NB divided by NA. Correct? So P naught A I'm writing as such minus, what is PS? PS is 0.8 P naught A divided by PS is again 0.8 P naught A is equal to NB, number of moles of solute. It is going to be mass of solute, mass of urea divided by molar mass of urea, whole divided by number of moles of solvent will be mass of solvent, that's 100 grams divided by molar mass of solvent, molar mass of water. P naught A, P naught A, P naught A cancels out. 1 minus 0.8 is 0.2 divided by, this is 0.8. Now 0.2 divided by 0.8 would be simply equal to 1 by 4. Would be equal to 1 by 4 is equal to, this would be WB divided by 60 and this is going to be 18 divided by 100. Can't you solve this equation and get the value of WB from here? What is this WB? This is the mass of solute which is to be added to decrease the vapor pressure by 20%. Okay? Perfect, guys. This was one of the question which was to be calculated. This was one of the question which was to be calculated. The second question here is, what will be the molality of the solution? In order to calculate molality, my dear students, I gave you one result. Do you remember that? People are saying WB value is coming out to be 83. Okay, I'm believing you here. Let it be 83 grams. So that means 83 grams of urea has to be added to decrease the vapor pressure by 20%. Okay? You had to decrease the vapor pressure by 20%. So initial vapor pressure was P0. Now, decrease it by 20%. So final vapor pressure will be P0 minus how much you have decreased. 20% you have decreased. So this comes out to be 0.8 P0. As simple as that. Now, my dear students, the second part of the question, we have to calculate molality. For that, I give you one result. P0A minus PS divided by PS is equal to, what was the result which we derived 2 minutes back? What was the result which we derived? See, P0A minus PS divided by PS is equal to MMA divided by 1000. MMA divided by 1000, right? It is going to be MMA divided by 1000. So people, P0A minus PS divided by PS. P0A minus PS divided by PS. P0A minus PS divided by PS. This value came out to be 1 by 4 if you look carefully. So instead of this whole term, I'll be writing 1 by 4. Okay. Molar mass of solvent, molar mass of water is 18. Perfect. So one equation, one unknown. So you can calculate molality, which will come out to be exactly how much? Almost 30. Perfect. This would be the molality of the solution. Am I clear to everyone now? Will you be able to solve the questions based on relative lowering? Yes or no in the chats? Quickly. Yes or no in the chats quickly? Yes or no in the chats quickly? Quickly, guys, everyone. Yes, 13.8 will be the exact answer. 13.8 would be the exact answer. All right. Okay. Value of Ma was 18. Ma is the molar mass of solvent, molar mass of water. That's 18. Now, my dear students, let's move on to the second colligative property, that's your elevation and boiling point. I'm not going into the very much details. I'm just giving you that information which is required to solve the questions. I'm giving you that information which will be asked in the exam. Okay? Not going into a lot of depth. Whatever is required, I'm providing you that. Okay? So guys, elevation of boiling point. So remember one thing. One statement I'm writing and remember it directly from now onwards. My dear students, on adding a non-volatile solute, in a volatile liquid, first of all, we know vapor pressure decreases, but remember, boiling point increases. And that increase in the boiling point, is called as elevation of boiling point, which I'm representing with delta TB. Okay? Which I'm representing with delta TB. So basically, what happens here, for example, again, this is a container which contains a volatile liquid. It contains a volatile liquid A. Okay. Let the boiling point of this volatile liquid is TB. I'm writing it as TB solvent. This is the boiling point of this volatile liquid. This is the boiling point of the liquid. Now, my dear students, when you will be adding a non-volatile solute B over here, What do you get first of all? You'll be getting a solution. This is a solution. This is a solution. This is the solution of A and B. This is the solution of A and B. Now, as I have told you, when you add a non-volatile solute in a volatile liquid, boiling point increases. Boiling point increases. Let the boiling point of this particular solution is equal to TB solution. Remember, TB solution is always greater than that of TB solvent. Is always greater than that of TB solvent. So, when you add a non-volatile solute in a volatile liquid, first of all, vapor pressure decreases, but at the same time, remember, boiling point increases. For example, if the boiling point of this liquid was 100, the boiling point of this solution will be more than 100. The boiling point of this particular solution would be more than 100. And this increase in the boiling point is what you call as delta TB, elevation in boiling point. And if I ask you how much boiling point has elevated, initially the boiling point was this, now the boiling point has increased, now it is TB solution. So elevation in boiling point is going to be boiling point of the solution minus boiling point of the solvent. Boiling point of solution minus boiling point of the solvent, right? And my dear students, remember this delta TB, elevation in boiling point, right? How it is exactly calculated? Let me give you one result directly. Remember that. Delta TB is equal to Kb multiplied by molality of the solution. Delta TB is equal to Kb multiplied by molality of the solution. What is Kb here? Kb is what you call as molal elevation constant. Molal elevation constant, or you can call it as ebullioscopic constant. You can call it as the ebullioscopic constant. And remember, the units of Kb is degree centigrade per molal. Is degree centigrade per molal. Or you can say Kelvin kg per mole. Okay. Perfect. You can call it as Kelvin kg per mole. Now, this Kb over here, remember it is solvent dependent. It is solvent dependent. Okay. This is one more point which I would want all of you to remember. And at the same time, guys, if you want to elaborate this particular equation, you can say delta TB is equal to Kb multiplied by molality of the solution will be equal to mass of solute multiplied by 1000 divided by molar mass of solute and mass of solvent in grams. Okay, this is something which you can remember as well. Okay, this is something which you can remember as well. Perfect. There is one more expression to calculate Kb separately, but that's not asked in your NEET examination. Only expressions which you have to remember is this and this. That's all. And one thing, when you add a non-volatile solute in a volatile liquid, what happens to vapor pressure? Vapor pressure decreases and boiling point increases. And that increase in the boiling point is what you call as elevation of boiling point. That's all. Okay, that's all. That's all. And what kind of question can be framed here? What kind of question can be framed here? You need to look at this particular question to understand what kind of question can be asked. Okay. If you look carefully, my dear students, in this question, find the weight of sucrose. Find the weight of sucrose. Sucrose is a non-volatile solute. That must be added to 100 grams of water to have the boiling point of solution 100.5 degree. Kb is also given. So a basic question this is. A basic question this is. See why it's basic question. As per the question, imagine that you have got 100 grams of water here. So mass of volatile liquid, mass of solvent here is 100 grams. Right? Since there is water in the container, what is the boiling point of water if I ask you? Boiling point of this solvent, boiling point of water, as you all must be remembering, it is 100 degrees centigrade. Now, as per the question, you are adding sucrose here. You are adding sucrose here. Sucrose is the example of non-volatile solute. When you will be adding sucrose, what will be happening? When you will be adding sucrose, what will be happening? Will the boiling point be increasing or decreasing? When you will be adding sucrose, you will be getting a solution. And you know, boiling point of solution is always more than that of boiling point of solvent. And what is the boiling point of solution here? As per the question, it's 100.5 degrees centigrade. Okay. What do we have to calculate? If I ask you, what do we have to calculate? We have to calculate the mass of sucrose which has to be added to increase the boiling point from 100 to 100.5. So the question is again based on elevation and boiling point. So people, I can say your delta TB is equal to KB multiplied by M. So how much is the elevation in boiling point? Earlier 100, now 100.5. How much boiling point has elevated? 0.5. This is the elevation in boiling point. KB value is given to me as 0.52 approximately. Molality of the solution would be mass of solute multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams. Correct? So people, it is going to be 0.5 is equal to 0.52. WB we have to calculate multiplied by 1000 divided by molar mass of solute means molar mass of sucrose, which is 342, and mass of solvent is 100. Do you see? You have got one equation which only contains one variable, and that is WB. So you can easily calculate your mass of solute here, which is to be added. Am I clear with this? Am I clear with this, everyone? Am I clear with this? Quickly. Yeah, a lot of people are saying the answer is 34.2. All right, I trust you. It is 34.2 grams. So 34.2 grams of sucrose has to be added to increase the boiling point of water from 100 till 100.5. Okay? All clear? All clear, guys? Quickly in the chats. Quickly in the chats. Done? Aditya, that's not required. That's not required. Perfect. Now, my dear students, this is the similar type of question. Just tell me in the chats, can you solve this? Look at the question once. On dissolving 3.24 grams of sulfur in 40 grams of benzene, elevation in the boiling point was 0.81 Kelvin. Calculate the molecular formula of sulfur if Kb is equal to something. Look at it once. Look at it once. Look at it once. See guys, how we are going to solve this question. See, first of all, as per the question, we are given with 40 grams of benzene. So benzene is your solvent here, and this mass of solvent, mass of benzene is 40 grams. Perfect. As per the question, since we have got a volatile liquid benzene, now in this benzene we are adding sulfur. I don't know which sulfur we are adding, right? Let the molecular formula of sulfur be Sx. It can be 2, 4, 6, whatever. We'll check that. Okay. Let the molecular formula of sulfur is Sx. And how many grams of this sulfur we are adding? What mass of the solute we are adding? We are adding 3.24 grams of this sulfur. And when we are adding 3.24 grams of sulfur here, I'll be getting a solution. I will be getting a solution. This is the solution which I have. Okay. In the question, they have mentioned when sulfur is added into benzene, boiling point has elevated. Elevation in boiling point is there. How much is elevation in boiling point? As per the question, delta TB value is directly given as 0.81. Right? But we know already delta TB is what? It is Kb multiplied by molarity, which is mass of solute multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent. And as per the question, this is 0.81. Now, Kb value as per the question is given 2.52. Mass of solute is 3.24. Multiplied by what? Multiplied by 1000. Molar mass of solute I'll be calculating. Molar mass of sulfur I'll be calculating. Mass of solvent, that is mass of benzene, is 40. And this is equal to 0.81. Can you solve this and let me know what is the value of MB which you'll be getting from here? Can you check it out? People are saying it is coming out to be 256 grams. So basically, you got the molar mass of solute. You got the molar mass of this Sx. If you got the molar mass, that means what would be the molecular mass of Sx? molecular mass of Sx will be 256 U or 256 AMU. Now you know molecular mass is what? Sum of atomic masses. So atomic mass of sulfur is 32 and how many sulfur atoms? X is equal to 256. Can you get the value of X here? I think the value of X will come out to be 8, right? If the value of X is equal to 8, I can say the molecular formula of the sulfur here is simply going to be S8. Am I clear? Am I clear, guys? Am I clear to everyone? Let me know in the chats quickly. Yeah? Am I clear? Next chapter is starting in next 45 minutes. Perfect. Now, my dear students, we have got one more colligative property. What is that? That is depression of freezing point. Again, one statement you will remember. That's it. One statement you will remember. And my dear students, the statement is like this. On adding a non-volatile solute in a volatile liquid, freezing point decreases. Freezing point decreases. And that decrease in the freezing point and that decrease in the freezing point is called as depression of freezing point, represented by delta TF. Like I told you, when you add non-volatile solute in a volatile liquid, what happens to vapor pressure? Vapor pressure decreases. What happens to boiling point? Boiling point increases. What happens to freezing point? Freezing point decreases. Freezing point decreases. So, remember it like this. For example, you have got a volatile liquid here. You have got a volatile liquid here. Let's say this volatile liquid is water. Okay? Perfect. It will be having some freezing point, which I'm representing with freezing point of solvent. Perfect. And freezing point of water, you already know, that is how much? 0 degrees centigrade. Now, when you'll be adding a non-volatile solute here, what you'll be getting? You'll be getting a solution here. This is a solution. This is a solution of A and B, right? Let this non-volatile solute be B. This is a solution of A and B. Now, this solution will also have a freezing point, which I'm representing with this freezing point of solution. Remember, when you add a non-volatile solute in a volatile liquid, freezing point decreases. So if the freezing point here was 0, here the freezing point will be less. It will be, for example, minus 0.3. It will be, for example, minus 0.3. And this decrease in the freezing point, is what we call as, depression of freezing point. Remember, freezing point of solution here will be always less than that of freezing point of solvent. Freezing point of solution will be always less than that of freezing point of solvent. Okay? Okay, I hope this is clear. Now, my dear students, if I write depression in freezing point, delta TF, depression in freezing point, like I gave the result for delta TB, similarly, there is one result for delta TF, and delta TF is nothing but, it is KF multiplied by molality of the solution. Or you can write it like this. Delta TF is equal to KF multiplied by molality of the solution is mass of solute multiplied by 1000 divided by molar mass of solute, and this is mass of solvent in grams. Okay, I hope this is clear. Perfect. And people, this KF is what you call as molar depression constant, or you can call it as cryoscopic constant. And at the same time, let me tell you, this cryoscopic constant, it is again solvent dependent, and its units are same, degree centigrade per molal, or you can say Kelvin kg per mole. Okay, right? So 3 things which you have to remember. On adding a non-volatile solute in a volatile liquid, first of all, vapor pressure decreases, boiling point increases, freezing point decreases. Okay, perfect. Perfect, guys. Now, can you give this question a try? A simple basic question. Can you give this question a try? A simple basic one. Find the freezing point of the solution obtained by mixing 18 grams of glucose in 90 grams of water. Kf is given. Kf is given. If you look carefully, this is the container, and in this particular container, what do we exactly have? We have got 90 grams of water. So mass of volatile liquid here is 90 grams. And what is this volatile liquid? It's water, right? So if you have got solvent as water, what would be its freezing point? Freezing point of solvent, freezing point of water is nothing but 0 degree, right? And now people, what are we adding here? We are adding a non-volatile solute. Which one? That is glucose. That is glucose. And how many grams of glucose we are adding? We are adding some 90 grams of, we are adding some 18 grams of glucose. We are adding some 18 grams of glucose. So what is going to happen? You know it already. What is going to happen? You know it already. When you add a non-volatile solute in a volatile liquid, you get a solution here. This is the solution of glucose and water. Now people, what would be the freezing point of this solution? Is it going to be more than 0 or less than 0? We already know on adding a non-volatile solute in a volatile liquid, freezing point decreases. So first of all, one thing is clear. TF of solution, that will come out to be less than that of TF of solvent. Okay, that will come out to be less than that of TF of solvent. Now people understand. Now people understand. We know delta TF, as I told you a few minutes back, is equal to KF multiplied by M. What is going to be delta TF? Depression in freezing point is going to be equal to TF of solvent minus TF of solution. TF of solvent minus TF of solution is equal to KF multiplied by molality. TF of solvent is already 0. So this term is 0. So it comes out to be minus TF of solution is equal to KF value is given to me as per the question, which is 1.86. Molality of the solution is equal to mass of solute multiplied by 1000 divided by molar mass of solute, molar mass of glucose multiplied by mass of solvent, 90. So when you solve this equation, what is the freezing point of solution which you get from here? Can you let me know in the chats? People are saying it's minus 2.06. Okay, I believe you. It is minus 2.06 degrees centigrade. This is something which I was supposed to calculate. That's it. Perfect. Perfect, guys. Am I clear with this, everyone? Right? Okay. All right. A lot of people are asking about what is going to be the next chapter. Let me create one more poll for you so that I get to know what people want the next. Just a second. And then we'll start with that only. Just a second, guys. Just a second. Just a second, guys. Okay, I'll check the poll results after some time. Okay, now since we are done with depression and freezing point, now let's have a look on one more colligative property. What is that? That is your osmotic pressure. That's your osmotic pressure. First of all, what is osmosis basically? What is osmosis? If you look at the definition here, it is the net moment of solvent molecules, net moment of solvent particles from just a second, from solvent side to the solution side, or from less concentrated side to the more concentrated side. What does it mean? Let's try to understand. See guys, let's try to understand what this osmotic pressure is all about. See guys, for example, this is a container which I'm taking. Let's say this is the container which I'm taking. Okay, I am dividing this particular container in two parts with the help of a semi-permeable membrane. This is a semi-permeable membrane which I am using. And I am using that semi-permeable membrane which allows the movement of solvent particles only. Which allows the movement of solvent only, not the solute. Which allows the movement of solvent only, not the solute. Now, my dear students, here, what exactly am I doing? Here on this side, I'm keeping a pure solvent. On this side, I'm keeping a pure solvent. And on the other side, what am I doing? On the other side, I'm keeping a solution. First of all, whenever you have got solvent and solution in direct contact with each other with the help of that SPM which allows the movement of solvent molecules, what happens? Through this SPM, there will be movement of solvent. There will be movement of solvent from this side to this side as well as this side to this side. There will be movement of solvent from this side to this side as well as this side to this side. Perfect. But remember, the net movement of solvent will be from solvent side to the solution side. The net movement of solvent will be from solvent side to the solution side. Okay? And this net movement of solvent particles from solvent side to the solution side is what you call as osmosis. Since there is a net movement of solvent molecules from solvent side to solution side, so what will, if for example there is a piston here, what will happen to this piston? There is a net movement of solvent molecules from solvent side to solution side, right? So what will happen to this piston? Will it go down or it will start going up? It will start going up, right? If I do not want this piston to go up, I'll have to apply some pressure here. If I do not want this piston to go up, I'll have to apply some pressure here, right? The minimum pressure, the minimum excess pressure that has to be applied, the minimum excess pressure that has to be applied on the solution side, to stop the net movement of solvent from solvent side to the solution side, is what you call as osmotic pressure. So the minimum excess pressure which I have to apply on this side to stop the net movement of solvent molecules is what I call as osmotic pressure. And this osmotic pressure is represented by pi. Number one. Number two, this osmotic pressure pi, it is equal to, I'm giving you the direct results, it is equal to CRT. This osmotic pressure pi is equal to CRT. What is C here? C represents molarity of this solution. Or you can say concentration of this solution. Or you can just write it as pi is equal to MRT, where M is the molarity of this particular solution. Or you can write it like this. Pi is equal. Molarity is number of moles of solute divided by volume of solution in liters, R and T. My dear students, this is the result with the help of which you can calculate the osmotic pressure of the solution. Number one. Point number one. Point number two, my dear students. As I told you, the minimum excess pressure which has to be applied on this side to stop the movement of solvent molecules, to stop the net movement of solvent molecules, is what you call as osmotic pressure. Now, tell me one thing. Tell me one thing. If the applied pressure is greater than that of osmotic pressure, if the applied pressure is greater than that of osmotic pressure, what will happen? I'll say this piston will start going down. So there will be net movement of solvent from solution side to solvent side. And at that is something which you call as reverse osmosis. At that time, what happens? Reverse osmosis happens. Okay? And that reverse osmosis is the technique used for desalination of seawater. Desalination of seawater. And remember, when we do the desalination of seawater, the semi-permeable membrane used at that time is cellulose acetate. Okay? The SPM used at that time is cellulose acetate. This can be asked as a direct question. Okay? Perfect. Now, people, there are few more things which I would want to share with you. I believe these three things you would have studied in your bio as well. What are, first of all, isotonic solutions? Two solutions are called isotonic if they have got the same osmotic pressure. If they have got the same osmotic pressure, right? If they have got the same osmotic pressure, I'll write at same temperature. At same temperature. If I've got two solutions, for example, if I've got two solutions which have got same osmotic pressure, pi 1 is equal to pi 2. Pi 1 is equal to pi 2. What is pi 1? Pi 1 will be C R T. Pi 2 will be C2 R T, because temperature is same on both the sides. So RT gets cancelled out. So I can say C1 has to be equal to C2. So whenever you have got isotonic solutions, the ones which have got same osmotic pressure, the ones which have got same osmotic pressure at same temperature, remember their concentrations are also same. Remember their molarities, their concentrations, they are also same. Remember this particular point. Okay, two solutions which have got same, again I'm repeating the same thing. Two solutions which have got same osmotic pressure at same temperatures, right? Remember their concentrations, they are also the same. Their molarities are also the same. What is hypotonic? Hypotonic and hypertonic. Hypotonic and hypertonic. A solution is called as hypotonic if its osmotic pressure is lower than that of solution from which it is separated by a semi-permeable membrane, right? These are the direct definitions which I believe you would have studied in your bio as well, hypertonic as well as hypotonic. You have to remember directly their definitions, nothing else. Remember their definitions directly. I'm directly jumping into the questions which are asked basically. What are the questions? Let's have a look. For example, you have got a question like this. Let's say you have got a question like this. You have got a question like this. See guys, calculate the osmotic pressure at 273 Kelvin of a 5% weight by volume solution of urea in ATM. So first of all, what is meant by 5% weight by volume? It means that 5 grams of solute, that's urea, is present in 100 ml of solution. Correct? This is something which is given. This is something which is given. So basically, the mass of solute, W2, is equal to 5 grams. Volume of the solution is equal to 100 ml. Molar mass of solute, molar mass of urea, remember it directly from now onwards, it's 60 grams per mole. What do I need to calculate? Osmotic pressure. What do I need to calculate? Osmotic pressure. Osmotic pressure I'm representing with pi. That's equal to MRT, or you can say CRT. So pi is equal to molarity is number of moles of solute divided by volume of solution in liters, R as well as T. So I'll say pi is equal to number of moles of solute would be equal to mass of solute, that's 5 grams, molar mass of solute, that's 60, volume of solution in liters, 100 ml means 0.1 liter, R value 0.0821 ATM liter per Kelvin per mole, temperature is given to me as 273 Kelvin. You just need to solve this equation and you'll be getting the answer exactly in what? Answer you'll be getting exactly in ATM, atmosphere. Okay? Perfect, guys. Is it clear? Let me know quickly in the chats. Is it clear? Is it clear? Everybody in the chats. Is it clear? Is it clear, people? Yes, temperature has to be in Kelvin. So whenever osmotic pressure has to be calculated in ATM, at that time use this value of R, 0.0821 ATM liter per Kelvin per mole. Okay? Someone is asking, please give the R values. R has got three values to be remembered. One is 8.314 joules per Kelvin per mole. One is 0.0821 ATM liter per Kelvin per mole. And the third one is 1.98, or approximately you can take 2 calories per Kelvin per mole. These are the three values of R, which you have to remember. I believe I am clear with all of this. And my dear students, it is the time to talk about the last topic of the chapter. What is that? That is Introduction to Van 't Hoff Factor. Introduction to Van 't Hoff Factor. Before discussing the Van 't Hoff Factor, if you remember, we have discussed four colligative properties. One is the relative lowering. That is P naught A minus PS divided by P naught A is equal to mole fraction of solute. Number one. Number two was elevation in boiling point, delta TB. That was equal to KB multiplied by molality. Similarly, delta TF, that was equal to KF multiplied by molality. Similarly, osmotic pressure, that is equal to C, R, and T. These are the four colligative properties which we have discussed. Number one is, this is what you call as relative lowering. This is called as elevation of boiling point. This is called as depression of freezing point. And this is called as osmotic pressure. This is called as osmotic pressure. These are the four colligative properties which we have discussed till now. Now, my dear students, what exactly is going to happen now? We are going to start talking about the Van 't Hoff Factor. So I'm writing the heading here as Introduction to Van 't Hoff Factor I. Introduction to Van 't Hoff Factor I. Okay, Introduction to Van 't Hoff Factor I. So, see what is going to happen basically. Since we have got four colligative properties, relative lowering, elevation, depression, osmotic pressure. Okay. My dear students, in order to calculate any colligative property, be it lowering, be it elevation, be it depression, be it osmotic pressure, in order to calculate any colligative property, we have got exactly two ways. We have got exactly two ways. Either you will be calculating the colligative properties with the help of these formulas. You can calculate the value of colligative properties with the help of these formulas, which I'll be calling as the calculated value of colligative property. Okay? Or you can call it as the theoretical value of colligative property. Theoretical. Or you can call it as expected value of colligative property. So whenever the value of colligative properties are calculated with the help of these formulas, you call the colligative property as calculated or theoretical or expected. Now, if you want to calculate colligative property of a solution experimentally, you can calculate it experimentally as well. And at that time, it is called as directly observed value of colligative property or actual value of colligative property or experimentally determined colligative property. So basically, we have got two ways to calculate the colligative property. Either with the help of formulas, which you already know, or you can analyze the solution in the lab and get the experimental value of colligative property. Now, my dear students, let me tell you, there are some solutions for which there are some solutions for which there are some solutions for which experimentally determined colligative property and theoretically determined colligative property, they come out to be equal. There are some solutions for which these two come out to be equal. Experimental and theoretical, they come out to be equal. But again, there are some solutions for which experimentally determined colligative property and theoretically determined colligative property, they do not come out to be equal. They do not come out to be equal. They do not come out to be equal. First of all, when these two come out to be equal, these two come out to be equal when the solute used in the solution neither dissociates nor associates. What does that mean? When you drop solute into the solution, it should not break down. It should not break down. It should not associate as well. Breakdown means one particle should not form two particles in the solution, or two particles should not combine to form one particle. So that's why I'm telling you this particular thing, experimentally determined colligative property of a solution and theoretically determined colligative property, they are equal for those solutions where the solute used neither dissociates nor associates. Okay? But experimentally determined colligative property and theoretically determined colligative property, they do not come out to be equal for those solutions which dissociates or associates, wherein solute dissociates or associates. Remember this particular time. Remember this particular point. Remember this particular point, it's important. Okay? And since, my dear students, as I told you, there are some solutions wherein experimentally determined colligative property and theoretically determined colligative property, they do not come out to be equal. They do not come out to be equal for some solutions. For some solutions. So what do we do? What do we do? Since LHS and RHS is not equal. Since LHS and RHS is not equal. So if I want LHS and RHS to be equal, I'll be adding one correction factor here. And when I add this correction factor, your LHS and RHS, it comes out to be equal. LHS, RHS comes out to be equal. And this correction factor used is what you call as your Van 't Hoff vector. This is what you call as your Van 't Hoff vector. So I over here is nothing but it is CP observed experimental divided by CP calculated. Divided by CP calculated. Perfect. Remember this particular point. Number one. Number two, my dear students. Number two. Since colligative property is inversely proportional to molar mass of solute. Since any colligative property, it's inversely proportional to molar mass of solute. So I can write it like this as well. I can write it as molar mass of solute calculated divided by molar mass of solute observed. This is one more way of calculation of your Van 't Hoff vector. Remember these 2 points. Remember these 2 points because I'll be using these 2 points directly in the questions. Okay? So guys, tell me one thing. Since these are the 4 formulas which we have discussed, tell me one thing. Are these formulas always giving the correct results? I'll say these formulas are only giving us the correct results when the solute neither dissociates nor associates. What if solute in the solution dissociates or associates? At that time, these formulas are not going to give us the correct results. So in order to modify these formulas, in order to make sure that from these formulas we get the correct results, what do? I'll be multiplying everywhere with the Van 't Hoff vector. Now they are the corrected formulas. Now they are the corrected formulas. Now they are the corrected formulas. Am I clear? Now they are the corrected formulas. Now people, how do we do the calculation of this Van 't Hoff vector? Understand and remember. Understand and remember. First of all, if we have got the solute that neither dissociates nor associates, if we have got that solute, when you have got a solute that neither dissociates nor associates, for that particular solute, I value is directly taken as 1. For that solute, I value is directly taken as 1. For that solute, I value is directly taken as 1. But whenever you have a solute that dissociates, whenever you have a solute that dissociates, what does that mean? See, for example, I have got a solute like this. Let's say I've got a solute of this format, AN. Let's say I've got a solute of this format. When you put this solute into the solvent, let's say it dissociates like this, N times A. See, the stoichiometric coefficient here is 1. The stoichiometric coefficient here is N. Let's say N value is greater than 1. Let's say N value is greater than 1. For example, N value is 2. If N value is 2, that means one particle of solute, when it goes into the solvent, it is giving 2 particles. If N is 3, one particle is giving 3 particles. One particle will be giving 4 particles. One particle giving 5 particles. So it is the case of dissociation. And whenever you have got a solute which undergoes dissociation, for that, I value, first of all, is always greater than 1. And how do you calculate this I? Simple result, 1 plus N minus 1 into alpha. 1 plus N minus 1 into alpha. How do we get this? You have got nothing to do with that. I'm not going for the derivation and stuff. Okay? Perfect. Similarly, whenever you have got that solute which associates, that means if you have got a solute like this, N times A gives AN. Here the coefficient is N. Here the coefficient is 1. Let's say N value is again greater than 1. Okay? If N value is greater than 1, that means it can be 2. If N is 2, that means 2 particles of solute, when they enter into the solution, they give 1 particle. So 2 particles are associating to form 1 particle. Or it can be 3 particles associating to form 1 particle. It can be 4 particles associating to form 1 particle. Right? Okay, so this is the case of association. In case of association, remember, first of all, I value is always less than 1. And how do we exactly get this I value? It is 1 plus 1 divided by N minus 1 into alpha. I is equal to 1 plus 1 divided by N minus 1 into alpha. Okay, perfect. Remember these 2 results. My dear students, here alpha is what you call as degree of dissociation, and here alpha is what you call as degree of association. Okay? Perfect. Perfect, guys. In case of dissociation, I value is directly proportional to N. In case of association, as you can see, in case of association, I is inversely proportional to N. In case of association, I is inversely proportional to N. Now, people, let's see what kind of questions will be asked here. And I believe you can easily solve the questions. I believe that. See, for example, this is the question. For example, this is the question. The question is the values of observed and calculated molecular weights. The values of observed and calculated molecular weights of AgNO3 are 92.64 and 170 grams respectively. Calculate degree of dissociation for AgNO3. So first of all, tell me how this AgNO3 solute will undergo dissociation. It will undergo dissociation as Ag positive plus NO3 negative. Right? Now, here the stoichiometric coefficient is 1. Here it is 1. Here it is 1. So 1 particle is giving 2 particles. So N value here is 2. 1 particle is giving 2 particles. So N value here is 2. Correct? What do I need to calculate? I need to calculate alpha. First of all, you know your Van 't Hoff factor I is equal to calculated value of molecular weight divided by observed value of molecular weight. What is calculated? Calculated is 170. What is observed? Observed is 92.84 or 64. 92.64. This value will be approximately equal to 1.8. So what did we get? We got the Van 't Hoff factor. People, if you got the Van 't Hoff factor, what do we need to calculate? Alpha. You know, I is nothing but it is 1 plus N minus 1 into alpha in case of dissociation. I value we have calculated 1.8. 1 plus N value is 2 minus 1 into alpha. So alpha value here directly comes out to be 0.8. Is this clear? Is this clear to everyone? Quick, people. Is this clear to everyone? Yeah? Perfect. Okay. The degree of dissociation of a weak electrolyte AXBY. Imagine you have got the solute, you have got the weak electrolyte as AXBY. First of all, how will it undergo dissociation? Weak electrolyte AXBY undergoes dissociation as X times AY positive plus Y times BX negative. First of all, what is the N value? This is 1 here. The coefficient here is X, the coefficient here is Y. One particle is giving X plus Y. One particle is giving X plus Y particles, right? And what is N? Number of particles produced from one particle of reactant. Number of particles produced from one particle of reactant. So N value is nothing but X plus Y. You just have to write, you just have to get the I value. And you know, I is nothing but 1 plus N minus 1 into alpha. We have to calculate degree of dissociation alpha. We have to calculate degree of dissociation alpha. So I'll say alpha has to be equal to I minus 1 divided by N minus 1. So I am writing as such minus 1 divided by. What is N? N is X plus Y minus 1. So this is the value of alpha in terms of I. This is the value of alpha in terms of I. I hope this is also clear. I hope this is also clear. Perfect. Okay. Look at this question, for example. This is a special one, okay? Because Hg2Cl2, you have to remember this. How Hg2Cl2 undergoes dissociation. Okay, remember this. Hg2Cl2 undergoes dissociation as Hg2 di positive plus 2 times Cl negative. Remember this example. Okay, this Hg2Cl2 will be using in equilibrium chapter as well. Hg2Cl2, it undergoes dissociation as Hg2 di positive and twice Cl negative. The stoichiometric coefficient here is 1. Here the stoichiometric coefficient is 1. Here it's 2. First of all, one particle is giving 2 plus 1, 3 particles. So N value is 3. One particle is giving exactly 3 particles. So N value here is 3. Okay, N value here is 3. Now, as per the question, this electrolyte is 80% ionized. That means alpha is 0.8. We are done. What do I need to calculate? Van 't Hoff factor I. Since this is the case of dissociation, so I is equal to 1 plus N minus 1 into alpha, which is 1 plus, what is the N value? N value is 3 minus 1. What is the alpha value? Alpha is 0.8. So it is going to be 1 plus 2 into 0.8. It is 1.6 plus 1. That comes out to be 2.6. So I value here is nothing but 2.6. Are you understanding what I'm doing exactly? Okay. Perfect, guys. All right. One more question. One more question. Look here carefully. Look here carefully. Calculate I when 0.1 molar solution of NH4Cl. So basically you are taking NH4Cl. First of all, you should know how NH4Cl undergoes dissociation. NH4 positive plus Cl negative. So one particle is giving 1 plus 1, 2 particles. So N value here is 2. N value here is 2. Okay. What do I need to calculate? Alpha is given. Alpha is 0.8. We have to calculate Van 't Hoff factor I. See, all the other parameters which are given, they are just to confuse you. They are just given to confuse you. Nothing else. I just have to use the formula. I is equal to 1 plus N minus 1 into alpha. So 1 plus N value is 2 minus 1 and alpha is 0.8. So the value comes out to be simply 1.8. That's it. All the other parameters, they are given to confuse you, nothing else. They are given to confuse you, nothing else. Okay? Perfect. Perfect, guys. Okay. A millimolar solution of K3FeCN6. K3FeCN6 is 70% dissociated. Find the osmotic pressure. First of all, you should know how this K3FeCN6 undergoes dissociation. It undergoes dissociation as 3 times K positive plus FeCN6 tri negative. This is how it undergoes dissociation. Number 1. Number 2, the coefficient here is 1. The coefficient here is 3. The coefficient here is 1. So one particle is giving 3 plus 1, 4 particles. If one particle is giving 4 particles, N value is 4. What do I have to calculate? What do I have to calculate? What do I have to calculate? I have to calculate, okay, one more thing is given. This K3FeCN6 is 70% dissociated. So alpha is 0.7. I have to get the value of osmotic pressure. Osmotic pressure is pi. And pi is nothing but ICRT. ICRT. So pi is equal. First of all, I need to know the value of I. I need to know the value of I. And I for dissociation is nothing but 1 plus n minus 1 into alpha. So I is equal to 1 plus, what is n? N is 4 minus 1. What is alpha? 0.7. So 7 3s are 21 plus 1, that is 3.1. So I value I got to know is 3.1. I is 3.1. Concentration is molarity. Millimolar means 10 raised power minus 3 molar, right? We have to calculate the value in ATM. So R value, which one I'll be using? 0.0821. Temperature, how much? 27 degrees centigrade. That means 300 Kelvin. Solve this and get the answer exactly in what? Get the answer exactly in atmosphere. Am I clear? Am I clear, guys? Am I clear? Quickly, let me know in the chats. Am I clear? Everybody. Yeah? Everyone in the chats, am I super clear to everyone? Okay, I had given you a poll, guys, and you have made it a tie. 50% students are saying kinetics, 50% students are saying electrochemistry. So which chapter should we start? Write it in the chats now. I want to know it in the chats. Okay? Guys, one topic I'm leaving here in the solution that you need to do on your own. That's a complete theoretical topic. A smaller one, that's Henry's law. Just remember its applications from your NCRT. That's it. In your NCRT, there are few applications of Henry's law given. Just remember that directly. Tell me the next topic, next chapter, guys. I want to know in the chats. I want to know in the chats. Everyone. Everyone. Till then, I will be sitting here for like 2 minutes. So tell me, which chapter is the next? Electrokinetics. Wow, nice, good. Electrokinetics. Hello? Okay, so people tell me. Tell me. You're saying electro, huh? All right. Let's do one thing. Let's complete kinetics first. Because kinetics is small. Kinetics will not take more than, I think, more than 3.5 hours. Okay? Let's start with kinetics. All right? Let's start with kinetics. It's okay. We'll complete it quick. Anyways, we have to complete everything, right? We are together till 7 a.m. You have promised that. And you cannot break your promise. That too with your teacher. Yeah? It has adverse effects. It has adverse effects. We have to complete everything. We have to stay awake till 7 a.m. I hope you know that. If you're sleepy, go wash your face. Yeah? Come back. And then we'll start. I'm giving you the break of 15 minutes. Okay? You can freshen up so that we can start with the next chapter. And the next chapter is going to be chemical kinetics. So, break till, what is the time now? It is 11:30. So, break till 11:45. But I would want everyone to be back on time. Is that a promise? Is that a promise? Yeah? I would want all the 1300 students who are watching us live right now, I would want them to be back exactly at 11:45. Okay? Chalo. Guys, only you are not tired. Let me tell you what was my schedule for today. Let me tell you. I started my offline classes at 8 in the morning. From 8 till 4, I took 7 to 8 offline classes. Okay? Then from 7 p.m., I started the online class. 7 p.m. to 7 a.m., I have got your class. Okay? Then again tomorrow at 8 a.m. in the morning, I have to go for the offline classes. Again, 7 classes back to back. And once I come back tomorrow, then I'll sleep. That is my schedule. I can do that, you can do that too, right? Anyways, you guys are going to go into the college, right? You guys will be going to the college. For me, I'll be here only. Yeah? So we have to do a lot. If I'm sacrificing something, you have to sacrifice too. Okay? And that's how you succeed. Okay? Chalo, I'll see you after the break. So, people, are you back? Is everyone back or not? What's up? With the same Josh or not? With the same Josh or not? Yeah? With the same Josh or not? Perfect, perfect. Amazing. All right, so guys, tell me whatever things we have discussed till now, is everything clear? Let me know once in the chats. Whatever things we have discussed till now, is every single thing clear? Yeah? All right. All right. All right. All right. Perfect then. Should we start? Are you ready for the chemical kinetics? Are you all ready for the chemical kinetics? Tell me that. Are you ready for the chemical kinetics? Okay, one thing I want to ask you before starting kinetics. Have you studied this chapter before ever? Have you studied this chapter before ever? Okay. Okay. All right, got it. Chalo, let's begin. I'll be starting from the basics only, don't worry. Okay? Since a lot of students are saying they have studied for the boards level and all, so I'll be starting from the basics only, don't worry. Got it. Chalo, let's get going. Let's get going, guys. First of all, I am going to start this chapter with one statement. And the statement is pretty much simple. What is that? As a chemical reaction proceeds, as a chemical reaction proceeds, remember, concentration of reactant decreases and concentration of product increases with time. Concentration of reactant decreases and the concentration of product increase with time. What does that mean, first of all? My dear students, for example, you have got the reaction like this. A gives B, where A is the reactant, B is the product. Okay? Let's say this particular reaction is taking place in a vessel whose volume is V liters. First of all, if I ask you what is concentration? Concentration is nothing but number of moles divided by volume of the reaction vessel in liters. What does that mean? For example, if I write concentration of reactant will be nothing, just number of moles of reactant divided by volume of reaction vessel. Concentration of product is going to be nothing, number of moles of product divided by volume of reaction vessel. Okay. Now, my dear students, you must be knowing, as the reaction proceeds, number of moles of reactants, they keep on decreasing, because reactants, they keep on getting converted into products. So as the reaction proceeds, number of moles of reactants, it decreases with time. Similarly, I would say number of moles of products, it increases with time. Now people, if number of moles of reactants decreases with time, since they are directly proportional, therefore concentration of reactant also decreases with time. Similarly, if the number of moles of products increase with time, that means concentration of products will also increase with time. That is the statement which I have mentioned over here. As the reaction proceeds, concentration of reactant decrease with time, concentration of product increase with time. Okay? If you want to represent the statement graphically, you can represent the statement graphically as well. How exactly? Have a look. Let's say on this side I'm representing concentration versus time. Here also I'm representing concentration versus time. For example, I have to plot a graph for the reactant here. And here I have to plot a graph for the product. Now I told you, as the time goes on, concentration of reactant, it keeps on decreasing with time, like this. As the time goes on, concentration of product, it increases with time. So whenever the graph starts from the top, keeps on coming down, remember the graph is for reactant. When the graph starts from bottom and keeps on going up, remember the graph is for product. Point number one. Now point number two. Since you got to know, as the reaction starts, the concentration of reactants as well as products, it keeps on changing. Concentration of reactant decreases and concentration of product increases with time. That is something which you got to know. Now, my dear students, the first topic which we are starting here, from which questions are asked. What is that? That is the rate of reaction as per stoichiometry. This is the first topic from where you get a question. Rate of the reaction as per stoichiometry. My dear students, let's say I have got a balanced chemical equation like this. N1A plus N2B. Let's say it gives N3C plus N4D. First of all, the N1, N2, N3, N4. N1, N2, N3, N4. What are these? These are the stoichiometric coefficients of reactants products. Now, reactant here is A and B. And as I told you, as the reaction proceeds, reactants, their concentration decrease with time. Products, their concentration increase with time. Or I can say, reactants, they disappear with time. Products, they appear with time. They get formed with time. Okay? So people, the first thing which I'm writing over here, what is that? I'm writing a term, rate of disappearance. First of all, tell me, disappearance term, is it used for reactant or product? I would say disappearance term is used for reactant. For example, I'm writing rate of disappearance of A. It is written as rate of disappearance of A. Since I'm talking about disappearance, A is disappearing with time. So I'll be starting with the minus sign. Number one. Now I'll be writing change in the concentration of A in the time interval delta T. This minus delta A by delta T. Change in the concentration of A divided by time interval delta T. This is what I call as rate of disappearance of A. Point number one. If I, for example, want to write rate of disappearance. Rate of disappearance of what? Rate of disappearance of B. B is again the reactant. So I'll be starting with the minus sign. Change in the concentration of B divided by time interval delta T. This term represents rate of disappearance of B. Now, if I write rate of appearance, appearance is the term. You can write appearance or you can write formation. Appearance is the term which is used for product. So rate of appearance of C, I'll be starting with the plus sign. Then I'll be writing change in the concentration of C divided by time interval delta T. If I want to write rate of appearance of D, rate of appearance of D, I'll be starting with plus. It's again going to be change in the concentration of D divided by time interval. Now, my dear students, remember one thing. Whenever I want to write rate of disappearance or rate of appearance, whenever I want to write rate of disappearance or rate of appearance, I have got nothing to do with the stoichiometric coefficients. Whenever I will have to write rate of appearance or disappearance, remember, I'll have to do nothing with the stoichiometric coefficients. Do you see anywhere I wrote any stoichiometric coefficient? No. I did not use any N1, N2, N3, N4 anywhere. So remember, in short, whenever you need to write rate of appearance or rate of disappearance, you have got nothing to do with the stoichiometric coefficients. Point number one. Point number two, my dear students. Point number two. What is point number two? See, I'm writing the balanced chemical equation as N1A plus N2B. It gives N3C plus N4D. It's a balanced chemical equation. Now, my dear students, there is one more term. What is that term? That is simply rate of the reaction. First of all, I talked about rate of disappearance or appearance of a reactant or product. Now, there is one more term that's called as the rate of reaction. And how do you write rate of reaction? Rate of reaction is written as rate of disappearance or appearance of a reactant or product divided by the stoichiometric coefficient of the reactant or product. Rate of reaction is equal to rate of reaction. Earlier it was rate of disappearance appearance of a reactant product. Now it's rate of reaction. Rate of reaction is written as rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient. For example, if you look carefully, rate of reaction is equal to, let me write rate of reaction with respect to A. A is the reactant. So I'll be writing rate of disappearance of A. How do I write rate of disappearance of A? It will be minus change in the concentration of A divided by time interval, all divided by stoichiometric coefficient of A is N1. So the value comes out to be minus 1 divided by N1, change in the concentration of A divided by time interval delta T. So this particular term over here, it gives me the rate of the reaction. This particular term, it gives me the rate of the reaction. Similarly, if I want to write rate of reaction with respect to B, B is again the reactant. So I'll be starting with the minus sign, 1 divided by. What is the stoichiometric coefficient here? That's N2. Then I'll write change in the concentration of B divided by time interval delta T. This term again is giving me the rate of the reaction only. Similarly, I can write rate of reaction with respect to C as well. C is the product. So I'll be starting with plus sign, 1 divided by. Stoichiometric coefficient here is N3. Now here I'll be writing change in the concentration of C divided by time interval delta T. This term also is giving me the rate of the reaction only. Similarly, I can write it with respect to D. So plus 1 divided by N4, change in the concentration of D divided by time interval, that is delta T. Divided by time interval, that is delta T. So all these terms, this one, what these terms are going to give me? They are going to give me the rates of the reactions. They are going to give me the rates of the reactions. So my dear students, there is a difference. Whenever you want to write rate of disappearance or appearance, at that time you have got nothing to do with the stoichiometric coefficients. But whenever you have to write rate of the reaction, at that time you have to divide with what? You have to divide with the stoichiometric coefficients. Point number 1. Okay. And this equation which you got over here, this equation is what you call as differential form of rate. This is what we call as differential. This is what we call as differential form of rate. Differential form of rate. Okay, differential form of rate. Now, people, one more important thing. One more important thing. Let me tell you, for a homogeneous gaseous phase reaction, for a homogeneous gaseous phase reaction, rate can be expressed. Rate can be expressed. Rate can be expressed in terms of. Rate can be expressed in terms of pressure as well. Rate can be expressed in terms of pressure as well. What does exactly that mean? What does exactly that mean? For example, I'm taking a gaseous phase reaction like this. N1A gas plus N2B gas. It gives me N3C gas plus N4D gas. If you look carefully, all the reactants and products, they are in gaseous phase. All the reactants and products, they are in gaseous phase. So it's a homogeneous gaseous phase reaction, which is, for example, carried out at a particular temperature. Which is carried out at a particular temperature. Now, my dear students, if I want to write the differential form of rate, how do I write it? R is equal, rate of the reaction is equal, minus 1 divided by N1, change in the concentration of A divided by time interval delta T. With respect to B, minus 1 divided by N2, it is change in the concentration of B divided by time interval delta T. Similarly, plus 1 divided by N3, change in the concentration of C divided by time interval delta T. Similarly, plus 1 divided by N4, change in the concentration of D divided by time interval delta T. So this particular equation, as I told you already, is called as differential form of rate. And my dear students, remember one thing. Whenever you need to calculate rate, and you'll be using this expression or this expression or this expression or this expression to calculate the rate of reaction, remember, at that point of time, you are calculating rate in terms of moles, liter inverse, second inverse, if time is in seconds. Whenever rate is to be calculated in moles per liter per second, you have to use one of these expressions to calculate rate of the reaction. Now comes a point. Now comes a point. I believe every one of you would have heard about ideal gas equation. PV is equal to nRT. PV is equal to nRT. So can I say P is equal to N divided by VRT? Absolutely. P is equal to N divided by VRT. So P is equal to N by V is concentration. N by V is concentration. Moles per unit volume is concentration. So can I say PA is equal to concentration of ART? Similarly, PB is equal to concentration of BRT. PC is equal to concentration of CRT. PD is equal to concentration of DRT. Right? And people, if you want to write this equation in another format, you can write it as minus 1 by N1. Change in. Instead of concentration of A, I'll write pressure of A divided by RT. So it's pressure of A divided by RT, and in the denominator, already you have got delta T is equal to minus 1 divided by N2. Change in the, instead of concentration of B, I'll write pressure of B divided by RT multiplied by delta T, right? Similarly, it's plus 1 divided by N3. Change in, it's pressure of C divided by RT multiplied by delta T. Similarly, it's plus 1 divided by N4. Change in the pressure of D divided by RT multiplied by delta T. So first of all, this RT, I'm cancelling everywhere. So my final equation becomes minus 1 divided by N1, change in the pressure of A divided by delta T is equal to minus 1 divided by N2, change in the pressure of B divided by delta T, which is also equal to plus 1 divided by N3, change in the pressure of C divided by delta T, which is also equal to plus 1 divided by N4, change in the pressure of D divided by delta T. This equation is also called as differential form of rate, but this is in terms of pressure. This is in terms of pressure. So my dear students, remember one thing. Whenever you use these terms to calculate rate of reaction, that means at that time you are calculating rate, for example, in ATM second inverse. If pressure is in ATM, time is in seconds, then If you use this term, it will give you the rate of reaction in atm second inverse. This term also gives me the rate of reaction in atm second inverse. If pressure is in atm, time is in seconds. Similarly, this term also, this term also. So basically, two types of questions will be framed here. One will be calculate the rate of reaction in moles per liter per second. Second, calculate the rate of reaction in atm second inverse. If you are supposed to calculate rate of reaction in moles per liter per second, then use these terms. If you are supposed to calculate rate of reaction in atm second inverse or bar second inverse or mm of Hg second inverse, then use these particular terms over here. Am I clear? Quickly in the chats. Am I clear? Quickly in the chats, everybody. Am I clear till here? Everybody in the chats. Everyone in the chats. Everyone in the chats. Everyone in the chats. Let's have a look on the first question. Let's have a look on the first question. Have a look properly. As far as this question is concerned, I'm given with a balanced chemical equation. In the question, they have mentioned the rate of appearance of O2. How do I write rate of appearance of O2? It will be plus change in the concentration of O2 divided by delta T. This is what you call as rate of appearance of O2. And as per the question, it's 0.5 moles liter inverse second inverse. Then calculate the rate of disappearance of N2O5. How do I write the disappearance of N2O5? That will be minus change in the concentration of N2O5 divided by delta T. This is what you call as the rate of disappearance of N2O5. This is to be calculated. Rate of appearance of O2 is given. Rate of disappearance of N2O5 is to be calculated. How do I solve these sort of questions? See, whenever you get this sort of a question, the first thing which you will be doing, you will be writing the differential form of rate. Write the differential form of rate. I can say R is equal minus 1 divided by 2, change in the concentration of N2O5 divided by what? Divided by delta T is equal. It's again going to be plus 1 divided by 2, change in the concentration of N2O4 divided by time interval delta T is equal. It is plus 1 by 1, change in the concentration of O2 divided by delta T. This is my differential form of rate. Okay. Now, my dear students, from this particular equation, just take two terms out. This one and this one. Just equate these two terms. Just equate these two terms. And when I equate these two terms, I'll be getting minus delta of N2O5 divided by delta T. This 2 will come here is equal. It's going to be 2 times plus delta O2 divided by delta T. Now, my dear students, as per the question, 2 I'm writing as such. Delta O2 divided by delta T is nothing but 0.5. The value comes out to be 1 mole liter inverse second inverse. So whose value this is? Whose value this is? I'll say this is the value of what? This is the value of minus delta N2O5 by delta T, which is the rate of disappearance of N2O5. So you have calculated the rate of disappearance of your N2O5 and it came out to be exactly how much? 1 mole per liter per second. Am I clear with this? Am I clear with this? Quickly in the chats. Quickly in the chats. Everybody in the chats. Yeah? Perfect. Look at the next question, guys. I'm given with a reaction. All right. Calculate the rate of reaction in the interval 5 to 15 seconds. So interval that's given to us in the question is this 5 to 15 seconds. That means the interval here is of 10 seconds. 15 minus 5, this interval is 10 seconds. Okay. If you look carefully, concentration is decreasing with time. Concentration is decreasing with time. And we know concentration of reactant decrease with time. So this graph is basically valid for what? This graph is valid for reactant. And the reactant in this reaction is NH3. So I would say this particular graph is valid for what? This particular graph is valid for NH3. This particular graph is valid for NH3. Okay. This particular graph is valid for NH3. Now, my dear students, what do I need to calculate? I need to calculate rate of reaction. So rate of reaction, let's try to calculate with respect to NH3. I'll write minus 1 by stoichiometric coefficient, change in the concentration of NH3 divided by time interval. Now, it's going to be minus 1 by 2. Tell me, change in the concentration of NH3. At 5 seconds, This is the concentration of NH3. At 15 seconds, this is the concentration of NH3. So this is initial concentration of NH3. This is final. So change in the concentration of NH3 will be final concentration of NH3 minus initial concentration of NH3 divided by time interval is how much? Time interval is 10 seconds. So how much this value will come out to be? It will come out to be 0.02 moles liter inverse second inverse. Done? Moles liter inverse second inverse. This is what I was supposed to calculate, rate of reaction. I hope I'm clear to everyone. I hope I'm clear to everyone. My dear students, what if you get this sort of a question? What if you get this sort of a question? You are given with the reaction and there are some values which are given here. I need to get the relation between K1, K2 and K3. A simple basic question this is. It looks difficult. It's not. What do I need to do? First of all, the reaction that's given to me, write the differential form of rate for this particular reaction. Differential form of rate. I'll be starting with minus change in the concentration of N2O5 divided by delta T, because the stoichiometric coefficient here is 1. Here it's going to be plus 1 by 2 change in the concentration of NO2 divided by delta T. Here I'll be writing 1 by 1 by 2. 1 divided by 1 by 2 comes out to be 2 change in the concentration of O2 divided by delta T. Now it's completely your choice whether you want to write delta or you want to write D. You could have written minus D of N2O5 by dt plus 1 by 2 D of NO2 by dt. You could have written 2 times D of O2 divided by dt. The choice is all yours. The choice is all yours. Now people, as per the question, minus D of N2O5 divided by dt is given to me as per the question. That is K1 multiplied by N2O5 concentration is equal to 1 by 2. D of NO2 by dt. D of NO2 by dt is given to me as K2 multiplied by concentration of N2O5. Similarly, it's 2 times. D of O2 by dt. D of O2 by dt is K3 multiplied by concentration of N2O5. First of all, I can say this N2O5, N2O5, N2O5 cancels out. And when it cancels out, I got to know K1 is equal to K2 divided by 2 is equal to 2 times K3. Multiply throughout by 2. This becomes 2 times K1 is equal to K2 is equal to 4 times K3. Is equal to 4 times K3. Okay, this is the relation between K1, K2 and K3 which I was supposed to calculate. Am I clear? Am I clear? Everyone? Sir, will you take inorganic chemistry marathon also? Absolutely. I'll take inorganic chemistry also. I'll take class 11th physical chemistry also. Don't worry. All right. Perfect, guys. I hope all of this is clear. I hope all of this is clear. Now comes one more topic. What is that? Are you guys sleepy or what? You're not writing anything in the chats. The chat speed is very low. I don't want the chat speed to be low. I do not want the chat speed to be low at all. Yeah, now it's fine. Okay, you guys are awake. That's what I wanted to know. Great. See guys now. See what I'm doing here. Law of mass action. First of all, this law of mass action, it's a complete theoretical concept. It is a complete theoretical concept. Okay. It was given by 2 scientists. One is called as Goldberg. One is called as Goldberg and P. Vage. These were the 2 scientists which gave this particular concept, that is law of mass action. It's complete theoretical. It does not have any experimental background. Okay. Now people, what this law of mass action says. Say, for example, you have got the reaction like this. N1A plus N2B. It gives product. Let's say it's a balanced chemical equation. Let's say it is a balanced chemical equation. Now, law of mass action tells us that rate of the reaction is directly proportional. Rate of reaction is directly proportional to the product of active masses of reactants. Reactant here is A and B. So we have to write active mass of A multiplied by active mass of B raised to the powers of their respective stoichiometric coefficients. So active mass of A raised par its stoichiometric coefficient N1. Active mass of B raised par its stoichiometric coefficient N2. As per law of mass action, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. Okay. This is the simplest statement of what? This is the simplest statement of law of mass action. Now, my dear students, one thing I want you guys to remember. Whenever you see any reactant or product in aqueous state, for that reactant or product, active mass is its concentration. Whenever you have any reactant or product in gaseous phase, its active mass is going to be either its concentration or you can take its active mass as pressure. Whenever you have got a reactant or product in pure solid or pure liquid form, its active mass is taken as unity. These are the three things which I would want you guys to remember. Okay? For any reactant or product which is in solid or liquid form, its active mass is unity. Okay? Gaseous form, its active mass is its concentration or pressure. Aqueous form, active mass is its concentration. Perfect? For example, one thing. Imagine this is an aqueous state. Imagine this is also an aqueous state. So I can say rate of reaction is equal to, I'll put a constant K. Instead of active mass of A, I'll write concentration of A because A is in aqueous form. Raised par stoichiometric coefficient. This is concentration of B. Raised par its stoichiometric coefficient. So this equation also gives me what? This equation also gives me the rate of the reaction. And let me tell you, whatever rate of reaction we calculate with the help of law of mass action, it's always going to be the theoretical rate. It's always going to be the theoretical rate. Whatever rate of reaction we calculate with the help of law of mass action, it's always going to be the theoretical rate. Okay? It's always going to be a theoretical rate. Now, my dear students, let me tell you one very, very, very important thing. See, in order to calculate rate of the reaction, we have got two ways. Okay? Either I will be calculating rate of reaction with the help of law of mass action, which I'm calling as theoretical rate of reaction, or I will do certain experiments and calculate rate of reaction experimentally. I'm calling that rate of reaction as the experimentally determined rate. So basically, there are two ways to calculate rate of reaction. One is with the help of law of mass action. One is experimentally. Let me tell you, there are some reactions for which theoretically determined rate and experimentally determined rate, they come out to be equal. But again, there are some reactions for which theoretically determined rate and experimentally determined rate, they do not come out to be equal for some reactions. So what can you understand from this? For some reactions, theoretically determined rate, that means the rate calculated from law of mass action, comes out to be equal to the actual rate which comes from experiments. But for some reactions, theoretically determined rate and experimentally determined rate, they do not come out to be equal for some reactions. What does that mean? Does that mean from this particular expression, do you always get the correct actual rate of reaction? That means in this particular expression, there is some mistake which we are doing. In this expression. That's why from this expression, we do not always get the correct rate of reaction. We get correct rate of reaction for some reactions, but not for all. So this particular expression, right, it does not always give us the correct value of the rate of reaction. So basically, that means we need to modify this expression. So that the modified expression gives us always the correct value of rate. So what I'll be doing, I'll be introducing one more thing here. That is what I'll be calling as the rate law. That's what I'll be calling as the rate law. Let me tell you, if I talk about rate law is first of all based on, it is based on law of mass action. It is based on law of mass action. Now, what rate law is actually? It is the modified law of mass action. Rate law is basically when we modified law of mass action, we'll be getting the rate law. Now, try to understand what I'll be saying. For example, you have got the reaction N1A aqueous plus N2B aqueous. It gives us product. It gives us product. Okay? Now, my dear students, rate law says that rate of the reaction is directly proportional to the product of active masses of reactants. So I'll write concentration of A multiplied by concentration of B. But we used to, in the law of mass action, we used to take the powers as N1, N2 always. But rate law says that powers are not always N1, N2. The powers are going to be X and Y. The powers are going to be X and Y. And this X and Y is to be calculated experimentally. This X and Y is to be calculated experimentally. For some reactions, X and Y, when we calculate experimentally, they'll come out to be same as that of N1, N2 only. But for some reactions, X and Y comes out to be different. So first of all, remember this X and Y, they are calculated experimentally. They are calculated experimentally. So the equation becomes R is equal to constant K, concentration of A raised power X, concentration of B raised power Y. Concentration of B raised power Y. Okay, this equation is something which I call as rate law. What do I call this as? Rate law. We call this as rate law. Okay, we call this as rate law. So what is the difference between rate law and law of mass action? As per law of mass action, the powers are N1, N2 always. As per rate law, the powers are X and Y, which can be equal to N1, N2, but it's not necessary. They'll be always equal to N1, N2. Okay, it's not necessary. And let me tell you, this X over here, this X which you have over here, this X is called as order of the reaction with respect to A. Y is called as order of the reaction with respect to B. And if I add them up, this X plus Y is what you will be calling as the overall order of the reaction. You'll be calling as the overall order of the reaction. This R over here is what you call as the rate of the reaction. This K over here is what you call as rate constant of the reaction. It's called as a rate constant of the reaction. And let me tell you, this rate constant of the reaction, it gives us the idea about the speed of the reaction. It gives us the idea about the speed of the reaction. And at the same time, let me tell you, more the rate constant of the reaction, more is going to be the rate of the reaction. That means faster is going to be the reaction. Faster is going to be the reaction. Okay, rate constant, it gives us the idea about the speed of the reaction. More the value of rate constant, faster is going to be the reaction. Faster is going to be the reaction. Number one. Number two, this rate constant, I will say every reaction has a particular value. Every reaction has a particular value of rate constant. Every reaction has a particular value of rate constant at a particular temperature. Okay? And at the same time, my dear students, at the same time, rate constant of a reaction depends on temperature. It depends on temperature. For now, you will remember one thing. On increasing the temperature of the reaction, rate constant of the reaction increases. On increasing the temperature of the reaction, rate constant of the reaction increases. And if rate constant increases, eventually rate of the reaction is going to increase. Why it happens, how it happens, that's something which will be discussed in the Arrhenius equation. Okay, for now, you remember one thing, that your rate constant, it depends on the temperature. Perfect. When you increase the temperature of the reaction, the rate constant value automatically increases. And if the rate constant increases, the rate of the reaction automatically increases. Okay, these are the three things which I would want you guys to remember about the rate constant. So what is the difference? Where the difference lies in law of mass action and rate law? In law of mass action, the powers are always stoichiometric coefficients. In rate law, the powers are calculated experimentally. Okay, the powers are calculated experimentally, which can be equal to the stoichiometric coefficients, but not necessary always. Okay, got it? And x is what you call as order with respect to A, y is called as order with respect to B, x plus y is called as overall order of the reaction. I hope I'm clear with this. And if we are clear with this, then there is one more thing which I would want to discuss with you. What is that? See, we have got two types of reactions as per kinetics. We have got two types of reactions as per kinetics, as per chemical kinetics is concerned. One is called as elementary reaction. One is called as complex reaction. What is elementary? What is complex? Let's get to know about that as well, because this is a small topic, a basic topic this is. See guys, if you talk about the elementary reactions are the ones which are completed in a single step. Elementary reactions are the ones which are completed in one step only. Single step reactions are called as elementary reactions. And people, one important thing. For elementary reactions, law of mass action is truly valid. For elementary reactions, law of mass action is truly valid. What exactly that means? What exactly that means? Let's say this is one elementary reaction. Let's say this is an elementary reaction. Okay. I've got two ways to calculate rate. Either I'll use the law of mass action, I'll calculate the critical rate, or I can use the rate law and calculate experimentally determined rate. Where the difference lies? Here the powers are n1 and 2. Here the powers are x and y. Okay. X and y is calculated experimentally. And in case of elementary reactions, when you calculate x and y, x value exactly comes out to be same as that of n1 and y value exactly comes out to be same as that of n2. Okay. I told you already there are some reactions for which theoretically determined rate and experimentally determined rate, they come out to be equal. Which reactions are they? They are your elementary reactions basically. They are your elementary reactions basically. Okay? Am I clear? Am I clear, people? For elementary reactions, law of mass action is truly valid. Okay? Perfect. Let me know once in the chats if it is clear. Let me know once in the chats if it is clear, everyone, quickly. Everyone quickly. Now, my dear students, what are complex reactions? What are complex reactions? Complex reaction is opposite of it. Any reaction that gets completed in more than one step. Any reaction that gets completed in more than one step. Any reaction that gets completed in more than one step is called as complex reaction. And the steps which are involved in a complex reaction, they're elementary. For example, let's say I'm writing a reaction NO plus Br2. It gives us NOBr2. It gives us NOBr2. Now this NOBr2 plus NO gives us 2 times NOBr. Gives us 2 times NOBr. Now, my dear students, if I add these two reactions, can I say this term and this term gets cancelled out? So net reaction is NO plus NO makes it 2 times NO plus what? Plus Br2. It gives us 2 times NOBr. It gives us 2 times NOBr. Now, if you look at this net reaction, is this net reaction carried out in a single step or more than one step? I would say this net reaction is carried out in more than one step, right? So any reaction that gets carried out in more than one step, what do you call that reaction as? You call that as the complex reaction. Okay. How many steps this complex reaction has? It has got 2 steps, right? My dear students, the steps which are involved in the complex reaction, they're elementary. So I would say this step is elementary as well as this particular step is elementary. And among these steps, one of the steps will be the slow step. Among these steps, one of the step will be the slow step. And the slowest step is something which determines the rate of the reaction. So you call that as the rate determining step. The slowest step in the mechanism, is going to be your rate determining step. Okay? I hope this is clear. See, this was a reaction wherein this step is slow. So this particular step is going to be the rate determining step. Yeah? Perfect. I hope this is clear. Now, my dear students, comes one more point. What is that? That is molecularity of the reaction. What is molecularity basically? How do we define the molecularity? First of all, one thing, this molecularity concept, it is also a theoretical concept. It does not have any experimental background. It's complete theoretical. Okay? It's complete theoretical. Now, my dear students, one important thing. There is one topic that we have to discuss in this chapter, that is collision theory. And what collision theory says? Collision theory says that for the reaction to happen, reacting species, they must collide first. Collision theory says that for any reaction to happen, reacting species, they must collide first. Okay, they must collide first. Now, what is molecularity? The number of reacting species, which can be atoms, ions or molecules, the number of reacting species that collide simultaneously to form the products. How many reacting species are colliding simultaneously and forming the products? That defines molecularity of the reaction. For example, look at this particular reaction. If you look at this particular reaction, one molecule of H2, one molecule of I2, they are colliding and forming the product. So, since 2 molecules are colliding and forming a product, I would say molecularity of this particular reaction is 2. Okay. See, the coefficient here is 2, the coefficient here is 1. Okay. I'll say 3 molecules are colliding and forming the product. So, molecularity of this reaction is 3. Molecularity of this reaction is 2. And similarly, molecularity of this reaction is 1. So, based on molecularity, we classify reactions into many types. That reaction whose molecularity is 1 is called as unimolecular reaction. That reaction whose molecularity is 2 is called as bimolecular. Similarly, this is going to be your trimolecular reaction. Perfect. So based on molecularity, we classify the reactions into many types. Okay, I hope this point is also clear. Now, my dear students, there are few points which you need to know about molecularity, which are important. Molecularity of the reaction, it can never be 0, it can never be fractional, it can never be negative. See, if I say I've got a reaction whose molecularity is 0, what does that mean? That means 0 molecules have collided. Is it making any significance? 0 molecules have collided and formed the product. Does not make any significance, right? Does not make any significance. So molecularity of the reaction cannot be 0. If I say 1.3 molecules have collided and formed the products, does it make any significance again? No. If I say -3 molecules have collided and formed the products, does it make any significance? No. So remember, molecularity of the reaction, it can never be 0, it can never be negative, it can never be fractional. Okay. Similarly, reactions which have got molecularity greater than 3. They are rarely found. See, when 2 molecules collide and form the products, we say that reaction has got molecularity 2. When 3 molecules simultaneously collide and forms the product, we say that reaction has got the molecularity 3. Okay. Now, the probability of more than 3 molecules, the probability of more than 3 molecules to collide simultaneously, the probability of more than 3 molecules to collide simultaneously and form the products, that probability is very low. That's why those reactions which have got molecularity greater than 3, they are rarely observed, because the probability of more than 3 reacting species to form the products, the probability of more than 3 reacting species to simultaneously collide and form the products is very rare. Perfect. That's why those reactions which have got molecularity greater than 3 are rarely found. At the same time, molecularity term, it's only and only given for elementary reactions. Okay, molecularity term, it is defined only for elementary reactions. Complex reactions, molecularity of complex reactions does not make any significance. Molecularity concept is given to only elementary reactions. Okay, it's not valid for complex reactions. It's not valid for complex reactions. For example, see, this is one of the step, this is one more step. Perfect. If I add these two steps, what do I get? I get 2 times NOBr, 2 times NO plus Br2, it gives 2 times NOBr. This is the final reaction. What do I call this reaction as? This is a complex reaction. For the complex reaction, we do not define molecularity. Molecularity is defined only for elementary reactions. But we know the steps which are involved in the complex reaction, they're elementary. This reaction is elementary. This one is also elementary. And for the elementary ones, molecularity is defined. Molecularity is defined. So what is the molecularity of the first step? 1 plus 1. Molecularity of the first step is 2. Molecularity of this step is 1 plus 1. That's also 2. Okay? Molecularity of the complex reaction is not defined. But we know the steps which are involved. Steps which are involved in the complex reaction, they're elementary. And for elementary reactions, we define molecularity. I hope this point is also clear to everyone. Okay? I hope this particular point is also clear to everyone. Now, my dear students, like molecularity, there is something called as order of the reaction as well. As I told you already, there is something called as order of the reaction as well. What is order exactly? Order of the reaction. What is order? For example, I have got a balanced chemical equation, N1A plus N2B. It gives product. It's a balanced chemical equation. It's a balanced chemical equation. Now, people, if I write rate law for this particular reaction, how do I write rate law? R is equal to K, concentration of A raised by X, concentration of B raised by Y. This is your rate law. This is your rate law. Okay. Now, in the rate law, if you look at the powers, this X, as I told you a few minutes back, this is called as order with respect to A. Y is called as order with respect to B. If I add them up, X plus Y is what you call as the overall order of the reaction. The overall order of the reaction. So first of all, let me tell you, my dear students, in order to calculate order of any reaction, what do I need to write? I need to write the rate law. In order to calculate order of the reaction, what do I need to write? I need to write the rate law, because from the rate law only, the powers are going to give us the order. Okay? And if you know rate law, is it theoretical or experimental? Rate law is theoretical. Sorry, rate law is experimental. If rate law is experimental, that tells you that order is also experimental quantity. It is experimentally determined. It is the experimentally determined quantity, right? In order to calculate the order, we need to write the rate law. Okay? Rate law is experimental. Therefore, order is also the experimental one. My dear students, order of the reaction can be zero. Order of the reaction can be positive. Order of the reaction can be fractional as well. Okay? Can be fractional as well. That reaction whose order is 0, you call that a zero order reaction. That reaction whose order is 1, you call that as first order reaction. Order 2, second order reaction. Whose order is in fraction, that is the fractional order reaction. That is the fractional order reaction. But remember, order with respect to any reactant, order with respect to any reactant can be negative. Order with respect to any reactant can be negative. But remember the overall order. But remember the overall order of the reaction. Overall order of the reaction can never be negative. Can never be negative. This is one important point. Order of the reaction with respect to any reactant, it can be negative. But overall order of the reaction, it can never be negative. That means this X can be negative. Y can be individually negative. But when you do X plus Y is never going to be negative. This is something which has been observed experimentally. Okay? Perfect. Order with respect to any reactant can be negative, but overall order of the reaction can never be negative. And one more important point. For an elementary reaction, remember, order is equal to molecularity. For an elementary reaction, order is equal to molecularity. Okay, this is one more important point. For an elementary reaction, order is equal to molecularity. Whatever is going to be the molecularity of the elementary reaction, same is going to be the order of elementary reaction. Okay, and at the same time, one more point. A zero order reaction can never be elementary. A zero order reaction can never be elementary. It is always complex. A zero order reaction that is never elementary, that's always what? That's always complex. Why is that? Because if you have got the zero order reaction is the one whose order is zero. If the zero order reaction was elementary, that means its molecularity also should have been zero. If you have got the reaction whose order is zero, if that was supposed to be elementary, then its molecularity should also be zero. But molecularity is equal to zero does not make any significance. Perfect. So remember, a zero order reaction, it can never be elementary. It's always what? It's always complex. Okay, it's always complex. One more thing I would want to add over here. Okay, and after that we'll solve certain questions. What is that? Units of rate constant. Units of rate constant. Remember this point as well. Units of rate constant. For example, you have got the reaction like this. N1A plus, or let's keep it simple, N1A gives N2B. This is, for example, a balanced chemical equation. Okay, this is a balanced chemical equation. Let's say order of this particular reaction is equal to N. Let's say order of this particular reaction is equal to N. It can be 0, 1, 2, 3, whatever. Okay. Now, my dear students, remember, when you talk about the rate constant unit, rate constant units are going to be moles liter inverse raised power 1 minus N second inverse. Or it can be written as rate constant units are, let's say pressure is in ATM, raised power 1 minus N, let's say time is in seconds, second inverse. So basically, let's say you have got a zero order reaction. Zero order reaction is the one whose order is equal to 0. If N value is 0, 1 minus 0 is 1. So rate constant units are simply going to be moles liter inverse second inverse, or it can be ATM second inverse. For example, you have got a first order reaction. That means that particular reaction whose order is equal to 1. If N is equal to 1, 1 minus 1 is 0, anything raised power 0 is 1. So rate constant units are going to be simple second inverse. Similarly, here also, 1 minus 1 is 0, anything raised power 0 is 1, it's going to be second inverse. Perfect. Similarly, my dear students, for a second order reaction, I'll say that particular reaction whose order is equal to 2. Put the value of N as 2, it's going to be moles, 1 minus 2 is minus 1. So mole raised power minus 1, liter minus 1 raised power minus 1 is liter, and here is second inverse. Or you can write it like this as well, liter, mole inverse, second inverse. Or if you want to use this expression, put the value of N as 2, 1 minus 2 is minus 1. So K is going to be ATM inverse, and if time is in seconds, second inverse. So based on the order, the units of rate constant, they also change. Okay, based on the order, the units of rate constant, they also change. Now guys, if this is clear, Then let's have a look on simple questions which can be asked from the order. Okay, simple questions which can be asked from the order. Okay. Am I going fast? Am I going fast for you? No, right? It's perfect. No, I saw some of the comment. Someone was saying, sir, you are going fast. So that's why I thought. How to find the reaction is slow or fast? It will be given in the question itself. Okay. It will be given in the question itself. Now see guys, try to understand what I do here in this question. If you look carefully, for a chemical reaction A gives B, you have got a chemical reaction A gives B, whose rate constant is K. It is found that the rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. Whenever you see such kind of the question, do it with the help of a simple procedure. Let's assume that order of the reaction is equal to N. If order of the reaction is equal to N, you can write the rate law. R is equal to K, concentration of A, raised per order. Raised per N. Okay, raised per N. Because here, you have got only one reactant. That means order with respect to A, as well as the overall order of the reaction, will be equal to what? Will be equal to N. Okay, calling this equation number 1. Now, as per the question, it is found that the rate doubles. So initially, if the rate is R, now it has become 2R. The rate doubles when the concentration of A is increased 4 times. Earlier, the concentration of A was normally A, now it is 4 times A, raised per N. Equation number 2. So how many equations I got? I got 2 equations. My dear students, if I got 2 equations, just divide these 2 equations. Equation 2 divided by equation 1. When you divide them up, RR gets cancelled. On left side, you have 2. KK, A raised per N gets cancelled. This is 4 raised per N. When can be left hand side and right hand side equal? Left hand side and right hand side can be equal only if N value is 1 by 2. Right? If N value is 1 by 2. So simple. N is 1 by 2. That means order of the reaction is nothing but 1 by 2. Is this question clear? A simple one. Okay? A simple one. And can be asked. Simple one and can be asked. Now look at the next one. Look at the next one. You are given with the reaction A gives B, whose rate constant is K. First of all, let the order of this particular reaction is equal to N. Let the order of the reaction is equal to N. Now first thing, let me write the rate law. R is equal to K, concentration of A raised per N. Perfect. I can write this rate law like this as well. R is equal to K. Concentration of A is nothing but moles of A divided by volume of the reaction vessel raised per N. Let me call this equation number 1. Now the question says the rate of the reaction becomes half. So initially it was R. Now it is becoming R by 2. When volume of the vessel is doubled, so initially it was V, now it is 2 times V raised per N. Calling this is equation 2. Calling this is equation 2. So if I divide these 2 equations, let me divide equation 1 with equation 2. Equation 1 with equation 2. So RR gets cancelled, 2 comes up. Okay, is equal. KK gets cancelled. NA by V gets cancelled. So on this side, you get 2 raised per N. So 2 raised per 1 is equal to 2 raised per N. That means N value has to be equal to 1. And what is N? N is nothing but order of the reaction. Guys, do you understand how do we solve these sort of questions? Do you understand how do you solve these sort of questions? Say yes or no in the chats quick. Say yes or no in the chats quick. Yeah? Break I'll give you at 1:30. Okay? Break I'll give you at 1:30. Just be like this. Don't worry. Okay, break I'll give you at 1:30 exact. Okay, break I'll give you at 1:30. All right? Sir, your height. My height is 6 feet. I'm 6 exact. Okay. Guys, let's have a look. Let's have a look on one more topic. And this topic is also frequently asked. This topic is also frequently asked. And what this topic is all about? See, experimental determination of order. How order can be calculated experimentally. How order can be calculated experimentally. See guys, this particular concept of calculation of order experimentally, I'll make you understand with the help of the direct question. With the help of direct question. And look at the question carefully. You are given with a reaction, okay? And for this particular reaction, some experiments are carried out. Like you can see, in experiment number 1, concentration of NO is kept this much, concentration of H2 is kept this much. At that time, it is observed that rate of reaction is this much. Okay. Similarly, experiment number 2 is also carried out. On keeping the concentration of NO this much, H2 this much, rate of reaction is this much. Similarly, experiment number 3 is also carried out. So from these experiments, we have to get the order of the reaction. So how exactly am I going to solve this? Try to understand. I'll solve only one question of this particular concept, and from this question only, everything should be cleared. See guys, whatever reaction will be given to you, first of all, you will be writing the rate law for the reaction. Rate law says that R is equal to K, that is rate constant, concentration of NO raised by X, concentration of H2 raised by Y. The first step always is to write the rate law. So you have written the rate law. Now, my dear students, in this rate law, put the data of the experiments in this rate law. As per experiment number 1, rate of the reaction is equal to 3 into 10 raised power minus 5. So R is equal to 3 into 10 raised power minus 5 is equal to K. I am writing as such. Concentration of NO in the first experiment is 5 into 10 raised power minus 3 raised power X. Concentration of H2 is 2.5 into 10 raised power minus 3 raised power Y. Calling this is equation number 1. Okay. Now, put the experiment number 2 data in the same rate law. So R in the second experiment is 9 into 10 raised power minus 5 is equal to rate constant is K. Concentration of NO in the second experiment is 15 into 10 raised power minus 3 raised power what? X. Concentration of H2 in the second experiment is 2.5 into 10 raised power minus 3 raised power Y. This is your equation number 2. Okay, this is your equation number 2. Now, what about equation number 3? In equation number 3, R is equal to 36 into 10 raised power minus 5. 36 into 10 raised power minus 5 is equal to K. Concentration of NO. Concentration of NO is 15 into 10 raised power minus 3, and this is raised power X. concentration of H2 in the third experiment is 10 into 10 raised power minus 3 raised power y. This is your equation 3. So how many equations I got? I got 3 equations. I got 3 equations. Now, my dear students, we have to solve these 3 equations. How exactly? Let's do one thing. Let me divide equation 2 with equation 1. When I divide equation 2 with equation 1, what do I get? 10 power minus 5, 10 power minus 5 cancel. 9 divided by 3 is 3 is equal to k and k cancel. This term entirely cancel. 10 power minus 3, 10 power minus 3 cancel. 15 divided by 5 is 3. So it is going to be 3 raised power x. So from this particular equation, I'm getting to know that x value is nothing but 1. X value is nothing but 1. Okay, number 1. Number 2, if I do one thing, if I divide equation 3 with equation 2, I'm dividing equation 3 with equation 2. So 10 power minus 5, 10 power minus 5 cancel. 36 divided by 9 is 4 is equal to this term is cancelled out. K and k gets cancelled out. 10 power minus 3, 10 power minus 3 cancelled out. So 10 divided by 2.5 is 4. So this is going to be 4 raised power y. So which tells us that y is also equal to 1. What was x and what was y? X was order with respect to NO. Y was order with respect to H2. I got both x and as well as y. So can I say the overall order of the reaction is nothing but x plus y, which is 1 plus 1. That comes out to be what? That comes out to be 2. Did you understand how do we deal with such kind of the question? Did you understand how do we deal with such kind of the question quickly? Everyone in the chats. Yeah? What is the first thing you need to do? You'll be writing the rate law, and accordingly you'll be fitting the data here, and you're done. And you are done. Correct? Okay? Now guys, I told you I'll be giving you the break exactly at 1:30. Before that, I'm not giving any sort of break. So please do not ask for it. Do not ask for it. Do not ask for it, okay? Break will be given exactly at what time? 1:30. Guys, it's not my birthday. My birthday is on 6th. 6th April is my birthday. Okay, so don't wish me right now in the chats. My birthday is tomorrow night. How do you know, by the way? Where will you get the DPP? DPP I'll be sharing on my Telegram, which is Wassim Bhat Chemistry Official. Which is Wassim Bhat Chemistry Official. There only I'll be sharing the DPP. Okay? All right. Perfect. Chalo, let's move on. Let's move on, guys. Now comes one more important thing. What is that? That is zero order reactions. Okay, zero order reaction. What exactly are zero order reactions? What exactly are zero order reactions? First of all, in simple words, that particular reaction whose order is 0 is what you call as zero order reaction. Yeah, let's try to understand this. Let's try to understand this. See guys, for example, you have got the reaction A gives B. I'm not going to derive anything. I'll be giving you the results and we'll be using those results in the questions. Not deriving anything because that's of no need to us right now at this moment. See, let's say I've got the reaction A gives B. I'm assuming that order, since you have got one reactant, so whatever is going to be order with respect to A, that's going to be the overall order of the reaction. So let's say order of this particular reaction is how much? That's 0. So it's a zero order reaction first of all. It's a zero order reaction first of all. Now at time t is equal to 0, initially, at time t is equal to 0, let the concentration of reactant be A naught. So the concentration of product here will be 0 because the reaction has not started yet. Okay. Now as the reaction proceeds, concentration of reactant will keep on decreasing and concentration of product will keep on increasing. Let's say at time t, the concentration of reactant left, that is AT. The concentration of product formed, that is for example BT. That's for example BT. Okay. So first of all, my dear students, you need to remember the meaning of these terms. What is A naught? What is A naught? A naught is the initial concentration of reactant at time t is equal to 0. What is AT exactly? AT is basically the concentration of reactant. The concentration of reactant left at time t. What is BT? BT is the concentration of product. BT is the concentration of product formed at time t. Formed at time t. Okay, formed at time t. Now, my dear students, try to understand. Try to understand. The first thing, if I ask you, how do we write rate law for this reaction? You will say R is equal to K, concentration of reactant raised per order, that's 0. This is your rate law. This is your rate law for this 0 order reaction. Now, my dear students, there is something called as integrated rate equation. There is something called as integrated rate equation for 0 order reactions. I'm telling you that I'm not deriving anything. I'm giving you the expressions and I'll show you how to use those expressions in the questions. So integrated rate equation for the 0 order reaction can be written like this. AT is equal to A naught minus KT. AT is equal to A naught minus KT. AT is equal to A naught minus KT. What is AT? Concentration of reactant left at time t. What is A naught? Initial concentration of reactant. What is K? K is the rate constant of the reaction. What is T? T is that time in which the concentration of reactant goes from A naught till AT. So this is my integrated rate equation for the 0 order reaction. Point number 1. Point number 1. Point number 2. That is point number 2. That is half-life of a 0 order reaction, which I'm representing with T 50%, or you can write it as T1 by 2. Half-life of a 0 order reaction. What is meant by half-life first of all? Half-life is defined as time taken to complete. Time taken to complete. Time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction, right? Time taken to complete 50% of the reaction is what we call as half-life. And remember, half-life in case of 0 order reaction is equal to A naught divided by 2K. A naught divided by 2K. This is the second thing which I would want every one of you to remember. Similarly, the third thing. What is that? That is completion time. That is completion time, which we represent with T 100%. What does it mean first of all? It means that time taken to complete 100% of the reaction. How much time does it take to complete 100% of the 0 order reaction? Its expression is A naught divided by K. A naught divided by K. Remember this particular thing as well? It is A naught divided by K. This was A naught by 2K. Okay, this is AT is equal to A naught minus KT. Perfect. Now, if you look at these two expressions, from these two expressions, can I say T 100% will be equal to 2 times T 50%, right? It means that because T 50% is A naught by 2K, T 100% is A naught by K. That means T 100% is 2 times T 50%. What does it mean? It means that a 0 order reaction is completed in. A 0 order reaction is 100% completed in 2 half-lives. A 0 order reaction is 100% completed in 2 half-lives. Okay? It is 100% completed in 2 half-lives. Am I clear with this? Am I clear with this quick? Okay, these are some expressions. Someone is saying, what do you want as the birthday gift? What can you send me? Yeah? What can you send me as a birthday gift? What's my age? What do you think? I'm 29. I'm going to turn 30. Yeah, 95 born I am, not 96. Okay, let's continue now. Let's continue. Rest of the questions you can ask me at the end. Rest of the questions you can ask me at the end. Okay. No, I'm not married. Listen now. Should we continue? Should we continue? My native place is, I'm from Srinagar, Jammu and Kashmir. I'm from Kashmir basically. Okay. So first of all, integrate rate equation for zero order reaction, AT is equal to A naught minus KT. T half is equal to A naught divided by 2K. Completion time is equal to A naught by K. A zero order reaction gets 100% completed in 2 half-lives. That is the third point, right? Similarly, the fourth point. Fourth point is what you call as degree of dissociation. Degree of dissociation in case of zero order reactions. That is alpha. Degree of dissociation in case of zero order reactions. That is alpha. And let me give you the direct expression. Alpha for the zero order reaction will be equal to KT divided by A naught. It will be equal to KT divided by A naught for the reaction A gives B. Remember it directly. Okay? Remember it directly. Perfect. Now, there are some graphs which we need to make related to zero order reactions. Graphs related to zero order reactions. Let's try to make those graphs as well. The first graph that can be asked here, that's between AT and T. This is the first graph which we'll be making. The second graph is going to be rate of reaction versus concentration of reactant. The third graph is going to be T half versus A naught. The fourth graph is going to be T 100% versus A naught. The next graph is going to be between alpha versus A naught. Alpha versus A naught. Now, my dear students, if you look at this particular graph first, you know rate of reaction is equal to rate constant multiplied by concentration of reactant raised power 0. This is the rate law. Okay. Anything raised power 0 is 1. So R is equal to K. So I will say rate of reaction is independent of concentration of reactant. Rate of reaction is independent of concentration of reactant. So if rate of reaction is independent of concentration of reactant, it's going to be a straight line, right? Now the second one, AT versus T. Few minutes back I told you AT is equal to A naught minus KT. Now this term you are plotting along y-axis, this term you are plotting along x-axis. This is your y, This is your x, this is your m, sign here is minus, and this is c. Y is equal to minus mx plus c. Straight line like this. So its slope is equal to minus k exactly. Okay. T half versus A naught. T half versus A naught. You know, when it comes to T half is equal to A naught divided by 2k. T half is equal to A naught divided by 2k. Since T half you are plotting along y-axis, A naught you are plotting along x-axis, this term is your m, y is equal to mx, means a straight line. And if you talk about its slope, slope means the value of m, which is nothing but 1 upon 2k. 1 upon 2k, right? And similarly, my dear students, T 100% versus A naught is again a straight line, and its slope will be equal to 1 upon k. And alpha versus A naught. Few minutes back, I told you alpha is equal to kt by A naught. So alpha and A naught are inversely proportional. Whenever there are two variables which are inversely proportional to each other, the nature of the curve is going to be rectangular hyperbola. It's going to be rectangular hyperbola. I hope this particular thing is also clear to you, right? And people at the same time, there are few things which I would want you guys to remember about zero order reactions. Where are they? Just a second. They are the examples of zero order reactions. These three examples, please and please do remember them when it comes to zero order reactions. One is the photochemical reaction between H2 and Cl2. Second is decomposition of NH3 over molybdenum. Third one is decomposition of Hi over gold. Okay, these are the three reactions which I would want every one of you to remember. Okay, they can be directly asked. They can be directly asked. Okay, so these are the three things, three examples of the zero order reactions. Please and please do remember them because they are mentioned on your NCERT text as well. All right. Now let's see what kind of questions can be framed from your zero order reactions. Let's have a look. Let me show you a few questions so that it will be clear to you, so that you can solve the questions basically. The question is, my dear students, a zero order reaction is 20% completed. You have got a zero order reaction A gives B, whose rate constant is, for example, K. Okay. It is 20% completed in 10 minutes. At what time it will be 80% completed? At what time it will be 80% completed? So first of all, initially, at time t is equal to 0, let the concentration of reactants A naught, this is 0. Now the first thing says, a zero order reaction is 20% completed in 10 minutes. So at t is equal to 10 minutes. At t is equal to 10 minutes. This reaction is 20% completed. And when the reaction will be 20% completed, what does that mean? That means 20% of reactant has got converted into product. That means 20% of reactant has got converted into product. If 20% reactant has got converted into product, how much reactant would be left? 80% of reactant would be left. So I would say 80% of A naught, 80% of A naught, which comes out to be 0.8 A naught. So this is the concentration of reactant left after 10 minutes. And concentration of reactant left is represented by what? It is represented by AT. It is represented by AT. So I got one condition. The condition is pretty much simple. At t is equal to 10 minutes, concentration of reactant left is 0.8 A naught. Okay. Now the question says, at what time the reaction would be 80% completed? At what time? At what time? At what time the reaction would be 80% completed? My dear students, if reaction is 80% completed, what does that mean? 80% of reactant has got converted into product. So that means 20% of reactant will be still left. So at time t, the concentration of reactant left would be 0.2 A naught. So basically, what do we have to check? At what time? At what time 80% reaction would have got completed? 80% reaction completed means 80% of the reactant would have got converted into product. So 20% of reactant will be left. And concentration of reactant left is represented by 80. So how many conditions I have? Two conditions. I've got two conditions here. Condition 1, condition 2. Now I'll be introducing these conditions into integrated rate equation, which is nothing but AT is equal to A naught minus KT. AT is equal to A naught minus KT. So put condition number 1. In condition number 1, AT is nothing but 0.8 A naught is equal to A naught minus K. T is nothing but, that is 10 minutes. Okay. So from this particular expression, K would be equal to 0.2 A naught divided by 10. So I got the value of rate constant from the first condition. Put the second condition in this expression now. AT is nothing but 0.2 A naught is equal to A naught minus K we have calculated, that is 0.2 A naught divided by 10 multiplied by T. And T is something I have to calculate. So A naught cancelled out. When you solve this, T value comes out to be 40 minutes, right? So I can say after 40 minutes, 80% of the reaction would have got completed. Okay? Right? Perfect. So remember guys, you'll be making two conditions. From condition 1, you'll be calculating the rate constant. And from condition number 2, you'll be calculating the time. That's how you solve these questions. Okay? That's how you solve these questions. Okay? Perfect. I hope I'm clear. My dear students, look at this type of the question. The question says, for example, you have got the reaction A gives B, whose rate constant is K. There is some data given, and from the data, I have to calculate rate constant of the reaction. Okay? I have to calculate rate constant of the reaction. Try to understand what I'll be saying. As per the data, at time t is equal to 0, concentration of reactant is 1 molar. So technically, I would say A naught value is equal to 1 molar. And at time t is equal to 120 seconds, concentration of reactant left is 0. What does that mean? That means this 120 seconds is the completion time. When the concentration of reactant is 0, that means this 120 seconds is the completion time. If 120 seconds is the completion time, that means T 100%. T 100% is nothing but A naught divided by K for a zero order reaction. That's 120. So K would be equal to A naught divided by 120. What is A naught? That's 1 divided by 120. And its units are simply going to be moles liter inverse second inverse because it's a zero order reaction. I hope I'm clear with this. Okay, I hope I'm clear with this. Examples of zero order reactions I've told you to remember. Now we are going to jump into the first order reactions. And before starting the first order reactions, let's take a small break. Okay, I'll be giving you the break, guys, but will you make sure that you'll be coming back? Will you be making sure that you are going to come back? If you remember, we started with, there were 2,400 people in the beginning. Right now, there are almost 900 people. Okay? Your competition is decreasing. It's decreasing. So imagine it like this. Consider it is like this. And this is the reality as well. Your competition is decreasing. Okay? Your competition is decreasing. Let's take a break for, till what time you'll be back? Tell me. Till what time you will be back? It's 120, 130, 135, 140. Yeah? So let's take a break till 1:40 a.m. Or I think 140 is too much. Let's take it as 135. No, okay. 140 is okay. But I would want everyone to be back on time. If that is a promise, then okay. All right? Yes, the competition is decreasing. So break till 1:40 and we'll be back. Let me have some coffee or tea. You guys can also have some coffee or tea, but be back on time, guys, okay? I'll be expecting everyone to be back. Okay? What's up, people? All alive? All alive? Yeah? All alive? Yes? Perfect, perfect, perfect. Yeah, good morning, good morning. Good morning. Good morning. All right, tell me, whatever things we discussed till now, is every single thing clear? Whatever things we discussed till now, is every single thing clear? I just want to know. By the way, it does not feel like we have been studying from past 6, 7 hours. Feels like I started in like 1 hour before. Honestly, I'm telling. It feels like I started like 1 hour before. Is it same with you as well? Is it only me who is feeling it, or you guys are feeling the same? No, I'm being very honest. I'm not kidding. I'm being very honest. It feels like we started like 1, 2 hours before, not 2 hours also. Yeah? So are you guys actually enjoying the session? Are you guys actually enjoying it then? That's great. If you're enjoying the session, that's fun then. That's good. That's good. All right. Chalo. Should we start now? Let's get going. Let's get started again. So guys, till now, we have discussed about zero order reactions. Now let's have a look on, I would say, the most important topic of the chapter. That is first order reactions. Why is it important? Because I'll tell you, whenever a question is framed from the chapter kinetics, most of the times the question is asked from first order reactions. Okay, so try to understand this first order reactions in depth. Okay, and I'll be showing you all the problem patterns. Don't worry about that. All right. Perfect. So let's get going then. Let's get started. So let's get started with the first order reactions. First order reactions. My dear students, like I gave you the expressions in the zero order reactions, in the similar way, I will be giving you the expressions for the first order reactions, and I'll show you how to apply them. Okay, have a look. First of all, let's say I've got the reaction A gives B, and I'm assuming its rate constant is K, and also I'm assuming order of this particular reaction is 1. Order of this particular reaction is 1. So it's the first order reaction. Now again, at time t is equal to 0, let the initial concentration of reactant is A0. This is 0. Now at time t, let the concentration of reactant left be AT. Let the concentration of product formed is equal to BT. Okay, is equal to BT. These are the things which we already know. Now, the first thing which you must know, what is that? That is, how do I write the rate law for this particular reaction? Rate law is simple. R is equal to K, that is rate constant, concentration of reactant raised per order, that's 1. So first of all, this is how you write rate law for the first order reaction. Correct? Point number 1. Point number 2, what is that? That is the integrated rate equation. Integrated rate equation for the first order reactions. Well, in case of zero order reactions, there was only one integrated rate equation. That was AT is equal to A naught minus KT. In case of first order reactions, there are different forms of the integrated rate equation. And what all different forms we have? Have a look. The first form is ln of AT is equal to ln of A naught minus KT. This is the first form of the integrated rate equation of the first order reactions. The next form is going to be log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This is the second form of the integrated rate equation in case of the first order reactions. The next expression of the integrated rate equation, that's going to be equal to K is equal to 1 divided by T ln of A naught divided by AT. This is the next expression for the first order reactions. Okay. Similarly, the next expression for the first order reactions, let's have a look on them. Let's have a look on them as well. The next expression for the integrated rate equation for the first order kinetics, that is K is equal to 2.303 divided by T. Now it is a log of A naught divided by AT. This is one more important equation. Okay. Similarly, we have got one more form of integrated rate equation for the first order reactions. What is that? That is AT is equal to A naught e raised power minus KT. I'm not deriving them. I'm just giving you the expressions. We have to remember them and we have to apply them in the questions. Then we have got one more thing. What is that? That is half-life. Time taken to complete 50% of the first order reaction is always equal to 0.693 divided by K. 0.693 divided by K. We have got one more expression here. What is that? That is completion time, T 100%. How much time does it take to complete 100% of the first order reaction? Remember, T 100% in case of first order reaction is infinite. What does that mean? That means it takes infinite time for the first order reaction to get 100% completed. That means technically a first order reaction never undergoes 100% completion. A first order reaction never undergoes 100% completion. Remember this point as well, it's important. First order reaction never undergoes 100% completion. It takes infinite time to complete. Okay. Now, my dear students, one more thing. What is that? Time taken to complete X% of a first order reaction. It can be 20%, 30%, 40%, 60%, 70%. How much time does it take for the X% of the first order reaction to complete? Okay. The expression here is 2.303 divided by K. It is a log of 100 divided by 100 minus X. This is one more important expression which I would request all of you to remember. Okay. Now the 10th expression. How do you calculate degree of dissociation? Degree of dissociation for the first order reaction. Degree of dissociation for the first order reaction is equal to 1 minus e raised power minus KT. 1 minus e raised power minus KT. This is the degree of dissociation in case of the first order reaction that we have A gives B. Okay. Directly remember, because all these expressions can be directly asked in your exam. Now, one more important thing. What is that? Time taken to complete 75% of a first order reaction is always equal to 2 times the time taken to complete 50% of the reaction. So T 75% is always equal to 2 times T half. One more important thing. Similarly, time taken to complete 87.5% of the first order reaction is equal to 3 times the half-life. Is equal to 3 times the half-life. Again, one important expression from which questions can be framed. Similarly, time taken to complete 99.9% of the first order reaction is equal to 10 times the half-life. Okay, 10 times the half-life. Remember this particular expression as well. Okay, these are some important expressions which are related to what? Which are related to first order reactions. Only these expressions you have to remember. Nothing more than this. Nothing more than this. Now, what is the next thing? That is, what all graphs can be made when it comes to the first order reactions. So graphs which are related to first order reactions. Remember that as well. See guys, the first graph which we are going to plot here, that is going to be between ln of AT versus T. This is the first graph which I'll be plotting. The second graph which I'll be plotting is going to be between log of AT versus T. This is the second graph which I'll be making. Similarly, the third graph which I'll be making is going to be rate versus concentration of reactant. Okay, it can be asked. Similarly, I want to make the graph between T half versus initial concentration of reactant. One more graph I want to make. Perfect. Right? Similarly, I want to make one more graph that is going to be between AT versus T. AT versus T. And at the end, I would want to make one more graph between AT versus T. AT versus T. These are the different graphs which can be made when it comes to the first order reactions. And anything can be asked from these graphs. Have a look. Try to understand. The first graph is between ln AT versus T. My dear students, if you remember, there is an equation which I gave you already. Ln AT is equal to ln A naught minus KT. Now tell me, this ln AT, I'm plotting along y-axis. Time, I'm plotting along x-axis. This is your M. The sign here is minus and this is C. So y is equal to minus mx plus C. Y is equal to minus mx plus C is a straight line with a negative slope. And I would say slope here is equal to minus K. Okay, the first graph. The second one is between log AT versus T. Second one is between log AT versus T. If you remember, log of AT is nothing but log of A naught minus K divided by 2.303 multiplied by T. Correct? Now, log AT I'm plotting along y-axis. Time I'm plotting along x-axis. This term becomes your M. The sign is minus and this is C. Y is equal to minus mx plus C. Again, a straight line like this. Similarly, if you talk about its slope is going to be minus K divided by 2.303. Minus K divided by 2.303. This is one more graph which you guys are going to make. Similarly, the next graph, that is the rate versus concentration of reactant. If you remember your rate law, R is equal to K, concentration of A raised power 1. Rate plotting along y-axis, concentration of reactant x-axis. This is your M. Y is equal to mx, means a straight line. So its slope is going to be equal to the value of K. As simple as that. The next graph is T half versus A naught. You know, your T half in case of first order reaction is 0.693 divided by K. So can I say half-life is independent of initial concentration of reactant? And if half-life is independent of initial concentration of reactant, it's going to be a straight line, of course, right? Now we have got AT versus T. I gave you one equation, if you remember, AT is equal to A naught E raised power minus KT. AT you are plotting along y-axis. This T you are plotting along x-axis. So the equation is of the format Y is equal to E raised power minus X type. Y is equal to E raised power minus X will be exponentially decreasing. It will be exponentially decreasing curve. Okay? It will be exponentially decreasing curve. Right? I think I have repeated the same AT versus T here. The next graph here is alpha versus A naught. Alpha versus A naught. My dear students, in case of first order reactions, I told you few minutes back. I told you a few minutes back. In case of first order reaction A gives B, alpha is equal to 1 minus e raised power minus kT. So in this expression, do you see A naught anywhere? No. So can I say alpha is independent of initial concentration of reactant? Yes. So it's a straight line. Alpha is independent of the initial concentration of reactant. These are some of the graphs which can be framed when it comes to the first order reactions. Now let's have a look on the different types of the questions which can be asked in the first order reactions. Try to understand one by one how I'll be solving these questions. My dear students, the first question. Look at the question carefully and I'm pretty much sure you can easily solve these questions. I'm pretty much sure you can easily solve these questions. The question says a first order reaction is 75% completed in how much time? In 100 minutes. A first order reaction is 75% completed in 100 minutes. The question says, how much time does it take to complete 87.5% of the reaction? A few minutes back I told you, time taken to complete 87.5% of the reaction is equal to 3 times the half-life. Is equal to 3 times the half-life. Time taken to complete 75% of the reaction is 2 times the half-life. So 2 times half-life is equal to 100, or I can say half-life here is equal to 50 minutes. If you got the half-life, so 3 times half-life is 50, the value comes out to be 150 minutes. So I would say it will take 150 minutes to complete 87.5% of the reaction. This is something which I was supposed to calculate. Am I clear with this? The expression which I gave you a few minutes back, I used the same expression and we are done. I used the same expression and we are done. It is sorted. Let's have a look on one more question. Let's see how you guys are going to solve this particular question. Hey guys, understand. Understand. For an elementary reaction, X gives Y plus Z. It's an elementary reaction. It's an elementary reaction. And if you remember, I have told you, in case of elementary reactions, order is equal to molecularity. Do you see the molecularity here? It's 1. If molecularity is 1, that means order of this particular reaction is also 1. So you got to know the reaction follows the first order kinetics. The reaction follows the first order kinetics. Now, as per the question, half-life of the reaction is given to me as 10 minutes. Half-life of this reaction is given to me as 10 minutes. If half-life is equal to 10 minutes, what does that mean? Half-life is 0.693 divided by K. This is equal to 10. So from here, K would be equal to 0.0693 and it's going to be minute inverse, right? This is going to be the rate constant. Now in the question they are asking, how much time, in what period of time would the concentration of X be reduced to 10% of its original value? First of all, tell me one thing. In what period of time would the concentration of X be reduced to 10% of its initial value? What does that mean? That means we have to calculate time taken to complete 90% of the reaction. Because when 90% of the reaction gets completed, then only 10% of the reactant will be left. Okay? Then only 10% of the reactant will be left. So technically, I'm supposed to calculate time taken to complete 90% of the reaction. This is to be calculated. Now, my dear students, if you remember, Tx%, I've already given you. Tx% is equal to 2.303 divided by K. It is log of 100 divided by 100 minus X, right? What is X? Percentage of the reaction to be completed. Now, X value here is 90. So I'll put the value of X as 90. So time taken to complete 90% of the reaction is equal to 2.303 divided by K. K is 0.0693 and it's log of 100 divided by 100 minus X. X is 90. 100 minus 90 is 10. 100 by 10 is 10. Log of 10 is 1. So this term entirely gets cancelled out. And when you solve this, I think this particular value will come out to be 33 minutes. So it will take 33 minutes. It will take 33 minutes for 90% of the reaction to get completed. Am I clear with this? Let me know once in the chats. Am I clear with this? Let me know once in the chats quickly. Everyone. Let me know once in the chats quickly. Everyone. Yeah? Perfect. Perfect, guys. Have a look on this particular question from again the first order kinetics. My dear students, the question is, an organic compound undergoes a first order decomposition. Time taken for its decomposition to 1/8 and 1/10 of its initial concentration are this and this respectively. Calculate this value. Understand what the question is. Understand what the question is. You have got the reaction, for example, A gives B, and the reaction is following the first order kinetics. Now, initially at time t is equal to 0, let the initial concentration of reactant is A0. This is 0. Now, in the question, they are mentioning one thing. At t is equal to t1/8. At time t is equal to t1/8. How much reactant is left? 1/8 of initial amount. This is the concentration of reactant left at this particular time. And concentration of reactant left, we represent with AT. So this is my first condition. At time t is equal to t1/8, this is the concentration of reactant left. Similarly, in the question, they are mentioning that at t is equal to t1/10, how much reactant is left? 1/10 of the initial concentration, 1/10 of A0. This is the concentration of reactant left at t is equal to t1/10. These are the two things which are given to me in the question. Okay? At time t is equal to t1/10, this is the concentration of reactant left. At t is equal to 1/8, this is the concentration of reactant left. So how many conditions did I get? I got two conditions. I got two conditions. My dear students, if you remember, a few minutes back, I gave you one expression. T is equal to 2.303 divided by K log of A0 divided by AT. This was your integrated rate equation. Okay. Now, if I put this particular condition here, right, instead of T, I'll be writing T1/8 is equal to 2.303 divided by K log of A0 divided by, what is AT here? AT here is A0 divided by 8. So A0 A0 gets cancelled out. 8 will come up. 8 will come up. And instead of 8, I can write simply 2 raised power 3 and log of m raised power n. That comes out to be n log m. So 3 comes to the front. 3 comes to the front. 3 and log 2. Log 2 is 0.3. Okay. Perfect. Now, similarly, if I put this expression, if I put this particular condition in this expression, instead of t, I'll be writing t1/10 is equal to 2.303 divided by k log of A0, I'm writing as such, divided by AT here is A0 divided by 10. So A0 did not cancel, 10 comes up, log 10 is 1. Perfect, so this term is over. Now, as per the question, what am I supposed to calculate? If you look carefully, as per the question, I'm supposed to get this value. That is T1/8 divided by T1/10 multiplied by 10. Tell me what is the value of T1/8? T1/8 is 2.303 divided by K. This into this is 0.9. All divided by. T1/10 is 2.303 divided by K. And we have to multiply it with 10 as well. So this term gets cancelled. 0.9 multiplied by 10. The value exactly comes out to be 9. Okay, this is something I was supposed to calculate. Am I clear with this? Am I clear with this? Yes? Am I clear with this? I hope these sort of questions you should be able to solve easily from now onwards. Easily from now onwards. Okay? Now, my dear students, there is one more topic in the first order reactions. What is that? That's kinetics of a gaseous first order reaction. This is also asked in the examination. This is also asked in the examination. Try to understand what I'll be doing. See guys. For example, you have got a reaction like this. A gas, it gives B gas plus C gas. This is the reaction. Every reactant and product is in gaseous state. Okay. Now you tell me one thing. You tell me one thing. You tell me one thing. At time t is equal to 0. At time t is equal to 0. Initially, at time t is equal to 0. Tell me how many gases will be there in the container. At time t is equal to 0. Tell me how many gases will be there in the container. Can I say at time t is equal to 0, there will be only A in the container? That means there will be only one gas in the container at time t is equal to 0. So initially at time t is equal to 0, whatever is the pressure of the system, that is due to A. That is due to A. Let that pressure is P naught. Let that pressure is P naught. Since at time t is equal to 0, B and C, they have not got formed. So pressure due to B and pressure due to C, initially at time t is equal to 0, has to be 0. Okay? Has to be 0. Now, my dear students, try to understand. When the reaction proceeds, moles of A will keep on decreasing. So pressure due to A will keep on decreasing. Moles of B and C will keep on increasing. That means pressure due to B and C will keep on increasing. Okay? So that means at time t, pressure due to A will be decreasing. So at time t, let the pressure due to A be P naught minus X. Okay? Now we use the stoichiometry. 1 mole of A gives 1 mole of B. So from X you get X. 1 gives 1. From X you get X. Okay? So can I say at time t, if I ask you what is the total pressure? What is the total pressure of the mixture at time t? Since at time t there are 3 gases present. At time t there are 3 gases present. Gas A, gas B, gas C. Pressure due to gas A is P naught minus X. Pressure due to gas B is X. Pressure due to gas C is X. So total pressure at time t, total pressure of the mixture at time t would be equal to P naught minus X plus X plus X, which is going to be equal to P naught plus X. So Pt is equal to P naught plus X. You can say X is equal to Pt minus P naught. X is equal to Pt minus P naught. I hope till here it's clear. I hope till here it's clear. I hope till here it's clear. Now, my dear students, try to understand one more thing. What is the question asked? Question is asked, you will be asked to write the rate constant expression. And if you know, in case of your first order reactions, K is equal to 2.303 divided by T. It is log of A naught divided by AT. This is the expression which we have discussed for the first order reactions. But my dear students, here in case of gaseous phase reactions, instead of A naught, what was A naught? Initial concentration of reactant. Here we are not going to use initial concentration of reactant. Here you will be using initial pressure of reactant. So this is P naught. What was AT? AT used to be concentration of reactant left at time t. Concentration of reactant left at time t. Here I'll be using pressure of reactant left at time t, which is P naught minus X. So K here is simply going to be 2.303 divided by T. It is the log of P naught divided by P naught minus. What is X? X is nothing but that is Pt minus P naught. Okay. Now P naught minus Pt plus P naught. It comes out to be 2 times P naught minus Pt. It comes out to be 2 times P naught minus Pt. 2 times P naught minus Pt. This is something which will be asked to you. That is the rate constant expression. And this is the rate constant expression which you have made over here. I hope this is clear to everyone. Lot of spammers have started to come and I'm blocking everyone one by one. Just a second. Yes, blocked. I hope this is clear. I hope this is clear to everyone. Yeah. So guys, this is asked. You'll be asked to calculate, you'll be asked to get the rate constant expression, and you have to make the rate constant expression like this. I hope you got to know how do we exactly do this. Now, my dear students, let's move on to one more topic. What is that? Just a second. What is that? Just a second. One more topic from which a theoretical question or maybe a numerical one, a small numerical can be asked. That is the collision theory. That is the collision theory. That is the collision theory. My dear students, first of all, let me tell you this collision theory, it is based on KTG, kinetic theory of gases. It is based on kinetic theory of gases, number one. Number two, as per collision theory is concerned, the molecules are considered to be hard and rigid spheres. The molecules are considered to be hard and rigid spheres. Try to understand what I'll be doing. Now, as per collision theory is concerned, for any reaction to happen, reacting species must collide first. For any reaction to happen, reacting species must collide first. Okay? Let me write this point because these are very, very, very important points. Please and please have an eye on these points. See, as per collision theory is concerned, for the reaction to happen, reacting species must collide. Reacting species must collide. Now, my dear students, not all the collisions between the reacting species will lead to the product formation. Not all the collisions will lead to the product formation. Not all the collisions will lead to the product formation. There are only some collisions between the reactants which will lead to the product formation. And those collisions are what you call as effective collisions. Not all the collisions will lead to the product formation. There are only some collisions between the reacting species which will lead to the product formation, right? And those collisions which will lead to the product formation, they are what you call as effective collisions. And for the collision to be effective, there are two factors which decide whether the collision is going to be effective or not. One is called as energy factor. And one is called as orientation factor. As per energy factor is concerned, for the collision to be effective, energy of reactants should be greater or equal to the activation energy. For the collision to be effective, as per energy factor, energy of reactants should be greater or equal to activation energy. And as per orientation factor is concerned, the reacting species must collide with proper orientation. They must collide with proper orientation. Now, people, let's try to understand this energy factor a bit more in detail. Try to understand what I'll be doing. For example, I've got, let's say, an endothermic reaction. Okay, I've got an endothermic reaction. Let the endothermic reaction be R gives P. If the reaction is endothermic, that means delta H. Delta H will be positive. What is delta H? That is EP minus ER. It has to be positive, which is possible only if EP is greater than ER. Now, my dear students, try to understand. As per energy factor is concerned, reacting species, they must collide and form a complex That's called as activate complex. And this activate complex breaks down and forms the product. Energy of activated complex is very, very, very high. And if energy of activated complex is high, that means its stability is low. Reacting species, they should collide and form the activated complex. And this activated complex breaks down into the product. Now, let's have a look on how to make it on the graph. This is, for example, energy on one side, and on another side, I'm representing progress of reaction. I'm representing progress of reaction. My dear students, at this particular point, progress of reaction is 0. That means the reaction has not started. Progress of reaction is 0. That means the reaction has not started. If the reaction has not started, we'll be having reactant with us, and energy carried by reactant is, for example, ER. Let's say this point represents your ER, energy of reactant. Now, reacting species, they should collide and form activated complex whose energy is more, right? Whose energy is more. So reacting species, they'll be colliding and forming the activated complex. Let's say this point represents your activated complex here, right? And this activated complex further breaks down into the product, and energy of products is greater than energy of reactants. So the graph will be somewhere here. This point represents the products, right? This point represents the products. And at the same time, my dear students, if you look carefully, this particular point here represents your energy of products, right? This particular line represents your energy of reactants, okay? Energy of reactants. Now, one thing, if you look carefully, first of all, I'll say as per energy factor, a collision is going to be effective when the reacting species will cross this barrier and form the products. As per energy factor, a collision is going to be effective when reacting species are going to collide and cross this energy barrier, right? Now, all the reacting species while colliding cannot cross the energy barrier. All the reacting species while colliding, they cannot cross the energy barrier. Let me tell you, all the reacting species, they do not have sufficient energy to cross the barrier. They do not have sufficient energy to cross the barrier. So let me tell you the minimum extra energy required by the reacting species, to cross the barrier is what you call as activation energy. Right? Activation energy. So my dear students, this particular energy gap from here to here is what you call as activation energy of forward reaction. Okay. Similarly, this particular gap is what you call as activation energy of backward reaction here. Now, my dear students, one more thing. Since if I talk about delta H was EP minus ER. This was EP from here to here. This was ER. So EP minus ER. That means this energy gap, EP minus ER. This energy gap, it used to be your delta H, right? Is there any other way to calculate delta H? This is the activation energy of forward reaction. This is the activation energy of backward reaction. Can I say delta H is also equal to EAF minus EAB? Remember this particular point as well. Delta H is equal to EAF minus EAB. Correct? Now. As per energy factor is concerned, a collision can be effective when reacting species can cross the energy barrier. Or I can say it simpler words. For the collision to be effective, as per energy factor, energy of reactants should be greater or equal to this barrier. If energy of reactants is greater or equal to this barrier, then only reacting species can cross the barrier and form the products. Okay? Can form the products. So for the collision to be effective as per energy factor, energy of reactants should be greater or equal to the activation energy barrier. Right? Now, my dear students, let me tell you one more thing. The fraction of molecules which have got energy greater or equal to activation, That means I'm talking about those molecules which are going to cross the barrier, right? It is given by e raised power minus Ea divided by RT. This e raised power minus Ea by RT is what you call as Boltzmann's factor. It is what you call as Boltzmann's factor. This term is what you call as Boltzmann's factor. This is what you call as Boltzmann's factor. Now people try to understand what I'm going to say. More the value of this term, more the value of this term, I'll say more fraction of molecules will have energy greater or equal to activation. That means more molecules will cross the barrier. If more molecules will cross the barrier, more will be the product formation. If more is the product formation, can I say faster is going to be the rate? Am I clear? Can I say faster is going to be the rate of the reaction? So, can I say your rate of reaction that is directly proportional to e raised power minus Ea divided by RT? Your rate of reaction, it is directly proportional to e raised power minus Ea divided by RT. Correct? I hope this is clear. And if this is clear, my dear students, then there is one more thing. There is one more thing which I would want to discuss with you. What is that? Here only I'm representing one more thing. That is collision frequency. That is collision frequency, which I'm representing with ZAB. Collision frequency, which I'm representing with ZAB. Now, how do you define the collision frequency? In simple words, I would say collision frequency is number of collisions taking place between the reacting species per unit volume, per unit volume, per unit time. Per unit volume, per unit time. Number of collisions happening between the reacting species per unit volume, per unit time. You tell me only one thing. More the collision frequency between the reacting species, that means more collisions will be happening. If more collisions are happening, what does that mean? That means more are the chances of effective collisions. If more are the chances of effective collisions, that means more product formation will be there, more will be the rate of reaction. So rate of reaction is also directly proportional to your collision frequency. It's also directly proportional to your collision frequency. Okay, perfect. One more important thing, guys. The graph which I made a few minutes back, that was for endothermic reaction. If I want to make the same graph for exothermic reaction, you can do that too. Energy versus progress of reaction. It is just in case of, in case of your exothermic reaction, the graph goes down. Energy of products is less than that of energy of reactants. This energy of reactants, and here it's going to be energy of products. Perfect. And this was your activation energy of forward reaction. This is your, from here to here, it is going to be activation energy of backward reaction. And this particular gap is what you call as delta H, which is nothing but EAF minus EAB. Perfect. This is for the exothermic reaction. I hope this is clear to everyone. I hope this is clear to everyone. Okay. Now, people, one more important thing. So I told you, as per energy factor is concerned, reacting species should have energy greater or equal to activation so that they can cross the barrier and form the products. Now, there is one more factor which decides whether the collision is going to be effective or not. That is orientation factor. That is orientation factor. In short, as per orientation factor is concerned, which I'm representing with P, as per orientation factor, the reacting molecules, the reacting species, they must collide with proper orientation. Proper orientation. They must collide with proper orientation. That orientation wherein the steric hindrance will be less. That orientation wherein the steric hindrance will be less. Now, guys, one thing. I told you rate of reaction. Here in the expression, it is e raised power minus Ca by RT. Right? There was one more important thing, that was ZAB. If I ask you whether this equation is complete or incomplete, I'll say this equation right now is incomplete. There is one thing missing. What is that? There is one thing missing. What is that in this expression? That is orientation factor. So put orientation factor here. So this becomes your one more equation as per collision theory to calculate rate of the reaction. Am I clear to everyone? Am I clear to everyone quickly in the chats? I hope this is super clear to everyone, and I hope you got to know What is the meaning of all this? Okay. So people, for the collision to be effective, how many factors we have to consider? 2 factors. One is energy factor, one is orientation factor. As per energy factor, energy of reactants should be greater or equal to activation. As per orientation factor, the reacting species, they have to do the collision with proper orientation. Okay. Both the factors are equally important. Both the factors are equally important. Okay. Both the factors are equally important. Now guys, there is one more thing which I would want to tell you here. What is that? That is effect of catalyst. That is effect of catalyst. What does a catalyst do? First of all, catalysts, they are of 2 types. They are of 2 types. One is positive catalyst. One is positive catalyst and one is negative catalyst. One is positive catalyst, one is negative catalyst. Positive catalyst, it speeds up the reaction. It increases the speed of the reaction. Negative catalyst, it decreases the speed of the reaction. How it happens? Remember. How it happens? Remember. See guys, here I am plotting a graph. It is between energy versus progress of reaction. See, without the catalyst, let the reaction profile is like this. This is in absence of catalyst. This is in absence of catalyst. This is in absence of catalyst. Okay? This is in absence of catalyst. This is in absence of catalyst. This is in absence of catalyst. Now, in presence of positive catalyst, what does a positive catalyst do? I told you positive catalyst speeds up the reaction. What does a positive catalyst do? Positive catalyst decreases the activation energy barrier. So basically, in presence of positive catalyst, the profile is going to be like this. Okay, the profile is going to be like this. This is in presence of positive catalyst. In presence of positive catalyst. So positive catalyst decreases the activation energy barrier. Whereas when it comes to the negative catalyst, let me tell you, negative catalyst increases the activation energy barrier. This is in presence of negative catalyst. Okay. Do remember these 3 things as well. These are again very, very important. Okay. I hope this is clear. Now, my dear students, there is one topic left here in case of your chemical kinetics. What is that? That is your Arrhenius equation. That is your Arrhenius equation. So let's have a look on what this Arrhenius equation exactly is all about. Okay, let's have a look on this as well. I hope till here it's clear. I hope till here it's clear. I hope till here it is clear. I hope till here all the things are super clear to you. Okay, let's have a look on Arrhenius equation now. My dear students, Arrhenius equation, you call it as the temperature dependence of rate constant as well. I told you in the beginning, if you remember, I told you on increasing the temperature, rate constant of a reaction increases. I told you in the beginning itself. Now we'll see how rate constant increases on increasing temperature. We'll see how rate constant increases on increasing the temperature. My dear students, we have got an equation which is like this. K is equal to A e raised power minus EA divided by RT. This is one of the forms of the Arrhenius equation, where K is what you call as rate constant, right? EA is your activation energy, right? EA is what you call as activation energy, right? A is what you call as pre-exponential factor. This is what you call as pre-exponential factor. And my dear students, A and EA are combinedly called as Arrhenius parameters. They're called as Arrhenius parameters. Okay. This e raised power minus CA by RT. As I told you already, this is called as your Boltzmann's factor. Now, if you look carefully, let's say I've got the reaction whose temperature I'm increasing. if I increase the temperature of the reaction, what happens to this value? Which value? EA divided by RT. If I increase the temperature of the reaction, that means I'm increasing the denominator. If I increase the denominator, this whole term will decrease. This entire term will decrease. If I multiply with minus, now this whole term will increase. Okay, now this whole term will increase. At the same time, if this term is increasing, that means E raised power minus CA by RT. See, if this power is increasing, that means this entire term is also increasing. Entire term will increase. If this entire term is increasing, if I multiply it with A, so A E raised power minus CA by RT, so this term will also increase. And if this term increases, that means rate constant of the reaction is increasing. As I told you already, when you increase the temperature of the reaction, rate constant of the reaction, it automatically increases. So K is directly proportional to T. Point number one. Point number two. Remember, on increasing the temperature of the reaction by 10 degree, rate constant doubles or becomes even more. When you increase the temperature of the reaction by 10 degree, rate constant of the reaction, either it exactly doubles or becomes more than that. Okay? Or becomes more than that. That is the reason why I'm going to define a term here. That is temperature coefficient. What is temperature coefficient? Temperature coefficient, which I'm representing with N, it is defined as rate constant of the reaction at temperature T plus 10 degree divided by the rate constant of the reaction at temperature T. Let the rate constant of the reaction at temperature T was K. Therefore, rate constant of the reaction at temperature T plus 10 degree, it can be 2 times K. K gets cancelled. The value comes out to be 2. Right? Over here, I'm assuming on increasing the temperature by 10 degree, rate constant doubles. But it can become more than that. I've told you rate constant becomes 2 times K. Some hero is coming. Temperature coefficient is not important, guys. Some hero is telling you in the chats. Yeah, I think he's the last year's NEET topper who's telling you this temperature coefficient is not important. Then why do you think I'm teaching this? Yeah. Okay, so here I assumed that rate constant is exactly doubling, right? But it can become slightly more. It can become 2.1K, 2.2K, 2.3K. Perfect? So, if it is 2.1K, then temperature coefficient is 2.1. If it is 2.2K, temperature coefficient is 2.2. If it is 2.3K, then temperature coefficient is 2.3. So, in general, remember, temperature coefficient value, it is greater or equal to 2, less than 3. It is greater or equal to 2, less than 3. Yeah? Perfect. I hope this is clear. I hope this is clear. I hope this is clear. Now, my dear students, there is one more thing which I would want to tell you here. What is that exactly? What is that? For example, you have got the reaction A gives B. Okay. When the reaction was carried out at temperature T1, rate constant of the reaction was, for example, K1. Or let me write it like this. Rate of the reaction was, for example, R1. When I'm changing the temperature of the reaction from T1 to T2, now rate of the reaction is R2. At temperature T1, rate of the reaction is R1. At temperature T2, rate of the reaction is R2. Okay, rate of the reaction is R2. Now, is there any relation between all these four? Absolutely, there is one relation which you have to remember. Okay, relation is like this. R2 divided by R1 is equal to 2 raised power delta T divided by 10. 2 raised power delta T divided by 10. This is one expression from which questions are frequently asked. Like, you have got a question like this. The question is, on increasing the temperature of the reaction from 10 degree to 100 degree, from 10 degree to 100 degree, how many times, or I'll say how many folds, rate of the reaction will increase? How many folds rate of the reaction will increase? So it's simply going to be R2 divided by R1 is going to be equal to 2 raised power delta T, change in temperature, final minus initial, that's 90 divided by 10, which comes out to be 9. So R2 is equal to R1 multiplied by 2 raised power 9. So I will say the new rate of the reaction is equal to 2 raised power 9 times the initial rate of the reaction. Okay? Is 2 raised power 9 times the initial rate of the reaction. So from this particular expression, question is asked. I hope this is clear. I hope this is clear to everyone. Okay. Now, few more expressions about this Arrhenius equation, and we are done. See, guys, as I gave you the equation as K is equal to A e raised power minus EA divided by RT. Okay. If I multiply this equation with ln, it becomes ln of K is equal to ln of A minus EA divided by RT. This is one more expression of the integrated rate equation. This is one more expression of the not the integrated equation. This is one more expression of your Arrhenius equation. This is one more expression of your Arrhenius equation. Or you can convert one more expression. You can write log of K is equal to, it's going to be log of A minus EA divided by 2.303, and this is R, this is T. This is one more expression of your Arrhenius equation. Okay, one more expression of your Arrhenius equation. Perfect. And my dear students, there is one more expression which I'll be writing here. That is log of K2 divided by K1 is equal to EA divided by 2.303 R, and it's going to be 1 upon T1 minus 1 upon T2. This is one more expression of your Arrhenius equation. This is one more expression of your Arrhenius equation. So these are different expressions which we have when it comes to our Arrhenius equation. Okay. So here, let's plot a graph between ln of K versus 1 by T. If you look at ln K versus 1 by T, the equation is going to be, the graph is going to be y is equal to minus mx plus c format, and its slope is simply going to be minus EA divided by R. And similarly, if you want to plot a graph between log of K versus 1 by T, log of K versus 1 by T, it's again going to be a straight line like this, and slope is minus EA divided by 2.303 R. Okay, perfect. These are the two things which I would want all of you to remember. Am I clear with this? Perfect, guys. Okay, one more thing I would want to tell you over here. One more thing I would want to tell you. That's the question basically. What kind of question is asked? For example, if you look at this question, these are two questions. This is not just the one question. This is not just the one question. Sakti, just remember its definition only. Okay? You don't have to do the kinetics of pseudo first order reaction. You just have to do the kinetics of zero order and first order. That's it. Moreover, kinetics of your first order gaseous phase reaction. Okay? Now guys, if you look at this particular question, we are given with a graph between log K versus 1 by T. And few minutes back I told you log K versus 1 by T. What about the slope of this graph? Slope of this graph is nothing but minus EA divided by 2.303. What is slope basically? Slope is tan of theta. Slope is tan of theta. Theta is tan inverse minus 3. That means tan of theta is equal to minus 3. That means tan of theta is equal to minus 3 here. So I can say your EA is equal to 2.303, this R also, 2.303 R multiplied by 3. Multiplied by 3. Now, as per the question, we have to calculate activation energy first in kilojoules per mole, then in kilocalories per mole. When we have to calculate activation energy in kilojoules per mole, so I'll be writing 2.303. R value I'll be taking as 8.314 joules per Kelvin per mole multiplied by 3, right? Since I've taken the value of R as 8.314 joules per Kelvin per mole, right now the answer is going to be in joules, but I want it in kilojoules. So divided by 1000, now it's going to be in kilojoules per mole, right? This is your activation energy in kilojoules per mole. Now, what about activation energy in kilocalories per mole? So what you have to do, it is 2.303, R value is 2 multiplied by 3. Since I have taken the R value as 2 calories, so the answer here is going to be in calories, but I want in kilocalories. So divide with 1000 and get the answer in kilocalories. Perfect. This is how you guys are going to solve these sort of questions. Okay, I hope this is clear. Similarly, one more question, which I believe you can do on your own. I believe this sort of a question you can do on your own. The question is the rate constant of the reaction. This is the initial temperature. Convert this in Kelvin. This is the final temperature. This is the initial rate constant. This is the final rate constant. What do we have to calculate? Activation energy. So which equation you guys are going to use? Log of K2 divided by K1 is equal to EA divided by 2.303 R. And this is 1 upon T1 minus 1 upon T2. See, K2 is given, K1 is given. R value we know. T1 is given, T2 is given. So you can calculate EA directly. So it's a simple basic question, just the calculation based one. Okay? Just the calculation based one. Nothing new. Nothing new, my dear students. Okay? As you can see, K1, K2 is given. R value you have introduced here. T1, T2 in Kelvin. And you just have to get the activation energy from here. I hope this particular point is also clear. Right? Now, one last question in the chemical kinetics chapter, which I'm giving you. See, the question is for a reaction. For a reaction with activation energy with EA is equal to 0. For the reaction with activation energy equal to 0. On let me write it like this. At 27 degrees centigrade, rate constant of the reaction is 1.2 into 10 raised power 3 second inverse. Calculate the rate constant of the reaction at 100 degrees centigrade. Can you give this question a try? Can you give this question a try? What is going to be the answer of this question? What do you think? What do you think? See guys, it's pretty much simple. We have got a reaction whose activation energy is 0. If activation energy is 0, K is equal to A, E raised power minus EA divided by RT. If activation energy is 0, anything raised power 0 is 1. So K is equal to A. So in that case, the reaction whose activation energy is 0, in that case, rate constant becomes temperature independent. Rate constant becomes temperature independent. If rate constant is temperature independent, that means if you increase or decrease the temperature, nothing happens to rate constant. Since you are increasing the temperature here, Nothing is going to happen to the rate constant. Rate constant value is still going to be the same, which is 1.2 into 10 raised power minus 3 second inverse. So with this, our chemical kinetics is also done and dusted. Okay, with this, our chemical kinetics is also done. Is it clear, guys? Is it clear? Tell me once in the chats. I hope this chapter is clear to you. I hope this particular chapter is also clear to you. Yeah? Now we are left with one chapter, that is electrochemistry. Are you guys sleepy? Are you guys sleepy? Sequential and parallel reactions don't study. Electrochemistry will take further, I think, yeah, 3 to 4 hours. Second and third order is not in the syllabus. Okay, let's take a break. But I would again want you guys to be back, okay? On time. So we have got a break till P5. Okay? 15-minute break I'm giving you, but I would want every one of you to be back and we'll be starting the electrochemistry. Second order reaction is not in the syllabus. Guys, whatever I've taught you, just study these topics, nothing else. Ishika, this is going to be enough. This much is going to be enough. Let's take a break for just 15 minutes, okay, and be back on time. All right? Yes, I'll try to cover electrochemistry fast. Don't worry. Hello, I'll see you after the break. All right. Is everyone back? Is everyone back? Yeah. So guys, ready for the electrochemistry? Ready for the electrochemistry? Wow, amazing. You guys are awake. That's great. Okay, whatever concepts we have discussed till now from the first topic itself, tell me once, is every single thing clear? Honestly, you can tell me. Honestly, you can tell me. I think this is the first time you guys are watching the long marathon. Is that? Is that? Is that? But guys, tomorrow you have to once revise it. Okay? Once you have to revise it tomorrow. Then only you can remember each and everything properly. Okay. Exactly. I can see the desperation of cracking NEET. That's great. I like it. This is the desperation of cracking the examination. And this is good. This is good. Okay. So let's get going then. Let's get going then. And let's try to complete this electrochemistry chapter as well. Okay. I'll again start from the basics only, from the scratch only. Don't worry. So, my dear students, in order to start the chapter electrochemistry, there are few things which I would want to tell you. There are few things which I would want to tell you. Some basic things, first of all. First of all, let's exactly check. Let's exactly know how to identify. Let's first of all know how to identify the oxidizing agents and reducing agents. Let's first of all know how to identify the oxidizing agents and reducing agents. After that, we'll start the chapter, because this particular topic I'll be using in the chapter electrochemistry. So you should know it first of all. For example, understand properly. Let's say I'm writing a reaction which is like this. Zinc solid plus copper dye positive aqueous. Let's say it gives zinc dye positive aqueous plus copper solid. Let's say this is the reaction which I've written over here. Okay. Now, my dear students, just tell me one thing. What is the charge on zinc here? It is 0. What is the charge on copper here? It is plus 2. What is the charge on zinc here? It is plus 2. What is the charge on copper here? It is 0. Right? Now, try to understand one thing. Oxidation state of zinc is changing from 0 to plus 2. Oxidation state of zinc is changing from 0 to plus 2. Oxidation state of copper is changing from plus 2 to 0. Okay. So can I say oxidation state of zinc is changing from 0 to plus 2? That means oxidation state of zinc is increasing. Similarly, oxidation state of copper is what? Oxidation state of copper is decreasing. Remember, increase in the oxidation state is what you call as oxidation. Increase in the oxidation state is what you call as oxidation. And oxidation involves loss of electrons. Oxidation involves loss of electrons. Similarly, my dear students, decrease in the oxidation state is what you call as a reduction. And let me tell you, reduction involves gain of electrons. Reduction involves gain of electrons. Now, my dear students, oxidation state of zinc is increasing. That means the zinc is undergoing oxidation. And the one that undergoes oxidation is called as reducing agent. The one that undergoes oxidation is called as reducing agent. In the similar way, oxidation state of copper is decreasing here. And decrease in the oxidation state is what you call as reduction. And let me tell you, the one that undergoes reduction, that is called as oxidizing agent. So this is how, first of all, you identify in a reaction which one is oxidizing agent and which one is reducing agent. Okay. Let me take one more example so that it becomes clear to you. My dear students, for example, I'm writing the reaction. H2 gas plus 2 times, for example, Ag positive. Let's say it gives 2 times H positive. And I'm writing 2 times Ag solid. This is the reaction which I have. In this particular reaction, I need to identify which one is the oxidizing agent and which one is the reducing agent. First of all, oxidation state of hydrogen here is 0. Silver is in +1 oxidation state. Hydrogen in +1, silver 0. Now try to understand. Hydrogen is going from 0 to +1. Increase. Increase means oxidation. So this hydrogen is undergoing oxidation. The one that undergoes oxidation is what I call as reducing agent. +1 to 0. Decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. And the one that undergoes reduction is something which I'll be calling as oxidizing agent. Is it clear to everyone? Quickly in the chats. Be active now. Is it clear to everyone? Yes, the one that undergoes oxidation is the reducing agent. The one that undergoes reduction is the oxidizing agent. That's all. Okay? Now, my dear students, the first topic which we are going to start here, what is that? That is going to be our Daniell cell. This is our first topic, the Daniell cell. First of all, Daniell cell is the typical example. It is the most common example of what? It is the most common example of the galvanic cell. It is the most common example of the galvanic cell. And what galvanic cell does? Galvanic cell, it converts chemical energy. Galvanic cell, it converts chemical energy into the electrical energy. Now we need to know, first of all, how this Daniell cell, which is the example of galvanic cell, how it converts chemical energy into the electrical energy. Try to understand what exactly I'll be doing. My dear students, in case of Daniell cell, we will be using 2 electrodes. In case of Daniell cell, we'll be using 2 electrodes. Understand what I'll be doing. For example, in this particular container, let's say I'm keeping zinc sulfate. Okay. The zinc sulfate which I'm keeping in the container, it would have got dissociated into zinc dye positives as well as SO4 dye negatives. Similarly, in this particular container, let's say I'm keeping copper sulfate. And this copper sulfate would have dissociated as copper dye positive plus SO4 dye negative. Okay. Now, my dear students, over here in this particular solution, I'm introducing a zinc rod. This is the zinc rod which I'm introducing here in the solution. At the same time, this is the copper rod which I'm introducing in this particular solution. So how many electrodes do we have? We have 2 electrodes. Okay, we have 2 electrodes. Yes, Kalpana, you can watch it. We have got 2 electrodes. Now, my dear students, these 2 electrodes, externally I'm connecting them with the help of emitter. And internally I'm connecting them with the help of inverted U-type tube. This is the inverted U-type tube. And this inverted U-type tube, what does it contain? This inverted U-type tube, let me write it over here. this inverted U-type tube, it contains inert electrolyte. It contains inert electrolyte, like your K2SO4, which is mixed with gelatin, or agar-agar. And let me tell you, when the inert electrolyte is mixed with gelatin or agar-agar, what do we get? We get a jelly-like paste. And that jelly-like paste is introduced in this inverted U-type tube. Okay? And its ends are sealed with the help of cotton balls. Okay? So first thing, if I ask you, what kind of ions are present in this inverted U-type tube? Since you have used K2SO4, so there will be K positives in this inverted U-type tube as well as SO4 dinegatives. Perfect. And my dear students, this inverted U-type tube is what you call as salt bridge. You call this as salt bridge. Now, this is first of all the construction of your Daniell cell. In case of Daniell cell, this zinc electrode, it behaves like anode, and your copper electrode, it behaves like cathode. And from now onwards, remember, at anode oxidation takes place. And at cathode, what happens? At cathode, reduction takes place. And you should know, oxidation involves loss of electrons and reduction involves gain of electrons. Right? Now, my dear students, as I told you, at anode, oxidation takes place. This rod is made up of zinc atoms, and those zinc atoms will undergo oxidation. Those zinc atoms of which a rod is made up of, they will undergo oxidation, they will lose electrons and get converted into zinc dipositives. These zinc dipositives, they will enter into the solution, and these electrons will be accumulated on the rod, due to which this rod gets the negative charge. Number one. Number two, at cathode, as I told you, reduction takes place. Since in this solution, there are copper dipositives, these copper dipositives which are there in the solution, they'll be colliding with the rod. They'll be taking 2 electrons from the rod. So copper dipositives which were there in the solution, they'll be taking 2 electrons from the rod and will get converted into copper solid. And that copper solid will start to deposit here on this particular electrode. Now, if copper dipositives are colliding with the rod, taking 2 electrons from the rod, can I say electrons are snatched from the rod, due to which this rod gets positive charge? Okay, electrons are accumulated here. If electrons are accumulated here on the rod, due to the oxidation of zinc rod. The path is already made. If electrons are here, there will be the moment of electrons in this direction. Right? There will be the moment of electrons in this direction. Perfect. Is it just the moment of electrons, or I'll say electrons are moving in a particular direction? I would say this is the directional moment of electrons. And whenever charge moves in a particular direction, what happens? Current is generated. Perfect. So the first question which is asked, what is the direction of electrons in case of Daniell cell? It is from anode to cathode. And if this is the direction of electrons, so what is going to be the direction of current? Current direction is always opposite to the direction of electrons. So current direction is going to be from cathode to anode. Correct? Perfect. So my dear students, what this Daniell cell is doing? Due to certain reactions, current is being generated. That is the work of the Daniell cell, right? To convert chemical energy into the electrical energy. Perfect. Since this is the reaction at anode, this is the reaction at cathode. My dear students, in order to write the net reaction, you have to make sure, electrons in both the reactions are balanced. Right now, electrons in both the reactions are balanced. So you can directly add these 2 reactions. And when you add these 2 reactions, your net reaction becomes zinc solid plus copper dipositive aqueous. What does it give us? It gives zinc dipositive aqueous plus copper solid. This is the net reaction which is taking place in the Daniell cell. How many electrons got exchanged here? How many electrons got cancelled? 2. Remember, N value here is 2. And N represents the number of moles of electrons exchanged between anode and cathode. Number of moles of electrons exchanged between anode and cathode. Okay, I hope this is clear. Perfect. Now, my dear students, this zinc rod is made of zinc atoms. Those zinc atoms are undergoing oxidation, right? Getting converted into zinc dipositives. Those zinc dipositives are entering into the solution, due to which thickness of this rod is decreasing. And similarly, thickness of this rod will be increasing because copper is being deposited on the rod. So, point number 2, which you are going to remember from now onwards. The thickness of zinc rod decrease with time, and the thickness of copper rod, that increase with time. That increase with time. Okay? I believe I'm clear to everyone. Now, this salt bridge which we have used, what are its functions? Remember its functions directly. First of all, this salt bridge, it is used to complete the internal circuit. The internal circuit, number 1. Number 2, this salt bridge, it helps to maintain the electrical neutrality. The electrical neutrality of both the solutions in both the containers. It helps to, right, maintain the electrical neutrality of both the solutions in both the containers. Or you can say it avoids the liquid junction potential. These are the 3 points which you will have to remember about the salt bridge. These are the 3 points which you have to remember about the salt bridge. Am I clear to everyone? Now, my dear students, what I told you in the beginning, this Daniel cell, it is the example of galvanic cell, which converts chemical energy into electrical energy. So you exactly saw how, due to some chemical reactions, due to certain chemical chains, electrical energy is produced. I hope this is clear to everyone. I hope this is clear to everyone. Am I clear till here? Quickly, let me know in the chats. If I'm clear to everyone, quickly, let me know in the chats. Quickly, let me know in the chats. Yeah? Now, my dear students, how do we represent a galvanic cell? How do we represent a galvanic cell? How do we represent a galvanic cell? See guys, there is one simple thing. First of all, you'll be drawing 2 lines in the middle. These 2 lines, they are going to represent your salt bridge. On the left side of the salt bridge, you'll be always mentioning anode. On the right side of the salt bridge, you'll be always mentioning your cathode. This is a small thing which you have to remember. This is a small thing which you have to remember. Okay? This is a small thing which you have to remember. On the left side, you'll be writing anode. On the right side, you'll be writing cathode. For example, how exactly? See guys, for example, this is a cell reaction, a net cell reaction happening in some galvanic cell. By looking at the cell reaction, I have to represent the cell. So how I'll be representing it? Understand. Its oxidation state here is 0. Here its oxidation state is +2. Here its oxidation state is +2. Here it is 0. Correct? Now 0 to +2, increase. Increase means oxidation. Increase means oxidation, and oxidation happens at anode. Oxidation happens at anode. Now, my dear students, +2 to 0, decrease. Decrease means reduction, and reduction takes place at cathode. So first of all, you identified your anode and cathode. After the identification of your anode and cathode, just draw 2 lines which represent your salt bridge. On the left side of the salt bridge, you have to write anode, and at anode, your zinc solid is getting converted into zinc dipositive. So zinc solid is getting converted into zinc dipositive aqueous. This is your anode. On the right side, you will be writing cathode. Right? And at cathode, reduction takes place. Copper dipositive gets converted into copper solid. So I will say copper dipositive aqueous gets converted into copper solid. So you have represented the cell successfully. Am I clear with this? Quickly? Am I clear with this, people? For example, you have got a galvanic cell in which this cell reaction is taking place. There is some galvanic cell in which this cell reaction is taking place. Okay. Now, with the help of this cell reaction, we have to represent the cell. How will you be representing the cell? See, its oxidation state is 0. Here it is +2. Here it is +2. Here it is 0. Now, 0 to +2, increase. Increase means oxidation. Oxidation takes place at anode. Right? So that means this is your cathode. You have identified anode and cathode. So these two lines, they'll be representing the solid bridge. On the left side, you'll be writing anode. And at anode, your Fe solid is getting converted into what? It is getting converted into Fe dye positive aqueous. Perfect. On the right side, cathode. At cathode, copper dye positive aqueous is gaining some electrons and getting converted into copper solid. So you have represented this cell as well. Okay. You have represented this cell as well. Yes, first timers can also watch this session. Don't worry. You'll understand it. All right, people. I hope this is clear. 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 Now, for example, you have got some galvanic cell in which this is the cell reaction that's taking place. This is the cell reaction that's taking place. Now, from this cell reaction, again, I have to represent the cell. First of all, if I calculate the oxidation state of chromium, I hope you know how to calculate oxidation state. This is 2x minus 14 is equal to -2. So chromium here is in +6 oxidation state. Iron is already in +2 oxidation state. Chromium here is in +3 oxidation state. Iron here is in +3 oxidation state. Correct? Now understand. +6 to +3, decrease. Decrease means reduction. And reduction takes place at cathode. So if this is my cathode, so automatically this becomes my anode. Automatically this becomes my anode. So in the middle, you have got solid bridge. On the left side of the solid bridge, what do you write? Anode. At anode, Fe dye positive aqueous gets converted. At anode, Fe dye positive aqueous gets converted into Fe tri-positive aqueous. Now tell me one thing. Is the state same here? Is the phase same? This is aqueous, aqueous. When the phase is same, you have to separate them with the help of comma. If the phase is different, you have to put a slash. Okay, like I was putting till now, slash. But right now the phase is same. When the phase is same, you have to put comma in between. Okay, you have to put comma in between. Am I clear? On the right side, you'll be writing cathode. And at cathode, this Cr2O7 dinegative aqueous is getting converted into chromium tripositive aqueous. Chromium tripositive aqueous. Again, the phase is same. So put a comma here. Put a comma here. Now, my dear students, one thing. First of all, till now, one of the substance used to be solid and another used to be aqueous. This used to be in the earlier, whatever examples I took, one used to be solid, one used to be aqueous. Apart from solid aqueous, whatever things you get, whether aqueous, whether gas aqueous, right? Apart from solid aqueous, whenever you see anything apart from solid aqueous, at that time, you'll be using platinum solid as well. So platinum solid here also, similarly, platinum solid here also. Because here also you have got aqueous, here also you have got aqueous. So apart from solid aqueous, whenever you see anything else, just use platinum solid as well. Okay, I believe this is clear to everyone. So this was how you represent your galvanic cells. Now the point is, if the cell is given to us, how do we write the cell reactions? If the cell is, wait, let me block some people who are wasting others' time. Blocked? Who else is to be blocked, guys? Who you were telling? Wait. Wait. Script, huh? Okay. My dear script, you are blocked. Mariam, you are blocked. Okay. Congratulations. Congrats. Who else? Tell me quick, tell me quick. Tell me quick. Yeah, I need not to ask anyone to block somebody. I have the channel access, everything. I do it on my own. So tell me quickly, who all? Who all are disturbing? Jaldi in the chats. Quick. Flora, bro, take care. You're out. Next. Next, quick. Batman is over. Is any Superman there? Batman is also over and out. Tell me the names, quick. Mr. Pratik is also over and out. Who else? Quick. I think that's it, yeah? All of them are done and dusted. Okay, so should we continue now? All right. See guys. For example, if a cell is given to us from the cell, how do we write the cell reactions? That's also important. From the cell, how do we write the cell reactions? Well, you have got gas, aqueous. So phase is different, a single line. You have got aqueous and aqueous. Over here, there won't be a single line, there will be comma. It's a mistake here, you can correct it. There's a comma in between. It's not a slash. It's a comma in between. Okay. Now, my dear students, on the left side of the salt bridge, what do we have? We have got anode. On the right side of the salt bridge, what do we have? We have got cathode. Now, first of all, at anode, what happens? At anode, oxidation takes place. At anode, oxidation takes place. See, hydrogen is going from 0 to +1. 0 to +1 means increase in oxidation state. Increase in oxidation state means oxidation. Oxidation means loss of electrons. So I would say when H2 gas will be getting converted into H positive aqueous, it will be losing electrons. Now, how many it will be losing? How many it will be losing? One hydrogen atom loses 1 electrons. So 2 hydrogen atoms will be losing 2 electrons, in short. Okay? Right? So this is the reaction taking place at anode. Similarly, what would be the reaction taking place at cathode? At cathode, reduction is taking place. Sn plus 4 is getting converted into +2. +4 to +2, decrease means reduction. Reduction means gain of electrons. So I would say Sn plus 4 aqueous would be gaining 2 electrons and getting converted into Sn plus 2 aqueous. Correct? In both the reactions, are the electrons balanced? I would say in both the reactions, electrons are balanced. And if the electrons are balanced, I can directly add them up. If the electrons are balanced, I can directly add them up. And when I'll be adding them up, these two electrons cancel. So net reaction is going to be H2 gas plus Sn plus 4 aqueous. What does it give me? It gives 2 times H positive aqueous plus what? Plus Sn plus 2. Okay, this is my net reaction. If this is my net reaction, how many moles of electrons are cancelled? 2. So N value here is 2. N value here is 2. One more thing. I want to write the reaction quotient expression for this particular reaction. How do we write the reaction quotient? We start with the product. This product is in aqueous state. The one that is in aqueous state, we use its concentration. So I write concentration of H positive raised by its stoichiometric coefficient 2. This is also in aqueous state. The one that's in aqueous state, use its concentration. Concentration of Sn di positive raised by its stoichiometric coefficient divided by, go to the reactant side. This is in gaseous state. The one that is in gaseous state, use its pressure. Pressure of H2 raised by stoichiometric coefficient, that is 1. Right? This is aqueous. So use its concentration. Sn plus 4 concentration raised power stoichiometric coefficient. This is how you write QC expression as well. Okay, perfect, simple. Whenever you want to write the QC expression, reaction quotient expression, product divided by reactant. That product or reactant which is in aqueous state, use concentration. If it is in gaseous state, use pressure. If there is pure solid or pure liquid, then H to mass is unity. As I told you in a law of mass section, if you remember, kinetics. Okay, I believe this is clear. I believe this is clear to everyone. I believe this is clear to everyone. For example, this is the cell that is given to us. Let's say zinc solid. This is zinc dye positive aqueous. This is a salt bridge. This is your copper dye positive aqueous. And this is your copper solid. Let's say this is the cell that's given to me. By looking at this cell, I have to write everything. First of all, on the left side, we have got anode. And at anode, if you look carefully, zinc will get converted into zinc dye positive. So zinc solid will get converted into zinc dye positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction at anode. Similarly, what is going to be the reaction at cathode? At cathode, reduction takes place. Copper dye positive is getting converted into copper. So I would say the reaction is going to be copper dye positive aqueous plus 2 electrons. Gives what? Gives copper solid. So my dear students, electrons are balanced in both the reactions. Just add them up. When you add them up, 2 electrons cancelled. So N value here comes out to be 2. What is going to be the net reaction? Net reaction is zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus copper solid. This is my net reaction. If this is my net reaction, my dear students, I will be writing QC. I'll be writing the QC value. So how do I write the QC value? Start with the product. This is an aqueous state. The one that is in aqueous state, use its concentration. So concentration of zinc dye positive, raised power stoichiometric coefficient 1. Okay. This is in solid state. The one that's in solid state, its H to mass is unity, 1, nothing to do, right? Divided by. This is in solid state, its H to mass is 1, nothing to do with this, right? This is copper dye positive in aqueous state, so use its concentration. So copper dye positive concentration, raised power stoichiometric coefficient. Perfect. So I believe you got to know how to write the cell reactions, how to get the N value, and how to get the QC value. If I'm clear, let me know once in the chats quick. Let me know once in the chats quick. Yes, Afifa, yes. All right. Perfect. Now, my dear students, there is one more thing. That's what you call as electrode potential. What is electrode potential, first of all? First of all, let me tell you, electrode potential we will be representing with E. Electrode potential we shall be representing with E. What is electrode potential exactly? I would say electrode potential is defined as the potential difference. The potential difference that gets created. The potential difference that gets created between the rod and the solution. Between the rod and the electrolytic solution. What does it mean? What does it mean? Try to understand what I'll be saying. My dear students, for example, I'm keeping zinc sulfate here. Let's say I've kept zinc sulfate. Let's say this zinc sulfate, it has got completely dissociated into its ions. Zinc dye positives and SO4 dye negatives. I'm assuming that in this particular solution, there are equal number of cations and anions. There are equal number of cations and anions, right? If there are equal number of cations and anions, I'll say this solution right now is electrically neutral, okay? Now, for example, I'm introducing a zinc rod. You have got a zinc rod here, okay? I'm introducing a zinc rod. So I'll be calling this entire setup as electrode. Now, this electrode can behave like anode or it can behave like cathode. For example, if the electrode behaves like anode, what happens? The zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation, will get converted into zinc dye positives, and those zinc dye positives will enter into the solution. The solution initially was electrically neutral. Now extra zinc dye positives are entering, due to which the solution gets positive charge. Since zinc atoms, of which the rod is made up of, those are losing 2 electrons, getting converted into zinc dye positive. Those 2 electrons are accumulated on the rod, due to which rod gets which charge? Rod gets negative charge. Solution is getting positive, rod is getting negative. Can I say between the rod and solution? Between the rod and solution, can I say potential difference got created? Potential difference got created between the rod and the solution. And this potential difference between the rod and the solution is what you call as electrode potential. This potential difference between the rod and the solution is what you call as electrode potential. Perfect. I hope you got to know what is electrode potential. Perfect. My dear students, let me tell you, electrode potential. Let me tell you, electrode potential. Electrode potential, when measured, electrode potential when measured under standard conditions. Under standard conditions. Under standard conditions. What are standard conditions? Standard conditions are, if pressure is kept as 1 bar, okay, pressure is kept as 1 bar, concentration of the solution is kept as 1 molar, right? And temperature is kept constant, generally 25 degrees centigrade. Temperature is kept constant, generally 25 degrees centigrade. This is what we call as standard conditions. And electrode potential when measured under standard conditions is called as standard electrode potential. Electrode potential. What is electrode potential? The potential difference that gets created between the rod and the solution. That's electrode potential. When electrode potential is measured under standard conditions, you call that as the standard electrode potential, which is represented by E naught. What is E naught? It is the standard electrode potential. And my dear students, this E naught is further of 2 types. One is called as standard oxidation potential. One is called as standard reduction potential. Now, how do we represent SOP? How do we represent SRP? SOP is represented like this. E naught of M gives Mn positive. Similarly, standard reduction potential is represented like this. E naught of Mn positive gives M. See how we can check this? See, oxidation state of M here is 0. Oxidation state of M here is plus N. 0 to plus N means increase in oxidation state. Increase in oxidation state means oxidation. Increase in oxidation state means oxidation. So this particular term, it represents your SOP, standard oxidation potential. Here, if you look carefully, plus N to 0. Plus N to 0 means decrease in oxidation state. Decrease in oxidation state is what you call as reduction. So this particular term, it represents your standard reduction potential. Okay. So that's how you identify whether you are given with SOP, whether you are given with SRP. And remember, my dear students, for every element, standard oxidation potential is equal to minus times its standard reduction potential. Okay. So if you know SOP of an element, you can calculate its SRP as well. You just have to reverse the sign. That's it. SOP of an element is always equal to minus times SRP of the same element. Okay. This is also one more important thing which you have to remember. And my dear students, one more important thing. SOP as well as SRP. Let me tell you, SOP of an element as well as SRP of an element is calculated with the help of a reference electrode. With the help of a reference electrode. And that reference electrode is called as standard hydrogen electrode. That reference electrode is called as the standard hydrogen electrode. Okay, remember this particular point as well. SOP as well as SRP of different elements, right? They are calculated with the help of a reference electrode, and that reference electrode is what we call as standard hydrogen electrode. I hope till here things are clear. And from electrode potential, if you want to solve the questions, then you have to remember 2 statements. From electrode potential, if you want to solve the questions easily, you just have to remember 2 statements. What are those statements? What are those statements? Remember, more the SOP of an element, More the SOP of an element. More is the tendency of an element to undergo oxidation. More the SOP of an element means more is the tendency of an element to undergo oxidation. The one that undergoes oxidation easily, that's always going to be a better reducing agent. That's always going to be a better reducing agent. The one that is the better reducing agent, its reducing power is more. Its reducing power is more. This is the first statement out of which questions can be framed. It is the first statement out of which questions can be framed. More the SOP of an element. More is the tendency of an element to undergo oxidation. Better reducing agent, more reducing power. My dear students, in the similar way, remember, more the SRP of an element, more is the tendency of the element to undergo reduction. The one that undergoes reduction, that's called as oxidizing agent. And the one that undergoes reduction easily, that's going to be the better oxidizing agent. The one that is the better oxidizing agent, its oxidizing power would be more. This is one more statement. If you just remember these two statements, you're sorted. You can solve each and every question when it comes to your electrode potential. When it comes to your electrode potential. Okay, these two things you have to remember. Is that clear? Is it clear till here? Is it clear till here? Tell me once in the chats. Is it clear till here? These two statements are very important. You have to remember them. Okay, amazing. Now, people, let's see what kind of questions can be framed here. Let's see what kind of questions can be framed here. Let's see what kind of questions can be framed here. Just a second. Okay, look at this question. Look at this question. If you look at all these reactions, in all these reactions, gain of electrons is happening. Gain of electron means reduction. So these are your SRP values. These are your SRP values. These are your SRP values. Okay. We have to check which of the following is the strongest reducing agent. See, first of all, reducing agent itself undergoes oxidation. I told you a few minutes back. And the one that undergoes oxidation easily, that would be better reducing agent. Which one undergoes oxidation easily? The one that has got more SOP. The one that has got more SOP. What are we given with? We are given with SRP values, but we need to convert them into SOPs. How do I convert them into SOPs? Just reverse their sign. Reverse their sign. SOP of, when you reverse the reaction, I will say magnesium will undergo oxidation. So SOP of magnesium would be plus 2.37. SOP of zinc will be plus 0.76. SOP of nickel will be plus 0.73. SOP of iron will be plus 0.04. Which one of the following has got maximum SOP? It is magnesium that has got maximum SOP. The one that has got maximum SOP will undergo oxidation easily, so better reducing agent. So magnesium is going to be the correct answer of the question. Am I clear? Am I clear, people? Am I clear? Everyone? Yes? Magnesium is going to be the correct answer. Now, my dear students, there is one more thing. How do we calculate the standard EMF of the cell? Standard EMF of the cell is represented like this, E0 cell. Standard EMF. The maximum potential difference between the electrodes. The maximum potential difference between the electrodes when the cell is not in use is called as EMF. The maximum potential difference between the electrodes when the cell is not in use is what you call as EMF. The point is, how do you calculate standard EMF? This is something which you have to remember. Standard EMF of the cell is equal to E0 of cathode minus E0 of anode. What is E0 of cathode here? Let me tell you, E0 of cathode here is SRP of cathode. E0 of anode is SRP of anode. Remember this particular result because this is important. Remember this result? This is important. Standard EMF of the cell is always equal to E naught of cathode minus E naught of anode. Okay? E naught cathode means SRP of cathode. E naught anode means SRP of anode. Okay? SRP of anode. My dear students, for example, here you have got a question. We are given with a complete cell. We are given with a complete cell. We have to calculate its E naught. And E naught cell, as I told you a few minutes back, it is nothing but E naught cathode minus E naught anode. E naught cathode minus E naught anode. What is E naught cathode here? It is nothing but it is SRP of cathode. And this is SRP of anode. Now, first of all, in this particular reaction, which one is anode, which one is cathode? See, zinc is undergoing oxidation. So, this is your anode. This automatically becomes your cathode. Now, my dear students, E naught of cathode means SRP of cathode, SRP of iron. Since this is SOP of iron, because in this reaction, oxidation is taking place, loss of electrons. This is SOP of iron. What do I need? I need SRP of iron. So, reverse the sign, it is minus 0.41. Minus E naught of anode, that's SRP of anode. This is SOP of anode. This is SOP of anode because loss of electrons is happening. What do I need? I need SRP of anode. So, reverse the sign again. So, it is minus 0.76. The value comes out to be 0.35 volts. This is your standard EMF of the cell, which I was supposed to calculate. Am I clear with this? Am I clear with this, people? Quickly. Yes? Okay. I hope I'm clear with this. So it is plus 0.35. Now, my dear students, one more thing. See, first of all, for example, let's say I have got 2 electrodes. I'm writing, for example, A naught of A positive gives A is equal to 1.1 volt. E naught of B gives B negative. It is equal to minus 3.1 volts. So tell me, first of all, how many electrodes do we have here? We have got 2 electrodes. We have got 2 electrodes. We have got 2 electrodes here. For example, I'm connecting these electrodes externally as well as internally. When I connect these electrodes externally as well as internally, I'll be getting a complete cell. I will be getting a complete cell. Now, for that complete cell, I need to calculate E naught cell. E naught cell is basically what? E naught cathode minus E naught anode. This is SRP of cathode, this is SRP of anode. So first of all, I need to check which one is your anode and which one is your cathode. So first of all, check over here. Plus 1 to 0, decrease means reduction, so this is SRP. Similarly, 0 to minus 1, decrease, reduction, so this is SRP. So which one among the two has got more SRP? This is more SRP. More the SRP, more the tendency to undergo reduction. And reduction takes place at cathode. So I identified this is my cathode and this is my anode. So I'll be writing E naught of cathode, which is SRP of cathode, which is 1.1 minus SRP of anode, which is minus 3.1. The value comes out to be 4.2 volts. This is E naught of the cell. This is E naught of the cell. Okay, this is E naught of the cell. I hope this is clear to everyone. Yeah? Perfect. Is it clear, guys? All clear to here? All right. So guys, here I'm writing one more important topic, that is delta G versus E cell. Delta G versus E cell. First of all, I'm not deriving any expression here. Remember it directly. Delta G is equal to minus NF E cell. This is the first result which I want all of you to remember. Delta G is equal to minus NF E cell. And if I write the same expression under standard conditions, then you write delta G naught is equal to minus NF E naught cell. Is equal to minus NF E naught cell. Now people, try to understand very carefully what I'm going to say. See, first of all, in order to make a cell, how many electrodes do we need? We need 2 electrodes. Okay, we need 2 electrodes. In order to make a cell, in order to make a complete cell, complete galvanic cell, I need 2 electrodes. Let's say I've got 2 electrodes. I'm connecting them externally and internally. After connecting them externally and internally, now I need to check whether the cell will work or not. Whether the cell will work or not. Let me tell you, how can you check whether the cell can work or not? See, I can take any 2 electrodes, connect them externally, internally. I'll be getting a complete cell. Now, will that cell work or not? On what factor that depends upon? My dear students, after connecting the cell, if automatically, spontaneously at anode oxidation takes place, at cathode reduction takes place, then the cell will work. So I will say, for the cell to work, for the cell to work, comma, the cell reactions must be spontaneous. And for the cell reactions to be spontaneous, delta G for the cell should be negative. For the cell reactions to be spontaneous, delta G for the cell should be negative. What is delta G? Delta G is minus NF E cell. So this whole term should come out to be negative. When can be this entire term negative? This entire term can only be negative if E cell is positive. So remember, that cell works whose delta G is negative and whose E cell is positive. That cell works whose delta G is negative and whose E cell is positive. Okay? So for any cell to be working means for any cell to produce current, its cell reactions must be spontaneous. And for the cell reactions to be spontaneous, we can say its delta G has to be negative, or you can say its E cell has to be positive. This is the criteria for the cell to work. Okay? Now people, reverse of it. If, for example, delta G for the cell is coming out to be positive, delta G means minus NF E cell. If this term is coming out to be positive, when can be this term positive? This term can be positive only if E cell is negative. If E cell is negative. So that particular cell whose delta G is positive or E cell is negative, for that particular cell, I'll say cell reactions are non-spontaneous. And if the cell reactions are non-spontaneous, I can say cell does not work. Cell does not work. Okay? Cell does not work. And my dear students, in the similar way, if delta G for the cell comes out to be 0, which means that E cell is equal to 0, at that point of time, we say the cell is at equilibrium. What is equilibrium condition? You'll get to know in some time. Okay? First of all, these 3 points are to be remembered. So from now onwards, whenever you have to check whether the cell is working or not, you have to check either delta G or E cell. If delta G is negative, E cell is positive, cell will work. If delta G is positive, E cell is negative, cell will not work. If delta G is 0, E cell is 0, cell is at equilibrium. Okay, cell is at equilibrium. It does not produce current at that time. Okay? Perfect. I hope it's clear till here. I hope it's clear till here. Now, my dear students, there is one more thing. What is that? One more important thing. That is your Nernst equation. That is your Nernst equation. We'll solve the questions in some time, okay? Nernst equation. So first of all, when do we use the Nernst equation? My dear students, first of all, Nernst equation is used. It is used to calculate. Nernst equation is used to calculate oxidation potential of the half cell. Half cell means electrode. Oxidation potential of the half cell under non-standard conditions. Under non-standard conditions. To calculate oxidation potential of the half cell under non-standard conditions. Number two, to calculate reduction potential of the half cell. To calculate reduction potential of the half cell under non-standard condition. Second use of the Nernst equation. Third use, to calculate EMF of the complete cell, again under non-standard conditions. These are the three main uses of what? These are the three main uses of the Nernst equation. These are the three main uses of what? Nernst equation. To calculate oxidation potential of the half cell, to calculate reduction potential of the half cell under non-standard conditions, and to calculate EMF of the complete cell under non-standard conditions. Under non-standard condition. Am I clear till here? Am I clear till here, my dear students? Let me know once in the chats. Everyone? Let me know once in the chats, everybody. Is it clear? Now guys, let's talk about this Nernst equation a bit more in detail. Okay, let's talk about the Nernst equation a bit more in detail. So first of all, I'm writing the Nernst equation for half cells. Half cells means electrodes. Nernst equation for half cells. Half cells means electrode. For example, this is a container, and in this particular container, you have got an electrolytic solution which contains, for example, Mn positive ions. Which contains Mn positive ions. Okay, Mn positive ions. And with this, you have got anions as well in the container. And I'm assuming there are equal number of cations and anions in the container, due to which the solution right now is electrically neutral. For example, here you are introducing a rod of metal M. You are introducing a rod of metal M. So if you look carefully, a rod is dipped, a rod is introduced into its own ions. A rod is introduced in a solution that contains its own ions. So this setup is called as electrode, right? This setup is called as electrode. Now this electrode, it can behave like cathode or it can behave like anode. For example, if the electrode behaves like cathode, at cathode what happens? Reduction takes place. So Mn positives in the solution, they'll collide with the rod, take some electrons from the rod. So the reaction is going to be Mn positive aqueous will be gaining some N electrons and getting converted into M solid. So in this reaction, how many moles of electrons are exchanged? N. Can you write the QC value? See, this is in solid form, hectomass 1. This is in aqueous form. So write concentration of Mn positive raised by 1. This is QC. Since I made sure that electrode behaves like cathode, at cathode reduction takes place, right? So basically, I want to calculate the reduction potential of the half cell. I want to calculate the reduction potential of the half cell under non-standard conditions. And how Nernst equation is used here? I'll write reduction potential of the half cell is equal to E naught RED, standard reduction potential, minus 0.0591 divided by N, and here I'm writing log of QC. This is your Nernst equation. This is your Nernst equation, right? When you have to calculate reduction potential of the half cell under non-standard conditions, this is how you guys are going to write the Nernst equation. Now, for example, if you want to calculate oxidation potential of this half cell under non-standard condition, oxidation takes place at anode, then I'll make sure this electrode behaves like anode. I'll make sure this electrode behaves like anode. And my dear students, at anode, what happens? Oxidation, right? So just reverse this reaction. The reaction is going to be M solid. It gives what? It gives Mn positive aqueous plus how many electrons? Plus N electrons. Plus N electrons. This is the reaction taking place when this electrode behaves like the anode. So how many moles of electrons are exchanged? N. Can you get the QC value? Start with the product. Concentration of Mn positive raised power 1 divided by this is solid, its active mass is 1. So in order to calculate oxidation potential of this half cell under non-standard conditions, I'll be again using the Nernst equation. How? I'll be writing oxidation potential of the half cell is equal to E naught OX, which is the standard oxidation potential, minus 0.0591 divided by N, and it's going to be log of QC. This is the Nernst equation for the half cell when you have to calculate its oxidation potential under non-standard conditions. Okay. This is the Nernst equation for the half cell when you have to calculate reduction potential under non-standard conditions. Am I clear? Am I clear, guys? Okay. Am I clear? So whenever you have to calculate oxidation potential and reduction potential of the half cells under non-standard conditions, this is how you guys are going to write your Nernst equations. Perfect. Perfect. Are you guys tired? Are you all tired? So basically, my dear students, okay, got it. So basically, as I told you, there are three main uses of Nernst equation. One, to calculate oxidation potential of the half cell under non-standard conditions. And when you have to calculate oxidation potential of the half cell under non-standard conditions, how do you write Nernst equation at that time? EOX is equal to E naught OX minus 0.0591 divided by N and its log of QC. This is when you have to calculate oxidation potential of the half cell under non-standard conditions. And similarly, when you have to calculate reduction potential of the half cell under non-standard conditions, you will be writing ERED is equal to E naught RED minus 0.0591 divided by N, and it's log of QC. This is the reduction potential of the half cell under non-standard conditions. And when you have to calculate EMF of the cell, when you have to calculate EMF of the complete cell under non-standard conditions, at that point of time, Nernst equation is written like this. E cell is equal to E naught cell minus 0.0591 divided by N, and it's log of QC. And it's log of QC. This is your Nernst equation for a complete cell. When you have to calculate EMF of a complete cell under non-standard conditions. Now someone is saying, what are non-standard conditions? What are standard conditions? When pressure is 1 bar, concentration 1 molar, and temperature constant. If you change any of these, let's say you keep pressure as 2 bar, that means these are non-standard. It becomes non-standard. If you keep concentration 5 molar, that means it's non-standard. Okay? Got it? Perfect. So these three things you have to remember. Nernst equation when we have to calculate oxidation potential of the half cell under non-standard. Nernst equation when we have to calculate reduction potential of the half cell under non-standard. Nernst equation when we have to calculate EMF of a complete cell under non-standard conditions. Got it? Got it, guys? Now all this will be clear when I'll be solving certain questions. So let's try to solve some questions so that it becomes clear. See, let's have a look on this simple question. Let's have a look on this particular question. Calculate the oxidation potential. Calculate the oxidation potential of the following half cell. We are given with the half cell. We are given with the electrode. Basically, if you look carefully, you have got a container, and in this container, you have taken FeSO4. Okay? And here you have introduced iron rod. So it is the half cell. Correct? The concentration of FeSO4 is given to me as 0.1 molar. If the concentration is 0.1 molar, that means, is the condition standard or non-standard? The condition is non-standard. So as per the question, we have to calculate oxidation potential of this half cell under non-standard conditions. Okay? First of all, in order to calculate oxidation potential, since oxidation takes place at anode, so I'll make sure this electrode behaves like anode. And when this electrode behaves like anode, what happens? Oxidation. This is 0, this is +2. 0 to +2 means increase. Increase means oxidation. Oxidation means loss of electrons. So the reaction has to be Fe solid will be getting converted into Fe dye positive aqueous plus how many electrons? Plus 2 electrons. So how many moles of electrons got exchanged? 2. So N value here is 2. If I want to write QC expression, QC is going to be concentration of Fe dye positive raised by stoichiometric coefficient divided by, this is solid, its active mass is 1. What is concentration of Fe dye positive? It is 0.1 molar, that means 10 raised power minus 1. That means 10 raised power minus 1. Now what do we have to do? What do we have to do? We have to calculate oxidation potential, right? We have to calculate oxidation potential under non-standard conditions. So use the Nernst equation. EOX is equal to E naught OX minus 0.0591 divided by N, and it's log of what? Log of QC. So I'll say EOX is equal to E naught OX is standard oxidation potential. In the question, check, are we given with SOP or SRP? See, +2 to 0. +2 to 0, decrease, reduction. So this SRP, what do I need? I need SOP. So reverse the sign. SOP is here, plus 0.44 minus 0.0591 divided by N value here is 2, log of QC is 10 raised power minus 1. Now it's a matter of calculation. Log of M raised power N is N log M. So minus 1 comes to the front. Log 10 is 1. So this becomes plus. Solve it. The answer is going to be in volts. The answer is going to be in volts. Am I clear? Yes, I'm drinking the water. Actually, the voice is cracking. Is it cracking a lot? Let me check. It's fine. I hope all the things are clear till here. Okay. All right, guys, one thing I forgot to tell you when I was teaching you the electrode potential. Remember that in case of hydrogen electrode, for hydrogen electrode, SOP as well as SRP, both the values are 0. For hydrogen electrode, SOP as well as SRP, both the values are 0. Okay? Just write that in your notes. For hydrogen electrode, SOP as well as SRP, both the values are equal to 0. For example, this is one question which we have. Calculate the oxidation potential of the following half cell. Look at the half cell. H2 is basically getting converted into H plus 1. Okay? In order to calculate oxidation potential, what do we have to do? Oxidation should take place, right? Oxidation takes place at anode. I'll make sure this electrode behaves like anode. And when this electrode behaves like anode, so at anode oxidation takes place, 0 to plus 1, increase, right? So H2 gas should get converted into 2 times H positive aqueous plus how many electrons? 2 electrons. This would be the reaction which would be taking place at anode. Okay? This is going to be the reaction which will be taking place at anode. Now, first of all, N value here is how much? N value here is 2. If you want to write the QC expression, it's going to be concentration of H positive raised by stoichiometric coefficient divided by pressure of H2 gas raised by its stoichiometric coefficient. What is the concentration of H positive? Concentration of H positive is 0.1 molar. That means 10 raised power minus 1 raised power 2 divided by. What is the partial pressure of H2? That is 10. The value comes out to be 10 raised power minus 2 divided by 10. The overall value is 10 raised power minus 3. So this is QC. What do I have to calculate? I have to calculate oxidation potential. So again, I'll write the Nernst equation. EOX is equal to E naught OX minus 0.0591 divided by N, and then it's log of QC, right? What is E naught of OX? SOP. SOP of this hydrogen electrode. SOP of hydrogen electrode as well as SRP of hydrogen electrode, both are 0, minus 0.0591 divided by, what is N value? N value is 2, log of, what is QC? QC is 10 raised power minus 3, right? When you solve this, it becomes minus 0.0591 divided by 2 log of M raised power N, which is N log N. So minus 3 comes to the front, right? Solve this and get the answer exactly in volts. Am I clear with this? Am I clear with this? Am I clear with this? Everyone? I hope this is clear. Yeah? So like this, you are going to solve this question. Okay. Now let's have a look on a question wherein you have to calculate EMF of a complete cell under non-standard conditions. Till now I was checking oxidation potential and reduction potential of the half cells under non-standard conditions. Now let's have a look on one question wherein we'll be calculating EMF of a complete cell under non-standard conditions. EMF of a complete cell under non-standard conditions. See guys, first of all, these two lines, they represent your salt bridge. On the left side of the salt bridge, what do we have? Anode. At anode, if you see, tin is getting converted into SN di positive. So 0 to plus 2. So write the reaction at anode first of all. SN solid is getting converted into SN di positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction at anode. Okay. Now reaction at cathode. PB di positive getting converted into PB. So reaction has to be PB di positive aqueous would be gaining 2 electrons, getting converted into PB solid. Okay, I got the reaction at anode, got the reaction at cathode. In both the reactions, if you look carefully, electrons are balanced. So I can directly add these two reactions. When I add these two reactions, this 2 and 2 got cancelled. My net reaction is Sn solid plus PB di positive aqueous. What does it give us? It gives Sn di positive aqueous plus PB solid. Plus PB solid. This is my net reaction. If I ask you what is the N value here? N value here is 2. What about the QC value? QC is going to be concentration of Sn di positive raised power stoichiometric coefficient divided by concentration of PB di positive raised power stoichiometric coefficient. Yeah. Now, what is the concentration of Sn di positive? It's 1 molar divided by. What is the concentration of PB di positive? It's 10 raised power minus 3. So overall, the value comes out to be 10 raised power 3. 10 raised power 3. So I got QC, I got N. There is one thing which is missing, which I want. What is that? That is E naught cell. E naught cell we have to calculate, and E naught cell I've told you already, that's E naught of cathode minus E naught of anode. SRP of cathode minus SRP of anode. SRP of cathode means SRP of this electrode, lead, and this is the SRP of lead electrode that's given, minus 0.13, minus SRP of anode, SRP of tin, that is again minus 0.14. The value comes out to be 0.01 volt. This is E naught cell. Now, we have to calculate EMF for this cell. We have to calculate EMF for this cell. So, I'll be using the Nernst equation, which is E cell is equal to E naught cell minus 0.0591 divided by N, and it's log of what? Log of QC. Your E naught cell is nothing but 0.01 minus 0.0591 divided by, what is the N value? N value we have calculated, that's 2 log of QC. QC is 10 raised power 3, and you know log of 10 raised power 3, 0.01 minus 0.0591 divided by 2 log of m raised power n is n log m, so 3 comes to the front. Solve this equation and you will be getting the value of EMF of the cell from here, right? Which is something I was supposed to be calculating. Am I clear with this? So this was your EMF part, my dear students. I hope this is clear. I hope this is clear. I hope this is clear. Yeah? I hope this is clear. Perfect, guys. What questions you'll be solving? You'll be solving the questions which I will be sharing on my Telegram. E cell is coming out to be negative. If E cell is coming out to be negative, that means cell reactions will be non-spontaneous. So the cell will not be working. Okay? Cell will not be working. All right. The Sn will be positive, I think. What Sn will be positive? What are you telling? Sn would be positive. What Sn would be positive? I did not understand what you're trying to say. I stopped because my throat is hurting. Just wait. Just wait. Last 11th physical chemistry one shot also I'll be taking. Don't worry. Guys, I think I'll end this session here only because my throat is hurting. Not able to talk properly. So there are few topics which are left here. I'll tell you what to do in those topics. Just a second. Okay? At least you can. You are not going to sleep right now. Just wait. Just wait. See, this is our channel, Unacademy NEET English. You will go into the live category. You will go into the live category. And in the live category, you'll click on popular. Once you click on popular, here is one video. Complete class 12th physical. And in this complete class 12th physical, I want you to watch 1.5 hours from here in this video. I'll tell you exactly from where to where. Because I don't think I can talk further. My throat is continuously hurting. from exactly, I'm giving you the timestamp, 6:15. Wait, 6:15, 6 hours, 15 minutes to 6 hours, 15 minutes to 6 hours, 15 minutes to 8 hours. Okay. This is the timestamp. Please and please watch these remaining. These are only few topics. Okay. Okay. These are some few topics. Yes, yes. This is good. This is good to go. Okay. This is good to go. So from 6:15 till 8. All right. Because my throat has started to ache, guys. Sorry about that. A PDF I'll be sharing on my Telegram. I'll be sharing the DPPs as well. Okay, I'll be sharing the DPPs as well. One thing, do not sleep right now. Please and please do complete this 1.5 hour. Huh? Do complete this 1.5 hour right now. Right now. Do not go to sleep. Okay? And do tell me in the comment section, yes, you have completed it. Do tell me in the comment section, yes, you have completed it. All right? Telegram channel name is Wassim Bhat Chemistry Official. You can search it. You'll be getting my Telegram channel, wherein I'll be sharing the PDF and all. All right? Rest of the things you will let me know in the comment section of this particular video. Whether you liked the session or not, do give me your honest review. Okay? I'll see you in the next session, and my next session is going to be inorganic chemistry marathon, which will happen for that will be done in 7-8 hours only. My next marathon is going to be inorganic chemistry marathon. Okay? Chalo, I'm taking a leave. Do let me know in the comment section whether you liked the session. Huh? Take care, guys. Bye-bye. See you.